Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience.
This meeting is being recorded.
Good morning, everyone, or afternoon or evening, wherever you are in the world, and welcome to the final day of NASA's 2020 Exploration Science Forum. I hope you've all enjoyed it as much as I have. It's been just a fantastic experience connecting with everyone. Before I introduce our two guests, I want to let all of you know that the survey will be available on our website shortly, and you'll also get a link to it on the email. We strongly encourage you to fill it out. We'd like to know where we did well. We'd like to know where we can improve things. So please do that if you wouldn't mind. So today, we're very privileged to have two of NASA's leaders in the area that we are so immersed in exploration science. I'd remind everyone that Mark Robinson shared the story of how he came up with the idea of exploration enables science and science enables exploration, which is just so foundational to what we do at Survey and what our whole community does. And so today we've brought two important people in this area together, Dr. Lori Glaze and Mark Hirasich. And Dr. Lori Glaze is the director of NASA's Science Mission Directorate's Planetary Science Division, where amongst many other things, she oversees projects and programs such as Perseverance, due to launch later this month, and Viper, and so many others. Prior to headquarters, Dr. Glaze served as the chief of the Planetary Geology, Geophysics, and Geochemistry Laboratory at Goddard Space Flight Center in Greenbelt, Maryland, and as the deputy director of Goddard's Solar System Exploration Division. Her research interests include physical processes in terrestrial and planetary volcanology, atmospheric transport and diffusion processes, and geologic mass movements. Mark Hirasich has been the director of the Orion program since 2015, and more recently took on the lead division position for Sustainable Moon within HEOMD, something this entire community is, of course, interested in. He began his NASA career in 1983 at the agency's Johnson Space Center in Houston, and as a member of the Space Shuttle Flight Operations Team, he quickly advanced to the position of lead Space Shuttle Payload Officer in Mission Control. In 1996, he was selected as a flight director in charge of planning and executing NASA human spaceflight missions, serving in that capacity for multiple Space Shuttle missions and International Space Station expeditions. So Lori Glaze and Mark Hirasich, welcome, and please go ahead. Thank you so much.
Well, good morning, Greg. This is Lori. Hopefully you can hear me. I'm trying to share my video. It had worked earlier, but I'm not seeing it yet.
Yeah, we can hear you just fine, but no video quite yet.
Okay. Yeah, it was working earlier. I'm not sure why. But anyway, I'm really delighted to be here with Mark to talk to you guys. Oh, there, my video just popped up on my screen. Good. So really happy to be here with you and with all of the Exploration Science Forum folks, and with Mark as well, whom I just personally met just very, very recently, but really, really excited with working with him, working together going forward. So I don't know if Mark wants to say a few words, and then you tell us how we want to go, what the format is you'd like us to follow.
You bet, you bet. Yeah, Mark, please go ahead. We're not hearing you.
How's this?
There, that's great, thank you.
Yeah, hey, Greg and Lori, thank you both for inviting me, and welcome. I realize this is the last day. Welcome to all the participants to this session. Greg mentioned as the introduction, I'm relatively new to this this part of NASA's enterprise. I've been at the Johnson Space Center since 1983, a long time. And it was 4 months ago Monday, that I became a headquarters employee for the first time, albeit I've been a headquarters employee from my living room here in Houston, as we've all been learning to live and work in this new way. So I'm relatively new, and Greg talked a little bit about my past. The last 5 years, I was the program manager of Orion, the spacecraft that's going to take people to these destinations, which was, by the way, every job I get, I pinch myself all the time, including this one. It was an incredible job. One of the things I do when I'm in a job, I'm heads down a lot, heads down. So I didn't really know about our lunar program other than Orion and SLS. And I'll tell you, 4 months ago, when I came to headquarters and assumed this new job, I was incredibly surprised with, first of all, the breadth of it and the thought that went into it, both on the elements, the human elements, as well as how integrated we were with the technology and science areas. So it was really surprising for me. And Jake Bleacher, who, by the way, I work very closely in my new job, and also Greg, have given me an introduction to Survey. And again, another surprise to me. I didn't know all these things were out there. I'm really impressed by the way Survey gives those of us who typically deal with large aerospace contractors a way to quickly and easily engage a broader set of people from industry, from academia, from universities, beyond the typical NASA workforce and the contractors we usually deal with. And when Greg arranged for a couple-hour briefing to introduce me, I was really impressed with the work. And a couple of things that really hit home. I said, boy, I'd like to learn about that immediately. And for example, many of you might know that just a week or so ago, on board the International Space Station, a Survey-developed tool was for the very first time a key part of the extravehicular activity or spacewalk that we did. And also some of the tools that the Survey community is developing for science. There's a really neat tool that allows you to visualize the surface of the moon, to plan science activities. And I said, boy, we're going to need that for human activities too, and let's not redevelop it. So the first couple of weeks, I was really impressed with the work, very anxious to incorporate the work into our human plans. And also, it's really important for us, Greg said, and by the way, I was told, by the way, your job is to develop a sustainable lunar program. I said, great, I can't wait. What does sustainable mean? So Greg's, many people have been helping me with that. First of all, it means, hey, we have to fit our budget, but it also means we in the human program, especially since it takes so many resources to put people places, we have to make sure the work we do is of value to a larger group of people, to, for example, the science community, to the technology community. And so what we're doing, and it's very important, and Jake is helping me a great deal with this, Jake Bleacher, we are making sure that as we embark upon building these human systems, the lander system, the gateway, the rovers, that we're being very conscientious in our requirements and our designs to make sure we put the hooks in place, to make sure we're thinking about what you all need to do, what science you'll need to do to make sure we can accommodate on our vehicles, on our infrastructures, things that will be important to you, things that will be important to more people on Earth to make this program sustainable. So thank you for inviting me here today. If I can have 2 or 3 more minutes, Lori and Greg, I wanted to share just a couple of charts to show our progress. This will be tricky too. Let's see, I'm new on Zoom. Let's see, share screen. Here it is. All right, hopefully, let me know when you can see this.
Yes, we see it.
Good, we'll go to slideshow mode. I hope if we've been doing our job, that most of this is old news, but this is really a few of the key milestones that my organization, Advanced Exploration Systems, really the human systems, a few of the key milestones that have happened over the past couple of months. None I had anything to do with, just inherited briefly, really when I arrived. But the first thing I'm sure everybody now knows that really the key piece that enables us to get back to the moon is the lander. And the Human Landing System program is being led by Lisa Watson Morgan and the Marshall Space Flight Center. They had a very big accomplishment, a very big milestone, the end of April, early May this year. There was a big competition. They picked 3 companies, actually groups of companies, to go to the next level in design of the human landers, Dynetics, SpaceX, and the national team. And really interesting, you can just tell by the pictures, we wanted competition, we wanted innovation, different ideas, and boy, did we get them. If you look closely, 3 completely different approaches to putting people back on the moon. The Dynetics approach on the left, where you've got this crew cabin very low to the ground. By the way, it is a single element that lands, and then we actually jettison those propellant tanks on the side before ascending. The SpaceX, also single element, incredibly different concept. If you haven't heard about it, it's a gigantic vehicle. We can put 100 tons of payload on the surface of the moon. And that, by the way, that is to scale there. Right in the middle, those are people descending on an elevator to the surface. Incredibly bold and innovative concept. And then the national team developed by Blue, led by Blue, with Lockheed, Northrop Grumman participating. If those of us who are more traditional NASA, you see it looks kind of their initial proposal, kind of like the Apollo liner. So 3 completely different ideas. So what Lisa did to herself, now they've got a really tough job. We're in something called the base period. And the base period, all 3 of these designs are being furthered. The requirement set is being honed in on. And by the end of the year, we're going to have final briefings from these folks such that we can down select, if you will, to preferably 2 to go to the next step, which is the design and manufacturing of the very first landers. And that we are on plan to do by next February next year. Another key piece in our sustainability is the International Gateway. It will allow us, first of all, to have a permanent orbiting facility around the moon. It's not going to be nearly as big as Space Station, but it provides a lot of capability. And a key part of the Gateway is it's international. Really, the pieces, the core pieces here, which is the power and propulsion element, and this habitation element here, are provided by us. We launched those in 2023. Here's the lander, by the way. Here's the lander. Here's Orion. All these other elements are provided by international partners. And another big milestone just this month, the memorandum of understanding, which is between the governments, actually even above NASA, it's between our State Department and the equivalent from all of these international partners, Canada, Europe, ESA, JAXA, Roscosmos. The Russians are not yet involved. They are not part of the Gateway MOU yet. They will be soon. We focused on these 3 international partners. That MOU that formalizes the Gateway plan and formalizes the international commitments is in the process of being signed by every one of the member international partners. So another big accomplishment. And then next week, the first, we have a series of human surface elements, rovers that provide mobility, habitats that provide longer duration stays so people can stay longer on the surface and explore further. To do things like science, like in situ resource processing. The very first one of those elements is this rover here. It's called an unpressurized rover, LTV or lunar terrain vehicle. Very simple, very similar to what several of the Apollo astronauts used on the surface of the moon. That's the very first of these, what we call surface elements, that we are going to build. And we are having our acquisition strategy meeting within our directorate on Tuesday. So what that does, that kicks off the process of, first of all, establishing a program office. This program office will be at NASA's Johnson Space Center, and then also kicks off allows us to go out and start planning requests for proposals to ask for industry inputs on the process. Which leads, how can you have a discussion like this without a swoosh chart? I've learned, I never knew what a swoosh chart was before I came to this new job, but this is a great depiction of our plan, beginning with, by the way, we pick up here after the 2024 landing, but this talks about how we continue to build the gateway through 2030, and then how we expand lunar surface capabilities. So we, for example, deliver the international habitat, ESA's contribution. We will have the first gateway-based lunar landing. The airlock, we'll get an airlock hopefully from our Roscosmos, and then finally the exploration control module. And you can see more buildup of the surface elements here. The pressurized rover, really incredible element, human element. Actually, I've been in a lot of spacecraft on the ground. I've been in the International Space Station on the ground. This thing is the coolest element I've ever seen for people, because they can live and work inside. It's like a space station-esque kind of a habitat for up to 14 days, 2 people, 14 days, but it's on wheels and you can go places. It's like an RV for the moon. Very cool. We are, by the way, going to try and develop this jointly with JAXA, a Japanese contribution to our plan. So we're just starting to talk about that and the habitat. So anyway, we have all of these items in our budget summit for this year, in our plan, on our timeline. So I did not know any of this. You know, the piece I was working on is this little itty bitty here spacecraft here called Orion for the last 5 years of my life. So you can imagine how excited I am to be a part of this. And first of all, have your help in having your help in us achieving this, as well as us being a key part of the science and the work we're going to do here on the moon. So, hey, thanks for your time. Greg, Lori, back to you.
Great. Thank you so much, Mark. Lori, I don't know if you wanted to say any other words of introduction. I do have a question whenever you're ready.
I would like to give just a little bit of prefatory before we go to Q&A, if that's okay.
Please.
Really want to take advantage of this opportunity to talk to your audience while they're gathered for the forum. I thought I'd start by just giving a really, really quick update on planetary science program. This will be very brief and just top level. I'll try not to talk too much here. But just give you a quick update. The Mars 2020 Perseverance rover is on schedule now for a launch on July 30th. This is a delay from the original launch date of July 17th. There were some issues with the processing of the launch vehicle, but those have been resolved. There was a repair that was needed. The team down there, the ULA team, did a phenomenal job in getting that repair executed very, very quickly. And we are now moving steadily towards that open of the launch window on July 30th. So keep an eye out for that. Another big event that's going to be coming up in the coming months for planetary is with OSIRIS-REx, which is our mission to collect a sample from the asteroid Bennu and bring it back to Earth. This community knows full well just how important those samples are to not only just understanding specific questions that we have now, but being preserved for the future generations. So we're very much looking forward to that. OSIRIS-REx successfully conducted an early test of their what they call the tag, the touch and go, where they're going to take the sample. They successfully completed that earlier in the spring. They've got one more rehearsal called the match point rehearsal coming up in August, and then the actual sample collection is scheduled for October. So keep an eye out for that. Really excited about that. Coming up in 2021, the next big events on our watch list are going to be the launches of DART, the Double Asteroid Redirection Test, and the launch of Lucy, which of course is the mission to visit several asteroids in the Jupiter system, the Trojan asteroids. So really excited about those two things coming up. I wanted to also take a quick moment to let folks know that we are keenly aware of the current situation with COVID-19. Not only is it making our lives to work and interact together more complicated, but we know that there are going to be sustained impacts on all of our flight missions. And of course, those are big, expensive things to begin with. And they have been working really hard to ensure the safety and health of all of the personnel, taking lots of precautions for social distancing, and a lot of work was stopped for quite a while. Some of it has started back up, but there will be cost impacts associated with COVID. We fully expect, we're tracking those as best we can continuously. Every week we get more information and try and track those. But for folks to know, as of today, right now, there is no special magical pot of money that's going to show up to cover those COVID impacts. And so we fully expect that we will have to deal with those coming in the future, and we have we have a fixed budget. So just so people know, this is going to be challenging for a long time to come. I think we're going to be feeling the impacts for a while. And as we have more information about how we plan to deal with those impacts, we will share those with everybody as soon as we can, as soon as we know information about how we'll deal with specific impacts. The last thing I wanted to mention quickly as a planetary update is just to mention the decadal survey, of course, is coming on us fast. We've got the 2 co-chairs named, which is fantastic. The panels are coming together, and the white papers are going to be due soon. And there was a lot of community concern about the deadline coming up on July, that just passed, actually July 4th was the original deadline. And there was a lot of concern that with COVID and other social unrest that people were not going to be able to meet that deadline. And the panel chairs have agreed to stagger the deadlines. And so the first one now is for science papers due on July 15th. And then there's additional deadlines in August and September for mission concepts, and then for additional white papers. So hopefully that has provided a little bit of relief for the community there. I wanted to take a moment and just say how excited we always are, but really, really excited to be working with the survey, with the SEO office, with Science and Technology office, with HEO, with Mark. So glad to have Mark here, and so glad to be partnering with him. Really trying to maximize that science that we can do through Artemis. I think survey is really key to that, and really we're very a proud sponsor of survey, and really happy to be able to continue our support for survey. And I think, Greg stated up front, and it can never get old, that, science enables exploration and exploration enables science. I think it's our mantra, and we stick with it. Working together, we can do some amazing things. So really glad to see us all continuing in that collaborative spirit. Quick update on Viper. Of course, Viper was, has evolved from something previously known as Resource Prospector. The SEO office, which was run by Steve Clark, and then currently by Ben Bussey in an acting role. They were able to revive Viper and get that started again. And in December and January, we successfully transitioned Viper over to Planetary Science Division. So we're now managing that, and just really excited about this mission. Not only does it do some great resource work in preparation for human exploration, but it's also a tremendous science mission on its own merit. And so very excited about leading that. I want to mention that we are intending to offer a participating scientist program for Viper. I don't have a release date for that yet, but I do want you to know, we expect to do that within this year, and that's in an attempt to try and expand the science team and expand participation in the Viper team. Last thing I'll mention is just Lunar Trailblazer, which is one of 3 small sat missions that were selected through Simplex. And of course, Lunar Trailblazer is going to the moon, and they are coming along in their development. They have a preliminary design review coming up in the fall, and they will be taking a ride on a heliophysics mission called IMAP. And so we're really excited watching how these small sats are starting to progress. And with that, I think I'll stop and allow us to take some questions.
Great. Well, thank you both so much for those excellent overviews. And I've said this before, I've been at NASA 35 years now, and I have never been more excited to be at NASA. And it's because of both what HUMD and SMD is doing. And so so I would like to do a kickoff question that was basically the same question that Thomas Zurbuchen asked Doug Libero last December, and that's, how can science help? And excuse me, in terms of this great voyage that Mark talked about. And maybe Lori, I'll give that to you first, and then Mark.
I'll start, but I really think, it's important that we hear from both sides, because we're here to help. Science really wants to not only provide data and information on environments at the moon that may be useful for planning or helpful in planning or selecting landing sites. So, lunar reconnaissance orbiter data, additional science that we're doing, and the work that's going on within SURVEY, but also as we're starting to think about, as we're going to put humans on the moon, what are they going to do when they get there? What's the best science that we can do with humans on the moon? And I think science plays a really important role there in helping to define what are the big questions that we'd really like that human expertise, physically on the surface. How can they help? So we need to work together to answer those. But I think there's a huge trade space there where science can come to the table. Great,
thank you, Mark. Do you have any thoughts on that?
Oh my God, yeah. I hope I can fit it in. Don't let me run over. Wow, a lot of different ways across the entire life cycle. First, now in our planning, we're building vehicles, we're building spacesuits, we're planning missions, and information from scientific information, from studies, from trials, from experiments on people, pre-breathe protocols are helping us every day inform timelines. How long does the crew have to pre-breathe before they can go out on a spacewalk? Information about on the surface of the moon, the environment, the radiation is helping us design our spacecraft. So there's this front end part of science that we're using today, that in day in and day out of our design cycle, that's helping us. There's that I'll call the unexpected things. I'm sitting in survey briefings that Greg set up, and I'm saying, wow, you guys have done that. We need to know more about that, because these guys over here can learn from that. Like, for example, this visualization tool that I had no idea we had written already. And then of course, the piece that Lori alluded to, the piece that is, I think, most important for the long term. So we can do this long term. We have to provide return back to our larger stakeholders, the public, the people who let us do these great things. So the science, the things we're going to learn that help life here on Earth, that help the average person here on Earth, are extremely important to get that defined, get that planned. The little bit of science, a lot of technology development, the what we call in situ resource processing, learning how to take materials on the moon and converting them into things that we can then use to either keep people alive or further our mission. So, Greg, I see it every day, how science is helping the human program.
Fantastic. Yeah, thank you so much. I love those answers, and we're honored to help that. So I'd like to call on Clive Neal, who has his hand raised.
Yeah, my hand is perpetually raised, but it's a condition. It's a feature, not a bug. Okay, a couple of questions for Mark. And Mark, it seems like you've been drinking from a fire hose for the last 4 months. But on your chart, you had the Lunar Terrain Vehicle arriving before the first mission. How are you going to make that happen? And keeping in the rover mind, you talked about the pressurized rover being an international development, but Johnson has already done a lot of development on such a vehicle. How are you leveraging that particular investment?
Yeah, great. Yeah, thanks, Clive. And you're right. It's been fun though. It's been a lot to learn, a lot to catch up on, and a lot to appreciate what everybody else has done to get us to this point. Let's see, your first question, LTV, when does it arrive before the first crew? And then how do we get it there, right? All right, I might have mistakenly portrayed it. Right now, our plan is to launch and land the unpressurized rover on the surface of the moon in 2025, which will be actually after the first lunar landing, before the second one. And there's several reasons for that. One, again, it is going to be so hard to get people to the moon for the first time. And it is an important goal to make 2024. We wanted to have a focus on getting people there for the first one. I'm glad you asked, how do we get the rover there, if that was your question. because I forgot that's yet another example of how the science, and in this case, NASA Science Mission Director is helping us. We're planning to use a CLPS lander. Are you familiar? Everybody's got CLPS, right? The acronym more on Commercial Lunar Payload Service, but it's a service that SMD, incredibly innovative, new way of contracting for a service to get things at the surface of the moon. We haven't actually done one yet. I'm very anxious to see how the first one works, but these first CLPS rover landers are going to take tens of kilograms, and then the second class is a 500 kilogram version. It's going to be used first to land the Viper that Lori talked about on the surface of the moon. There's a second mission that I believe is an STMD mission. Our rover would be the third. So it's great first of all, it's great that SMD's doing this, and it's really good to have that opportunity so we don't have to develop the lander. We can take advantage of something that's already been built. That was your first question. Lori, did you have something to add before I get to the other two, or the second?
No, I think you've covered that well. Go ahead.
Good. You popped up big on my screen, by the way, which is always great. Let's see. Clive, I think your second question was, we've done a lot of work at Johnson on the pressurized rover. Yeah, you're absolutely right. There's a couple of things, there's always, and I knew this, you guys all know this, when our job, our job depends on federal funding, on the country funding us. So we have to listen to our constituents that fund us and find out what's important to them. It is important. First of all, it's very important to our leadership at the moment to involve JAXA in a major surface element. That's number one. Number two, the Japanese and their auto industry, they have a very strong interest in rover type things. So there was an idea to, even though we have done a lot of work, to let the Japanese lead development of the pressurized rover. So right now, that's the direction we're heading in. But you're right, the people at Johnson, both the rover people, Rick Ambrose, Mike Ehrenhardt, their team, as well as the ECLS team from Marshall and Johnson, have done an incredible amount of work. And if you haven't been in the rovers at Johnson, everybody should try to get there. It is, I said it before, it is the coolest human element I've ever been in. They're on their third generation, and they've done a lot of work. They really understand how to build one. Now, we're not going to throw that away. What we're going to do is, first of all, we're going to let them lead. They're going to be the NASA lead in working with JAXA. And then I envision there's going to be a lot of interaction. So we're not throwing it away. We're going to use all of the work we've done to get to this point to help make the Japanese successful in their development. Was that it, Clive, or was there a third one? Sorry, I went on.
There's always more. I mean, but there's other people with their hands raised, so I'm going to be quiet now.
There are.
Thanks, Mark.
All right, thank you. And I want to be respectful of both of your time. There's one more question from Dana Hurley, if you have time for it, and maybe that's it. So Dana, please go ahead.
All right, thanks. Hey, so I mean, this is a very exciting time, and NASA is doing a lot of great things with lunar exploration. So my question is, on the PSD side, how are you going to handle lunar science missions and with the competed lines? Are lunar science missions going to be through the Discovery New Frontiers lines, or conversely, how can we get Discovery and New Frontiers and flagship level science out of CLPS and the human exploration missions?
Dan, that's a great question, and I think the way I like to think about it is we have a whole big palette of options out there right now, which I think is great. Certainly, Discovery is an option, and I do think that there will be opportunities for future lunar missions through Discovery, but I'd like to see something even more frequent available for that, whether that be through Simplex or through some type of CLPS opportunities. And so we're talking, of course, with the SEO folks about what kinds of things they're going to run through their office and what kind of opportunities. And we want to make sure that there are some lunar science things that we can make sure we're able to take advantage of what's going on in SEO, but also again through simplex opportunities as well. So that's kind of where what I'm thinking. I think we have that full palette of options there to us, and we're open to thinking about other types of possibilities as well. So hopefully that'll partly address your question.
All right, thanks.
All right, great. Well, I know we're 5 minutes over right now, and I would love to have about 2 or 3 hours of each of your time. And I just want to say thank you so much on behalf of this of Survey and this entire community. It's just an honor to help in this great quest. And we look forward to the next few years. There's a lot of exciting things coming up. So thank you very, very much, both of you, for joining us.
Thank you, Greg.
Thanks, Greg.
Thank you,
Thanks for
everybody.
letting us be a part. Bye-bye.
Okay, bye-bye.
Bye.
Okay, it's time right now to transition to the parallel sessions. So we can go ahead, and for those in the odd number session, please just stay here. And the chairs are Andy Shaner and Aisha Khatib for parallel session 5.
Good morning, Aisha. Hello, Hannah.
Good morning, everyone.
Good morning, afternoon, good afternoon.
Oh, yeah, sorry, I guess.
Sorry. Those of us on the East Coast.
Yeah. Well, that looks like Dr. John Keller.
Hello, Andy Shaner.
How are you, sir?
Good to see you after many decades.
It's been a while. Okay, do we have Hannah's here?
I'm here, and whenever you want me to share, go ahead and let me know. You've given me permission, right?
Wow.
Yeah, you have permission. Good morning, everyone. It's Christina, but I think you can go. The numbers have stabilized. We might as well kick it off.
That sounds great.
Okay, sounds good. Thank you, Christina.
Thank you.
All right. Well, welcome everybody to our session this morning on human health and education or public engagement. My name is Andy Shaner with the Public Engagement Lead at the Lunar and Planetary Institute. My co-chair today is Aisha. Aisha, you want to introduce yourself real quick?
Hello, everyone. My name is Aisha Khatib. I'm a first-year PhD student at the University of Maryland. Yeah.
Welcome.
Great. And just so a few reminders for our presenters today. Remember to please leave your mics muted and your cameras off. Then, of course, once it's your time to present, you can turn those on. You'll have 10 minutes to present, followed by 2 minutes for Q&A. At the 8-minute mark, our chairs will break in and let you know you're at 8 minutes. And a reminder, you have 2 minutes left. It will break in again at 10 minutes, let you know that your time is essentially up. During the Q&A session, if you have a question, you can either raise your hand using the Zoom tool. We'll then recognize you and we'll respond to those in the order they appear in the participant list. Or you can send a question through the chat box if you'd rather do it that way. So, okay. Well, if you want to go ahead and share your screen, Hannah.
Yep, I sure will. Okay.
Hey, Aisha, I'm going to hand it over to you now.
There we go. There we go. May I start? Andy, may I start? Okay.
Yes.
So Thank you. I'll go ahead and start since I didn't hear it right away. So what I want to really present today is sort of an overview of the strategy that we're employing in RISE 2 on how to develop the next generation understanding of lunar dust toxicity. This is, of course, particularly important now because of the commitment for manned exploration of the moon towards the eventual goal, of course, of a surface outpost. So there is something that we do know about lunar dust toxicity, and in fact, it was implemented for Artemis 1, so phase 1 of the Artemis mission, and it was based on the Lunar Airborne Dust Toxicity Assessment Group study, and that allowed the development of sort of permissible exposure limit. And this was based, however, on primarily rat inhalation exposure studies. And rat inhalation exposure studies are important, but what we believe very strongly, if we're going to move into the next generation of long-term human presence on the moon, is that we need to understand more about the toxicological hazard of respirable lunar dust. So we've been focusing on using a variety of biological techniques. Of course, the time-honored rat and mouse inhalation studies, recent results from the workshop on lunar dust in February of this year that suggested that perhaps mouse inhalation studies are better than the use of rats. But again, we are working on this and developing an inhalation chamber over the next year. The second thing that we've been working on, particularly with graduate student Jamie Chang, is exposure of human lung cells to lunar dust simulants. And this takes on a variety of directions. We've been looking at pulmonary cell viability after exposure, genotoxicity of both mitochondrial DNA damage and nuclear DNA damage, as well as mitochondrial reactive oxygen species level, which indicates mitochondrial dysfunction. And again, there's been recent discussion of the results of these experiments earlier this year. The other thing that we're working on, and the next talk is going to focus on the work by graduate student Donald Hendricks, is on the effect of minerals on OH radical production, which of course is known to cause a variety of inflammatory processes in the lungs. And for this, we're using a variety of available simulants in aqueous media, but also in this region, we're looking at ways to modify these available simulants. And these simulants are good because they're available in quantity that we need for these toxicology studies. But we're interested also in the kind of modifications that would make these simulants more relevant to the lunar surface and new simulants that capture some of the other toxic components of lunar dust. So we are interested in not only in diverse approaches to studying toxicology, but also in diverse lunar materials and analogs. Because what our strategy is to try to identify the most toxic components of lunar finds, which in turn will allow us more predictive capabilities as we move to different portions of the moon for our manned expeditions. And of course, part of this is what controls our toxicity, which helps us understand predictive information. So if we look at lunar finds, everyone knows that the primary constituents of lunar finds are the rock-forming silicates, minerals, as well as the volcanic and impact melt glasses. And many of these, of course, are concentrated in different parts of the regolith by the comminution of rocks, by meteorite and large and small impacts. And this is just a slide that was borrowed from Schrader et al., which was a very nice depiction of the fact that the lunar finds in the regolith have a different composition. So if the bulk regolith is shown here by this horizontal line, there is a different abundance of these silicate particles in the finds, which of course will contribute to the inhalation hazard. So how well do we actually know the effect of these silicate dust components? Well, we thought we knew a fair bit because we thought olivine was olivine as an example, but I don't want to steal Donald's thunder at the next talk, but just to suffice it to say that when we even look at something simple as olivine, there is a strong difference in composition, and that is how it relates to OH generation. So clearly we still need to look at the relative toxicity of mineral and glass component of lunar finds. The next thing that we have to be aware of in lunar finds is the presence of the agglutinates, these glass solid particle composites. And so we need to have a fair amount of these available to look at their toxicity. So we've been exploring mechanisms where we can actually generate our own agglutinates. So here's an example of what we have done by roasting JSC1A, shown here on the left, ground original, roasting in hydrogen at 900 degrees. And these are both at the same scale. This is 1 micron bar here and here. And what you can immediately see is that some of the larger particles are still retained, but we have made a very different texture, one that has a highly sintered texture, which enough structural integrity to support these elevated regions, these spires. And we were just in the process of looking to see if we indeed were able to make the glass in this process that we need when our analytical facilities were shut down due to COVID-19. But we will continue working on this. The important thing that we have been able to ascertain already is that this reduced material, in addition to the starting material, does affect human lung epithelial cell viability and cellular DNA damage. And this reduced material that you just saw results in a significant decrease in cell viability and increase in DNA damage. So basically what it's saying is that as we're producing material that is more relevant to the lunar surface, we may find a change in toxicity level that's important for us to understand. Another direction that we're working on, which is actually quite important also and has been undervalued, is the presence of sublimates in the lunar finds. So we all know about the lunar orange soil, we know about the presence of these glass beads, and the presence of sublimate coatings on these beads. Now these sublimate coatings are very friable and have contributed to the respirable fraction in these soils. And importantly, they include a variety of sulfides, fluorides, halide salts, and you can see a variety of elements here with a variety of toxicity that we need to understand what role these might play when the astronauts are exposed to these dusts. The other thing that we've realized now is that the sublimate coatings change upon exposure to the surface of the moon, and we need to know what happens to these in terms of if we're producing a variety of metals and lose the coordinating ligands, the fluoride and the chlorides, and sulfides, does this render this material more or less toxic? So this is actually a real problem because, again, we need to know what are these sublimates and what are their stabilities. So we have turned to experimentation as part of our efforts through RISE 2, and that is if we actually take lunar magma and allow it to boil using the volatile saturated materials that we can generate in the lab at given low FO2s, what are the nature of the gases that are escaping from this? And most importantly, what sublimates, what crystalline material do they produce? And how stable is this crystalline material? So to give you an example of the kinds of materials that we can produce through these experiments, here is an example. This was actually from
8 minutes.
Thank you. But you can see here what this does for us. This is just an example of an evacuated silica tube in which we've allowed Martian basalt that was doped with a variety of volatiles to boil. And in the process of boiling in a strong thermal gradient, we were able to trap a variety of sublimates. And shown here is an example of the sublimates that we can see quite clearly. We have, for example, maghemite. We won't expect this on the moon, but it really just shows that we get nice sized particles that can be analyzed. In the case for Mars, it's this maghemite is adhered to the surface by mollicite, which is an iron chloride, and above it is a zone of massive sulfides. But what this is showing on the right here is that by using SEM, and we're also going to be using the XRF and TES beamlines at Brookhaven National Lab, NSLS2, we can see that we would be able to identify the nature of these sublimates. Here, for example, is a beautiful crystal of pyrrhotite, vapor deposited pyrrhotite. And then we can then go and buy some of this material once we know what it is that we produced, for example, lead sulfide or lead chloride, buy them off the shelf and subject them to space weathering, analyze the product to that, and then add that to our toxicity studies. So what this has allowed us to do is to add experimental work into our analytical work on trying to figure out what exactly are the toxic material parts of the lunar finds. So in summary, what we want to be able to look at is to assess the toxicological hazard of respirable finds based on a variety of biological techniques through the Stony Brook School of Medicine as well as look at diverse lunar materials and analogs that we have made and analyzed so that we have a better idea of what it is that we are subjecting our toxicological studies to in more detail. So I want to thank you at this point and open up for questions.
Thank you, Hannah. Do we have time for questions, Aisha?
We do have time for questions. So if there's anything in the chat.
I don't see anything in the chat. And nobody's raising the hand yet.
Oh, there is a question in the chat. Paul Funteb asked, why do they need to be below 5 microns?
Okay, that's a great question. And this was actually brought up extensively in the Lunar Dust Workshop in February by the people who are working on these things in medical school. And basically the thought is that the 5 micron size is the particle size that goes most deeply into the lungs, and therefore has a much tougher time coming out. And therefore, as it sits there, there's a greater chance of inducing inflammation and other problems. The larger particles can be readily coughed out, and therefore they are not remaining within the lung pockets for as long.
There is another question. Ron Creel is asking, shouldn't we be looking at isolating the crews from all of these questions about effects on their well-being?
Exactly. We certainly would like to be able to do so. And that's, for Artemis 1, the goal was, what is the minimum grain size that we have to worry about, because we would like to essentially not worry about it, to be able to avoid inhalation hazards. And that's ultimately the goal we want, but we also need to set standards. So to what extent is the toxicity such that an X amount of exposure per day is permissible? So, yes, ultimately we would like to not expose them at all, but realistically speaking, we need to develop the technology for a permissible load.
Great. Okay. Thank you, Hannah. Okay. Let's move on to our next speaker. Donald Hendricks is going to talk to us about chemical reactivity and potential toxicity of lunar soils.
I think it's this one. So unfortunately, my camera is not working at the moment, so I will have it turned off.
Okay, no worries.
Okay, so thank you. So we go on just to the next slide. So the purpose of my work is to understand the health effects of lunar dust. And the way I do that is I look at the reactivity, or how much OH radicals generated by terrestrial minerals and lunar stimulants. And the reason I specifically look at OH radical is because OH radical is theorized to be cancerous to lung tissues. So I'm part of the RISE-2 team, and within that team, I'm part of the Theme 3 group. So what the group does is we probe the health effects of lunar dust. And so what we more specifically do is we try and develop the next generation of better lunar stimulants. I myself try to assess the reactivity of these stimulants, which is what I'm going to talk about today. And there's others in our group who look at the toxicity of these stimulants in cells and living animals. So far what we've done is we've obtained and characterized terrestrial minerals similar to what's found on the lunar surface. We've also obtained lunar stimulants, and we've tried to reduce them to sort of replicate some of the space weathering effects. And so far we've done this with JSC1A, LMS1, and LHS1. With all these materials, what we've done is we've measured the OH radical generated, or the reactivity of these materials, using a technique known as electron paramagnetic resonance spectroscopy, or EPR spectroscopy. So with EPR, we're able to measure the amount of radical in solids, liquids, and gases. In our case, we're measuring it in liquids. So first we started using JSC1A because that's kind of what we had readily available. So JSC1A was originally meant to be a lunar Mare simulant, and it was developed to primarily aid in engineering projects related to lunar exploration. So some physical properties like grain size and specific gravity are pretty much on point with what you observe in the lunar dust. There are, however, a lot of downsides to using a JSC1A. There is only a trace amount of pyroxene, and if you're trying to replicate the lunar Mare, that's no-go. The amount of plage present in JSC1A is too high to be an adequate Mare stimulant. the plage chemistry in JSC1A is between about AN64 and AN70. On the moon, you have about AN85 plus for most of the time. The olivine in JSC1A is too phosphoric, or there's too much magnesium present in the olivine. There are clay minerals present in JSC1A, and there's no clay minerals present on the moon. The JSC1A has too much titanium magnetite compared to ilmenite, but the primary drawbacks are that there's no agglutinated glass nor metallic iron, which are primary characteristics of lunar dust. So we decided to get better lunar simulants. So we got the Lunar Mare Simulant 1, or LMS1, and we got the Lunar Highland Simulant 1, or LHS1. So we have LHS1 here at the top, that I'm circling, and here at the bottom we have LMS1. So the main advantage of these two simulants are that the mineral proportions, or the percent like olivine, plage, and pyroxene, are very close to what you find in the Lunar Mare and the Lunar Highlands. However, there's still drawbacks in using the simulants in that they're deficient in iron and calcium, and there's too much magnesium, sodium, and potassium. And it kind of just highlights the disadvantage of having to rely on terrestrial materials in making lunar analogs. But again, the primary drawback are that there's no agglutinated glass nor metallic iron. So we can get around the metallic iron problem. And so what we did was we added some lunar simulant to the center of this glass tube. So I'm kind of circling right here in the middle where we put our samples. And this glass tube is being flushed with hydrogen. And when that's happening, we were able to put this glass tube into this furnace back here, and we heated up the sample 900 to 900 C for 15 minutes. And when we removed our sample, we noticed that the sample was darker. So that's how we know how we did, in fact, create some metallic iron on the surface. And here we have further proof that we created metallic iron. So this is an SEM image of a bunch of JSC1A grains. And you may notice that there's a bunch of little blebs all over the surface. So I'm kind of just going around pointing to some of the blebs on the surface. And these blue arrows are pointing to some random blebs just to make it a bit easier for people to see. And so that's in fact metallic iron. There was a study done like 25 years ago where they took Apollo samples and they ran it through a really similar reduction method that we used. And they were able to determine that all the little blebs that formed on the surfaces of their materials were in fact metallic iron. And so to measure the OH radical generated by these samples, what we did was we took about 200 milligrams of sample and we incubated it in a solution of DMPO. So this molecule right here is DMPO, and DMPO is able to trap radicals such as OH radical, which is made by the sample. And this then reacts to form this stable compound here on the left. And the EPR can then measure this compound because this compound has a very high half-life. So we have plenty of time to make our measurements. We can't measure OH radical directly because OH radical is extremely reactive by itself. So here we have some data that we obtained from our EPR. And so here for the graph on the left side, we have just various terrestrial minerals, and we plotted their reactivity on the y-axis from 0 to 1.4. And on the x-axis, we plotted their iron oxide weight percent content. And so here on the bottom left of the graph, we have minerals such as albite, bidenite, labradorite, and quartz. These are felsic minerals. These are minerals that are not rich in iron. And they're pretty much not that reactive. We use quartz as a control. There's not really much quartz found on the moon at all, but we use it as a control because it's known that it's not that reactive, and it came out around 0.1, which is around where we expected it to come out. Our mafic minerals, or our more iron-rich minerals like diopside, olivine, and augite, were much more reactive. Olivine and augite generated about 1 micromole of OH radical. So pretty much the main takeaway of this side is that the more iron oxide you have in a mineral sample, the more reactive it is. And here on the right side of the slide, we have our various lunar simulants. We have JSC1A right here on the left side of the graph. So non-reduced JSC1A makes only about 2 micromoles of OH radical, or a little bit less. But once we reduce it here, it makes almost 4. So it's a significant increase in reactivity upon adding metallic iron to the surface of our lunar simulant. Now let's move over to the Mare simulant. The non-reduced Mare simulant makes a little bit more than the non-reduced JSC1. It makes about 2, but if you look at the reduced Mare simulant, it makes more, but not that much more. This is kind of odd because the lunar Mare simulant has a lot of mafic or iron-rich minerals present. So I expected this data or this bar to be a lot higher, and it's not. So it's a bit odd. Now I want to try and go back and look at that again and see if we get those same results. For our Highland stimulant, the non-reduced one makes a little bit more than 1, so it's kind of as expected. There's not many iron-rich minerals present in the Highland stimulant, so it came out about where we expected it to. But then if you look at the reduced stimulant, the reduced Highland stimulant, it makes almost 3, so it's a significant increase in reactivity. And the main takeaway from this is that the addition of metallic iron causes a very large increase in reactivity. Because if you look at the numbers like 4, 2.5, close to 3, that is well above what you see on this side, where we're going from 0 to 1.4. So it seems that not only does iron oxide affect reactivity, but metallic iron does as well. And metallic iron seems to affect reactivity even more than just iron oxide content by itself. So this has a lot of implications for lunar dust reactivity, since lunar dust itself is known to have a lot of metallic iron. And so we talked about the lunar simulants, their reactivity, the terrestrial minerals and their reactivity, and how the more iron-rich materials are more reactive, how materials that have metal iron in them are even more reactive. But there are, of course, drawbacks in using these materials, and the fact that they're made of terrestrial minerals. So you're lacking the high amounts of iron and calcium you observe on the lunar surface, and you have too much magnesium, sodium, and potassium. So one way we can sort of get around this is we can make our own samples. And Hannah kind of touched on this a little bit in the previous talk. So here I have the, thanks. So here I have the olivine solid solution series. So we made a few different types of olivine in the lab in the past few months before all this started. So here, down here on the x-axis, we have here magnesium, Mg2SiO4 or 4 straight, and at the end we have phthalate or Fe2SiO4. And interestingly enough, the end numbers are really not that reactive, but once you start moving towards the middle, the reactivity actually keeps on rising until you get to this peak right here, right at the 50-50 mark. So this is a really interesting result. We had no idea what was going to happen when we ran this. We actually thought that the phthalate, the Fe2SiO4, would be the most reactive because, as I said in the previous few slides, that the more iron oxide you have in a silicate mineral, the more reactive it is. But for some reason, it is our least reactive mineral, pretty similar to that of the 4 straight, which has virtually no FeO in it. This is a very interesting result. So the good thing about this is that we can see what the reactivity looks like across the olivine solid solution series, but we don't know why the reactivity shows up the way it does. So that's something that we have to look at in the future. It's going to be a really big challenge for us. And I also plotted the olivine from the previous slide. This is actually San Carlos olivine. This is FO91, so it plots around here. And it's not super far from this trend line. So it's very likely that that the left side of this graph is probably going to look a little bit like it does here on the right side. And so to conclude, metallic iron on the surface of our lunar simulants caused a significant increase in reactivity. So it seems that metallic iron causes a much larger increase in reactivity compared to just iron oxide by itself. The lunar Mare simulant, which has more mafic materials, generated about twice as much OH radical as the Highland simulant, which doesn't have that much mafic material in it. And when we look at the individual minerals themselves, iron-rich minerals generate much more OH radical or much more reactive compared to felsic minerals. And so by looking at reactivity on a mineral by mineral basis, like we did with olivine, like looking at just a solution series, is that we can see how reactivity changes across a mineral solution series, and we can actually make what's on the moon. We don't have to rely on these very hard to get lunar dust samples. We can just make whatever we want in the lab, although it's not in very large quantities to be like a stimulant that we can sell in kilograms. It's very, we can make enough for our work. And so that's one advantage of that. We can just make what's on the moon, and we don't have to worry so much about impurities, because with terrestrial minerals, you might have some like clay minerals present in your minerals. And so we don't want that because there's no clay minerals on the moon, and that might alter the results a little bit. And so I'd like to thank all these people here, and I'll take any questions you may have.
Thank you, Donald. We have one question in the participant. Micah Shabel has raised his hand. Micah, you can go ahead.
Hey, Donald. Great talk. That was very interesting. So I had sort of two questions. The first was, I didn't see where, maybe you mentioned it, but I didn't see you mention the FeO content of the simulants. And secondly, did you do anything to those simulants before you tested for the unreduced ones? Did you do anything to just the powders before you tested their reactivity?
So for these powders, what I do for all of them is I hand grind them for like about I'm moving this. I hand grind them for like about 10 minutes by hand before I test their reactivity. And so by doing that, we're sort of trying to simulate space weathering to some extent. So space weathering is known to break bonds in lunar dust. And so by mechanically altering our samples, we're actually making them more reactive. We're breaking bonds on the surfaces, and thus we're seeing higher reactivity. So I pretty much just grind them. But when I test the reactivity of both the reduced and the non-reduced, I do the same thing. I just grind them by hand for 10 minutes, and then I test the reactivity.
So the other part was, did you measure the FeO content of the simulants?
So we do have the FeO contents of them. So for the Highland simulant, it's around 3. And for the Mari simulant, it's around 8. So let me go back to that. You want me to go back to that slide? I can go back.
Yeah, that's exactly what I was hoping for. Yeah, right there.
Yeah, so I didn't plot them on this because this is data I had from like an old publication. This is the one on that I'm circling now is more recent data. But yeah, the Lunar Mari estimate has significantly more FeO content versus the Highland simulant itself.
Gotcha. Thank you.
Yes, of course.
Okay, thank you again, Donald. I think we should move on to the next talk. The next talk is going to be by Andy Shaner, and it's Scientists Should Engage Young Students, Why and How. So whenever you're ready, Andy.
Great, thank you. So I don't know if it's fortuitous or maybe it was planned that yesterday Amy Fagan and Ryan Watkins were talking about importance of mentoring and the next generation, because there are 2 elements that I'll be addressing in my presentation this morning. Sorry. There we go. So just from the National Science and Technology Council's Committee on Science, Technology, Education, and Mathematics, or STEM Education Committee, that basically, like many of us, all of us know here, to really be able to function well in today's society with the technology and with what we see going on with the pandemic, people really need to be good about having good evidence-based reasoning skills. Okay, but there's a problem, at least here in the US, with that. Across numerous national assessments and even international assessments where American students are compared to international students, they don't do so hot. So this is just an example of data results from one study, from one assessment that's done over multiple years. That's done over multiple years. And you can see, at least in terms of how people's students score being proficient level or above in science, that level is pretty low of how many students in those grades are proficient. And these assessments not only assess their content knowledge, like what's a rock, but also this process of science knowledge, skills and knowledge. How well do they understand that? This leads a lot. So what we see is a lack of interest in science among students, which is ultimately leading to a lack of STEM professionals in the country, which is becoming more and more of an issue. Lack of interest can be directly related to someone's attitudes towards science. Here on this slide, these are just 4 examples of different indicators or different things you can measure to consider what is somebody's attitudes towards science. This is not comprehensive. It's quite a long list of things you can look at, but I just want to put these here as an example. So from research, we do know that secondary students in particular possess poor attitudes towards science and STEM in general. But we know that if we can increase those positive attitudes towards STEM, it impacts their interest in pursuing careers, enrollment in science and mathematics courses, particularly at the college level, But even participation in STEM activities, and I italicize that because it's very important to remember that not everybody's going to be a scientist or a STEM professional. It's also just as important that we have STEM proponents, science proponents out there in the country supporting science and scientific research. So what can we do? Well, we can do there's two things we can do. This is not inclusive either, but we can allow students, give them opportunities to participate in authentic science experiences, and I'll tell you what that we mean by that. And also giving them time to interact with scientists, the opportunity to have scientist interactions. If we can do at least those two things, and there's other things we can do as well, we can improve attitudes towards STEM science and increase the number of STEM graduates and also STEM professionals in the workforce. So what do we mean by authentic science? Well, basically that just means students participating in authentic science are doing the things that you all do every day in your career as a scientist or as an engineer. That's authentic science. More specifically, if you look at the next generation science standards as a kind of like just it's your baseline, it's what your go-to for what those practices are if you're looking for a definition. It includes some of those. That's not comprehensive either, but that's just some of the things it includes. Asking questions, developing theories, looking at and analyzing data, all that kind of stuff. And when they do participate in authentic science, we know that it improves their perspectives and involvement with science. And it also promotes understanding of the scientific process. It gives them empowerment to do science and helps them to develop an identity as someone who can do science or as a scientist. Interacting with scientists, they're very beneficial, but uncommon. And we also know from research that if they do get to talk with scientists, students are more likely to pursue careers, they understand the scientific process, and they increase their positive attitudes towards science. So really, from that perspective of science interaction, it helps students see that scientists are people. They're not isolated in a lab. They work in groups. They work together all the time to solve problems and to solve questions or answer questions. So the LPI group of CERTI, the Center for Lunar Science and Exploration, we have led this program called XMASS for short, Exploration of the Moon and Asteroids by secondary students, for almost a decade, with an earlier version of it under the NASA Lunar Science Institute. And what we know through pretty rigorous evaluation and even a study looking statistically analyzing some surveys, this program gives high school students a chance to engage in authentic research while stimulating positive attitudes. We're increasing their positive attitudes towards science. Our program in general provides a foundation of lunar and asteroid science. Most high school students don't know much about the moon or asteroids coming in to high school. Provides student teams a research advisor, a practicing scientist, get an emphasis on student-led research. So they're not researching a scientist, helping a scientist gather data for their project. This is what the students want to do, and they're leading it with the guidance of an advisor. It provides the students an opportunity to collaborate and communicate research with peers and scientists. And it gives you all an opportunity to advise and train a future generation of STEM professionals and proponents. Can't stress that enough. Not just the researchers, but the folks out there that come and hear you speak. On the left, there's a map showing you the locations of schools that have participated in our program from the very beginning. The ones that are in pink are the ones that will be participating this fall, starting in the fall. On the right is a location of where advisors and judges, I say judges because at the end of the school year, teams, they present their research as a poster, and those posters are scored. So this is locations of where judges and advisors have been. So as you can see, you don't necessarily have to be near, or judges or advisors aren't necessarily near where schools are. It's great if they are, but with things like Zoom, it's not necessary. Just for fun, I put these three maps there showing locations on the moon where students have examined over the almost past decade. Pretty good spread. So I need advisors for the next year's program. We're gonna start about September. Of course, we'll have to see how school openings shake out. given COVID, but we're hoping that's the goal. We'll get started up again in September of this year. If you'd be interested, thank you. If you'd be interested in learning more, you please email me. You can contact me. We can chat about it, or I can send you some information and give you more. And again, it's okay if you don't live near a team. Like I mentioned, we have a pretty vigorous evaluation. We have them take a pre and post moon and asteroid content survey. We don't call it a test because we don't want to freak them out. The attitude towards science survey, this is a survey that we have used. We've taken the data from the past 4 years, actually. And from that data, we have seen statistically significant increases in students' attitudes towards science as a result of participating in this program. We have given them a process of science survey, which is where they basically just tick off different processes that they've done throughout the program. And then they get a general exit survey to give a chance to tell us what they really thought about it. I mentioned we've done that one study. We published that in Acta Astronautica in 2018. If you're interested in seeing that, I can help you. I can get you that paper. We'll continue to do an analysis of these, the attitudes, looking at this same survey, continue validating the survey and refining it, but also looking to see if we can keep increasing attitudes. And something we want to do now is look at, so we know from the research, as I showed you earlier, that working with scientists will give them positive attitudes and better feelings about science. But what that research did was they put students in a situation where they're working with a scientist, and at the end of that experience, they talked to the students about, did this impact your feelings? Yes, it did. But what we don't know is what is it about that relationship? What is going on in those communications between a scientist and a student that gets them excited and gets them interested and changes their mind, if it's that drastic. So starting this fall, this is something we want to start looking into using our program. So if you are an advisor for me, I shouldn't say for me, for the students, this next upcoming school year, we'll ask you to be part of that. And I know there's some folks out there listening who have been advisors in the past. I will be contacting you to participate in this study as well. So that hopefully by next summer, next forum, we'll have some early data to talk about in that respect. And why can I not go for? Okay, so I just want to leave you here with a couple of quotes. These are pieces of advice that past advisors have offered to people who might potentially want to advise in the future. Things just to kind of help you know what's expected of you as an advisor. And we can talk more about that too, if you want. What's expected as an advisor versus what's expected as the teacher who is working alongside with the students. So with that, I'll take any questions.
Thanks, Andy. If there are any questions in the chat. If not, I have a question. How are the how are the schools that XMS affects chosen? Or do they have to sign up? Are they selected? Are they public schools? Are they magnet schools? Are there any qualifications that are necessary for this kind of program? What can you tell us about that?
Yeah, so that's a good question. So how it works is teachers are encouraged to apply. They apply, and then we ask them to then think about who are the students they would want to bring on to participate in this. And the number of students that participate varies. They could have a core group of just 3 kids. They could have a classroom of kids or an after-school club of kids doing it. But they always have a very core group, a small core group that kind of is in charge of everything and makes sure everything happens. We've had private schools, public schools. We have even in the past had like an after-school group at the California Academy of Science. They have a program there already, but it's mostly biology related. But for a couple of years, they participated in our program and did lunar stuff and did quite well. So it's all over the place, really. As you saw from the map, it's all over the country for the most part. It's very difficult to choose teams. We'll normally get many more applications than we have advisors, which is my number one thing, by the way. That's the toughest part of our program, is finding advisors, because you're all so busy, and we totally understand that. But that's the tough part. So we take 10 a year, but we get close to 30. It's really hard to down select. And we've tried different ways with the application to try to find things we can pull out to use, but it's difficult. One thing we did start doing this year was it was voluntary, but a teacher could ask a student to then fill out a short questionnaire we created. So we could use that to see how does a possible student who might participate, how are they responding to some of these questions? And we can maybe use that as a way to differentiate. Paul, how much time? Yeah, that's a good question, Paul. Thanks, Paul. We asked advisors that, and it ranges, to one extreme where teams never contacted their advisor, obviously to their own detriment. Whereas we'll have teams talking to their advisor every day, every other day, a couple times a week, and that's during the program. But even we had one case, and this was fantastic. We had a paper published out of this program about 7 years ago. And while that's not necessary, it's not required, it happened, but it was because the advisor felt so strongly about that project that the advisor worked with that team beyond the school year to get some more data, get the paper a little more polished for publication, and it happened. So that's on the other extreme. I would say 5 to 10 hours a week is kind of what we hear on average.
Okay, so thank you again, Andy, and it's time to move on to the next talk. Thank you again. The next talk is by Molly Wasser. It's Share Your Fieldwork with NASA Expeditions, a loanable from NASA's social media account. So Molly, whenever you're ready.
Okay, can everyone see or hear me and see my screen?
Yes, everything's perfect.
Okay, so hi, I am Molly Wasser. I am the digital media lead for planetary science at NASA Goddard Space Flight Center. And I'm also the public engagement science activation lead for the GEODS survey node led by Nick Schmer. And I'm here virtually today to talk to you about NASA Expeditions, which is a NASA loanable social media account focused on NASA-funded fieldwork. So originally when I proposed this, I was not anticipating that fieldwork would be so drastically affected by COVID. So have that as a caveat during my talk. And I'll talk a bit about how fieldwork and COVID have been impacted through the end with the NASA Expeditions account. I'd also like to draw attention to my collaborators who helped set up the account, particularly the Goddard Instrument Field team. They've been great. And I have a challenge for all of you during this talk, which is to consider how this social media account could potentially work for you, how you can share your science, your work through this social media account. So what is NASA Expeditions? It is a social media account on Twitter and Facebook. And the account focuses on fieldwork, NASA-funded fieldwork. It features weekly takeovers from teams who are out in the field or have recently been out in the field. And the goal of the account is to share this aspect of NASA that I would say most of the public isn't aware of. If you ask someone, what do you think of when you think of NASA, they'll think of astronauts probably, or spectacular images of space, which we have those are great. But as you all know, NASA does a lot of work here on the ground, and that is really cool as well. So we created these accounts in order to share that aspect of NASA, which may not be as visible to the public. So what does the account do? Well, one, we share science of fieldwork. So on the left here, I have an example of a post from a team who went to Iceland, and they have an image of a volcano in Iceland and then a similar volcanic feature on Mars. So talking about the context of their work, what they're doing, planetary analog studies. In the middle here, I actually, a heliophysics team took over the account and talked about a balloon launch, which for me in planetary science was so cool to see. I wasn't anticipating that heliophysics would be doing a lot of field work, but they do. And then on the right is a post and an image that I took in Hawaii with the Goddard Instrument Field Team of some research being done in a lava tube. So the science that NASA Expeditions shares, we really focus on the scientific process. A lot of communications work focuses on, I would say, the published result. But on social media, I think it's a wonderful way to share the scientific process. What does science look like? And who is doing the science? So a big part of what we share on the account is the people behind the science. And as Andy mentioned in his previous talk, you know, this is a way to meet scientists, you know, see the diversity of people who are doing science, see that it's collaborative, it's done in teams, it's not, you know, one person in a lab coat, alone in a lab, a lone genius coming up with a scientific breakthrough. That's usually not what science looks like. So the NASA Expeditions accounts lets us share some of those stories, and we featured all different kinds of people on them, which to me, I love to do, because just breaking down that stereotype. And of course, fieldwork involves a lot of logistics behind the scenes. I think the logistics is the first time I learned about fieldwork and got to go out in the field with some teams. I was just amazed at how the process of all this works. I thought it was really interesting. So we do share all of that on the account as well. This post on the left, celebration in the forecasting room as Andre appears with snacks, is one of my very favorite posts that has ever been on the account, because you just see the joy and delight of snack time, which I think is just so relatable. Everyone loves snacks. So it shows that NASA scientists too love to eat snacks. And then on the right, there's a little video I made. Let's see if it plays, hopefully. Here we go. Hopefully you can see that. But this is just something I put together in Hawaii to show off some of our safety gear that we use to actually go into lava tubes. So, and again, this is a way to show what data collection involves, and what you actually need, and emphasizing that we're doing, you know, proper safety procedures. And then, of course, social media is social. It's not just about putting out content, it's also about interacting with people. So on the NASA Expeditions accounts, we have done several live events. This is not always possible depending on your field location, but in Hawaii, I interviewed Jake Bleacher on a Facebook Live. And on the right, my colleague Samson Rainey, I'm not sure exactly how he did this, but he did interview some people on a plane during a fire study campaign from Earth Science. And I think what's nice about this is that a lot of times when you're doing fieldwork, you know, you're very isolated, you're very focused on your task. And for when I've been in the field with scientists, they've loved seeing that people outside of their group are interested in what they're doing and really care about it. And it just, I think it provides a little bit of motivation to be like, wow, you know, what we're doing here does have an impact beyond just our team. So why should you post on NASA Expeditions? So our audience is fairly large. So we have 67 1,000 followers on Twitter, 226,000 followers on Facebook. And then because it is a NASA official account, NASA accounts tend to only amplify other NASA accounts. So it's kind of an easy in to the NASA social media universe, which has millions and millions of followers. So the potential reach of this is just huge. It's also really nice to have just kind of one place to tell the story of your field expedition. There's, field expeditions have a lot of different institutions involved, partner institutions. And so I have this post on the left showing all the different teams that were out in the field, and then they could combine their efforts into one social media feed. And then also by participating, you will get support from me and from my colleague, Katie Mersman. And we are both experienced NASA social media leads and familiar with all of the roles. So what is involved in a world in which fieldwork is possible? It's a takeover is 1 week, usually Monday through Friday, a few posts per day on Twitter, 1 to 2 on Facebook. If you have a communications person with you in the field, you can do a live option. And mostly because every post needs to be approved by a NASA communications person who is familiar with the rules and guidelines. And also it does take a fair amount of work, so we don't want to distract you from your scientific duties too much while out in the field. But most of the takeovers have actually been done after the fact. So scientists will provide me with content, images, text, and then I will post it after the fact, kind of pretending we're out in the field for a week. But as I said, COVID has greatly impacted this. So I've really been focusing on one-off posts or a few posts. So sharing updates on data processing, images, anything that's fieldwork adjacent. So if anyone here does have something that they think would be nice to share on the account, I encourage you to email me. And so my final slide is just the contact info. So if you're interested in participating or would like to learn more, please email me, Molly Wasser. I am the general lead for the account and also focus on planetary science. And then Katie Mersman, my colleague, manages all the earth science participation because there is a lot. So with that, I'd like to thank you and see if there are any questions.
Yes, are there any questions? If not, I have a question. What is the engagement like between live posts versus Twitter posts? For example, for like videos that you post on Twitter, you can see views. So would you say there's more engagement for those versus live?
I would say there's actually more engagement on the live posts. So when we do go live, we've seen a lot of participation at the time in the hundreds. And then the non-live posts tend to have a little bit lower than that. It takes them a little bit of time to grow.
Okay. Micah Shabel also has a question. He asks, is there any way to take this concept indoors?
Yes, we are definitely flexible. I'd like to hear more about what you mean by indoors, but I think we can define expedition broadly. So definitely if you like to do something, I'd be curious to hear about it.
Okay, thank you again, Molly. I think it's time to move on to our last talk of the session, which is John Keller, who's talking about forward lunar exploration and beyond the Fisk Full Dome film. So John, whenever you're ready.
Thank you very much. And actually, Tom Ludlow will be sharing his screen for me. But I'm pleased to share with you an exciting planetarium Fold'em show that we're working on at Fisk Planetarium. I'm a planetary scientist at the University of Colorado Boulder, not the John Keller at Goddard, but the John Keller at Fisk. And this is a collaboration looking at lunar exploration and the Artemis mission in collaboration with Jenny Shipway at the Planetarium Consultancy and with 10 Studio, which is up in northern Colorado. So what Forward is, Forward to the Moon, and I'm going to advance my slide now, if I can. And Tom, you may need to advance the slide for me.
The first one.
This is a survey engagement augmentation that the NEST project at University of Colorado Boulder received a year and a half ago. We're putting together a 25-minute Fold'em planetarium show that we'll be distributing worldwide to planetariums. The script was developed by Jenny Shipway in England in collaboration with Fisk and Lockheed Martin. And the animations are being produced right now by 10 Studio, with Tom, who is sharing his screen, being one of the primary artists on this project. We're looking to do location shoots in coordination with NASA centers, although COVID has made that challenging to get onto NASA centers. But as we progress with Artemis, we'll be getting Fold'em footage at Kennedy and at Johnson Space Center. And we are right now securing narration. We've actually received very positive feedback from both Katie Sackhoff from Battlestar Galactica and Carrie Byron from Mythbusters. They both indicated interest in being narrators for this show. And film editing mixing is being done at Fisk. And we are then supporting, this whole project is supported both by the Survey grant augmentation, as well as by additional support from Lockheed Martin. We're in a unique position at Fisk Planetarium in that we have a network of over 300 planetariums worldwide that are already participants in our NASA Explorations Fold'em video series, which are short 3-minute clips around NASA science. And so we'll be distributing both to that network as well as to the overall planetarium network for this free planetarium film show. Next slide, Tom. The script of the show is related. Actually, the purpose of the goal of the project is to really, as Andy was talking about, to generate interest and engagement to then stimulate the next generation of STEM professionals and space explorers. We are focusing on Orion, on the Gateway, and on human landers, which you see there at the bottom of the screen, and how all of those will be leading us towards understanding the Earth, the solar system, and the universe. But our main goal is to, through that story, to really capture engagement and awareness of the public, and then inspire the next generation of STEM professionals through students and the public to know what NASA is doing with the work of Artemis. Next slide. This is a sign that shows the scenes that are in the film. And you can see that we introduced with Jack Schmitt, one of the Apollo 17 lunar landing mission, telling us what the moon used to be like. But we're really emphasizing this is going forward to the moon. And so we spend the next 6 scenes really laying out what current NASA mission plans are for getting to the moon before our Artemis 3 launch sequence. And the last 3 scenes of the show, of the film, are focused on the science that will be coming out of the Artemis mission, followed by plans for how Artemis will help lead us on to Mars exploration. What we want to do is to share with you just some brief clips, a preview of this film. And so we're gonna, unfortunately we can't do this in the planetarium right now due to COVID, but what we'll be sharing with you is preliminary visual cuts that 10 Studio has put together with a circle in a square projection. And so just to get you oriented here, you're now looking at an entire planetarium film, a planetarium dome, where the lower part of the screen is the front of the dome. So you need to imagine you're looking forward. Behind you, or the top of the screen, is the back of the dome. Left is still left and right is still right. And up is straight up. There is a sweet spot in many planetariums, which we've labeled with an X, which is kind of where forward. So you'll see most of the action of these 2 previews we're going to share down in that lower corner right above the front of the dome. And so the first scene we're going to show with you is from scene 6. This scene was generated, is around the mission plans for getting to the moon with the Orion spacecraft and the Gateway. And these are just clay passes, so don't have all the special effects that will be added over the next several months. And we're also adding an actual spacecraft model for Viper now that Astrobotic has been selected to do the landing for that. And so we're going to play this scene for you just for about 3 minutes to give you a sense of what the film is coming together with. And also we have the narration on this track is not the official narrator. It's a narration for timing. So we'll also be working on the sound levels of the film. We'll see how this plays. Tom, we're not hearing that, are we? Okay, so I will talk over this. I will become the official narrator. What we're seeing here is the Orion space capsule heading away from the Earth, and it is this story right now is talking about about space radiation and the issues that space radiation will face as we move forward with the Orion space capsule. And Tom, are you able to play this?
Tom, did you select the audio, computer audio when sharing your screen?
Is that better?
Yeah, it's very faint, Tom. I'll go ahead and just talk over what you're seeing in the shots. So that was a scene that emphasizes space radiation and micrometeorite issues for the Orion capsule. This is the Orion capsule docking with the gateway. And we have a sequence to really emphasize the importance of the gateway for long-term sustained presence on the moon. You can see the Orion coming here to lock with the docking bay of the gateway. We do really emphasize in this film the importance of telerobotic communication and the use of the gateway to do sustained robotic activity on the moon. And we can see here, conversations around both how lunar landers will eventually, we know that Artemis 3 will not go through the gateway initially, but we will be using the gateway eventually for doing rendezvous points and cargo storage pieces and bringing together sustained activity on the moon. Gateway has a unique orbit, which we see here, that allows us to stay in contact with the backside of the moon, while at the same time staying connected to the Earth through radio communications. And so really the importance of the gateway in the sustained presence. This scene ends with a view of a simulated view of what the landing surface of the moon will look like in the future. It is definitely an amalgamation of many different missions together, but basically to give a sense of how this mission will land. And so we'll end this scene in a second as we are going around. And here's the final scene. Again, these are just sample models that we have in place, but we'll be showing and depicting what the landing surface looks like in terms of the gateway and the Orion mission. So Tom, if you want to go ahead and pause there. The second scene that I wanted to share is just talking about some of the science that will be happening in the mission with the Lunar Farside mission. And so this is doing low frequency radio science. If you want to go ahead and press play, Tom. This is a really important emphasis to talk about the value of using the lunar dark side of the outside, the lunar far side, away from the radio shadow of the Earth, to see the dark ages of the radio universe. This is showing the cosmic microwave background, and the script is talking about that right now. But then we also talk about the dark ages after the CMB, but before the first stars had turned on. And the issue, of course, is that the Earth is a very large radio source that is blocking our ability to see that data. And so when we are able to use the Dapper mission and the Farside mission to have a radio silent view of the dark ages of the cosmos, we'll be able to learn significantly more about that unknown period, right, between the CMB and the first galaxy being stars. And so that is, we're going to stop there because I wanted to share with you briefly kind of what the plans for this project are. In terms of filming, we are going to be doing a release of this film in October. That'll be a virtual release given COVID issues. And then in summer of 2021 is when we'll finish the full-length promotion or premiere of the show with the 2022 update once we have more film footage from the Artemis mission. And we are going to be then providing full dome masters to planetariums around the world. And we're also experimenting and planning to develop a virtual planetarium environment where people will be able to show the show with audio once we have, we'll be able to show this during the COVID times when many planetariums right now are closed. That will not last forever, but we do want to be able to have people engage with this during that time. And so the final slide is just my contact information of how to reach me if you would like to promote this in your area or provide any feedback. And again, this work is run by both by NESS and by Lockheed Martin are the main supporters through the SERPI project. Thanks.
Thank you, John. Okay, anybody have any questions for John? Just looking. Well, I got one for you, John. So when this is out and once we're all able to, leave our homes again, what are some ways that survey scientists or anybody, scientists in general, could use this?
Mm-hmm. Yeah, so we'll be using this again. This will be available in planetariums around the country. And so one easy way for that to happen would be for local scientists to identify if there is a planetarium in their space where they are working and to coordinate with that planetarium facility to do a live presentation. We do a lot of those at Fisk where this is a 25-minute show, so it easily allows for a full half-hour presentation by a lunar scientist to then preview or start talking about the context of lunar exploration to then give a live talk at a local planetarium. Actually, that would be beneficial to us in the sense of like having a scientist come to a planetarium to say, here's a free show, why don't you show it? And then we can do that live talk would be a very useful way to promote and build upon this work.
Great. Hey, anybody else in the chat box or you raise your hand, call on you? Okay, great. So, okay, I guess it's time to go, or time to wrap up our session. So thank you all again for attending. We appreciate you being here. Christina, what do we do next?
What do we do next? I just pop in at the end of all the sessions. We continue with plenary session 6, water and ice, at 10:35. We're going to keep to the schedule. So that's about a 20-minute break. So we will see you all back then. Thank you. Thank you, Andy. Thank you, Aisha.
Thank you all.
Hey, John, if you're still there, Molly, I had a question for you in the chat.
Oh, yeah, sorry.
Okay, Molly.
No worries.
I didn't get to it in time.
Yeah, I was just getting ready to actually respond to that. But yeah, so the movie topics were decided we only had 25 minutes. And so we went through several iterations around both wanting to tell the story of humans and robots working together. That was part of the original proposal. And then also, like, we can't do all of the lunar science, but we are focusing on lunar geology and radio farside work that you saw in those previews.
Cool, thanks. Yeah, I was wondering if you gather user data of what people are interested in, or
it's been driven largely by the science teams, but we are definitely focusing on as a director perspective, I'm really focused on providing the human perspective. As we were talking about earlier, the importance of sharing humans doing the work and telling the narrative of the human exploration, of the human research endeavor is definitely a focus and theme of the show.
Cool, thanks. That was really beautiful to see. I wish we could see it full dome one day.
Yes, one day it'll come to a planetarium near you, hopefully before 2024.
Yes. Okay. Well, yeah, thank you. And thanks, Andy, if you're still on.
Yes, thank you, Molly.
Okay.
Hi, Carl. How are you? This is Christina.
Hey, Christina. How are you doing? Need to get this started.
Good. You just, yeah, you guys are next. You all set? We're going to stick to 10:35 in case you weren't at the end of the last session.
I was.
Okay,
And I think Ariel is going to lead off this session with the rules and everything,
Yeah.
which is great. And
Yeah.
I'll simply sit back and look at the chat window and whatnot. I'll take the last 6 talks.
Okay. Hi, Ariel. I see you now too. Thank you both. So maybe what we'll do.
I don't hear Ariel. She was speaking, but I didn't hear it.
Oh.
Sorry, I was muted.
Okay, there we go. We'll do like we've been doing. Greg or I'll jump in kind of after the last talk has a question or so. We'll kind of set the time for the start of the next session, and then you guys can finish off some discussion with any trailing questions once we just set the new time. So anybody who wants to just go have a break can, and anyone who wants to continue discussing can.
Sounds great.
Okay. Thanks, you guys.
So Ariel, I'll keep time too, just in case one of us forgets.
Perfect.
Yep, maybe you could do the same when I'm running the last 6.
Definitely.
Okay.
Just wanted to say a quick hi, Carl and Ariel.
Hi, Greg.
Hi.
Hey. Meeting's going very well. I've enjoyed it.
Oh, great. Thank you. Appreciate it.
Okay, our first talk is scheduled to start in just a moment, so maybe I'll start now introducing our section. So welcome everyone to the 6th plenary session. It's all about water and ice. I'm Ariel Deutsch, and I'm co-chairing this session with Carl Hibbets. And we have a really excellent lineup of 12 talks in the session. But before we get started, we just wanted to remind some people about the rules. All the speakers have 12-minute slots. So these are designed for 10-minute talks and 2 minutes of questions. And Carl and I will give all the speakers warnings at the 8-minute mark and then again at the 10-minute mark. And if you can, speakers, it'd be great if you could stay tuned after the following, at the last talk for a discussion section where we'll have more time for questions. And so if you're in the audience today, you can ask questions either by using the hand raise function on Zoom, and then Carl and I can call on you and you can unmute and ask your question. Or alternatively, you can also type in a question into the chat box and we'll go ahead and ask it for you. So yeah, it's almost time. Casey, if you want to start sharing your screen and unmuting and turning on your video. But I'm thrilled to introduce our first speaker, which is Casey Honeyball. And Casey's talk is entitled Molecular Water on the Sunlit Lunar Surface, Detection of the 6 Micron HOH Fundamental with the SOFIA Airborne Observatory. So go ahead, Casey.
Can you see my screen and hear me?
Yes, we can.
All right, perfect. So we are at 1:35, so I'll go ahead and get started. So as Ariel said, I'm Casey Honeyball, and I'm going to be presenting the first ever detection of molecular water on the moon using 6 microns and the SOFIA Airborne Observatory. So I'm going to start with some background. For many decades, the moon was thought to be dry, but beginning in 2008, evidence of lunar hydration began to emerge. And Sal et al. 2008 measured high water contents from pyroclastic deposits returned by Apollo. Then in 2009, 3 spacecraft measured a 3 micron absorption feature, which is attributed to hydroxyl and possibly molecular water. And then most recently, UV observations show a diurnal signal in the water ice band ratio, possibly indicating molecular water on the moon. Now, while these observations show that the moon is not dry, the 3 micron and UV observations have not been able to distinguish between hydroxyl and molecular water. And that's because of the ambiguity in the 3 micron band and lack of laboratory studies. So the 3 micron band is created by the symmetric and asymmetric stretch of the OH bond, and both hydroxyl and molecular water exhibit this 3 micron band. This plot here shows the different forms of molecular water and hydroxide ions can mimic the shape of molecular water. And so currently the band shape and center of hydroxyl attached to different metal cations cannot be predicted, and separating water from hydroxyl is difficult at 3 microns. In the UV, the water ice band ratio has been used to detect ice deposits at permanently shadowed regions. But on the sunlit moon, it is unknown what causes these water ice band ratios to vary diurnally. Hendricks et al. 2019 assumes that adsorbed water spectrally behaves like water ice in the UV, but there's no lab data to confirm this, and hydroxyl cannot be ruled out just yet. Therefore, there has been no definitive detection of molecular water on the sunlit moon. So new methods are needed for its detection, and fortunately, molecular water shows a fundamental vibration frequency at 6 microns, which is explicitly due to molecular water without contamination from hydroxyl. The 6 micron band is strong and narrow and well suited for the detection. And if you can see my mouse, it is shown right here in this spectrum. So while this method is new to remote sensing, it is not new for the detection of water in geologic thin section samples and has been used since 1962. It has even been pointed out in the literature that observations of the moon at 6 microns could prove the existence of water. The 6 micron band has, however, been observed in remote measurements of samples and planetary bodies. Apollo samples returned measured at RELAB, and meteorite samples measured at APL exhibit both a 3 and 6 micron band shown here in A and B. And from spacecraft, a 6 micron band has even been observed on Mars, shown here in C, and on asteroids, shown here in D. What's interesting is that the 6 micron feature on Mars has even been mapped, as shown in this image on the bottom. These examples show that if molecular water is present on the moon, it should exhibit a 6 micron band. But currently, there are no spacecraft capable of making 6 micron observations of the lunar surface, and from ground-based telescopes, the atmosphere is completely opaque. This plot shows the atmospheric transmission from Mauna Kea Observatory here in blue, and as we can see at 6 microns, there is no signal available to measure. However, the higher the observatory, the more the atmosphere opens up. And this allows us to use the Stratospheric Observatory for Infrared Astronomy, SOFIA, to look at the moon at 6 microns. SOFIA flies at an altitude of about 14 kilometers, which is 99.9% above atmospheric water vapor, opening up the 6 micron region as shown by the green line up here. Using the forecast instrument on SOFIA that operates from 5 to 8 microns, we have made the first observations of the moon at 6 microns looking for molecular water. Our first flight on SOFIA was on August 30th, 2018, and we collected 12 frames of data with 248 spectra each. We observed 2 different locations, a Mare reference location shown here by these white lines, which indicate the slit location of the forecast instrument, and we also observed the Clavius crater region down at the high southern latitudes, shown down here. So results from these observations are shown in this plot, and these spectra are from each of the Clavius region observations, showing the maximum and minimum spectra that reported abundance, molecular water abundances. And so you can see that there is a strong and prominent 6 micron emission band in each of these frames of data that we collected at Clavius. These bands are about 2% in strength, and we attribute them to molecular water. And this is the first unambiguous detection of molecular water on the sunlit moon. Now, just to prove that this band that we're observing on the moon is due to molecular water, we compared our lunar 6 micron band properties to other observations and to literature values of the HOH band centers. So this histogram here shows the distribution of literature band centers from Falk 1984 in red, and overlaid we put the lunar band centers in blue. And we can see that the lunar 6 micron band centers all fall within the range of the cited band centers from Falk 1984. Now, if we take a look at this bottom plot, we see that we compare the moon lunar spectrum to meteorite spectra and to water-bearing glasses. And when we look at the lunar spectrum in red and compare it to meteorite spectrum in black, we see that they are similar in shape, center, and width. But when we look at and compare the moon to the water-bearing glasses, we see that it is broader and shifted to lower wavelengths. These results, however, indicate that we are actually detecting molecular water on the moon at 6 microns. So next, we estimated the abundance of water present. And so to do this, we used the strength of the 6 micron band, which correlates to absolute water content, which is commonly used to measure water in thin sections. We are using the strength of the band to estimate water abundances in remote sensing data, which has not yet been done. So we use the water-bearing glasses with known abundances of water that feature both a 3 and 6 micron emission band or absorption band to derive an empirical relationship between band depth and abundance of water. The empirical relationship is shown on the bottom plot. So we estimate that about 100 to 400 ppm of water is present in the Clavius crater region with a mean of 250 ppm. This histogram here shows the abundance of water for each spectrum in the Clavius region, and the plot next to it is showing the abundance of water as a function of latitude measured by SOFIA in black, and also the total water abundance measured at 3 microns by the Moon Mineralogy Mapper in red. And when I say total water, I mean the sum of hydroxyl plus molecular water at 3 microns. So the abundances we measure with SOFIA all fall within 1 sigma of the measured M cube abundances. And the latitude trend we observe with SOFIA is due to the location that we observed, with some of our observations passing through Tycho crater ejecta. So the lower latitude, thank you. The lower latitude observations were in Tycho ejecta, while the higher latitude observations were not. So this latitude trend is probably localized and likely not a global phenomenon. Lastly, we wanted to infer where the water might be stored on the lunar surface. So there are a few places it can be, but I'm only going to focus on 2. And the 2 are chemisorbed on grain surfaces or sequestered into impact glasses. At the latitude and temperature of our 6 micron observations, models suggest that only 3 ppm of water can be chemisorbed on the grains. So this implies that the water we are observing with SOFIA is actually not on the surface of the grains, but stored within the grains, the impact grains themselves. And we estimate that 300 to 1300 ppm of water is confined within impact glasses. These results are consistent with water being produced from pre-existing hydroxyl during micrometeorite impact. So in conclusion, we have made the first direct detection of molecular water on the sunlit moon using SOFIA forecast 6 micron measurements. We estimate abundances in the range of hundreds, and we find that most of the water is likely stored within impact glasses. And the trend we observe with latitude is a local phenomenon and not a global phenomenon. So in the future, we plan to continue this work by continuing observations of the moon with SOFIA with over 20 hours of observing time coming up. And we plan to map water on the moon and compare our 6 micron compare 6 microns and 3 microns to each other, looking at the differences in diurnal variations. We will also be investigating the presence of molecular water at pyroclastic deposits to provide better estimates of hydroxyl versus molecular water, and which provides better constraints on and to inform us about future missions to the moon regarding potential resources. And that concludes my talk. Thank you.
Thank you, Casey. That's really exciting work. So reminder if,
Sure. Yeah, I just thought that was really fascinating. I just had a quick question. If you could explain how or why you focused on the Clavius region, and if you know where you'll be able to map on your upcoming SOFIA flights.
Because these observations had never been done before. Clavius was very obvious, and it was at high southern latitudes, which meant we had a higher chance of detecting molecular water than we did at lower latitudes.
Okay, and I think we have time for one more quick question. Okay.
Try to unmute myself. Wait, can you hear me?
There we go.
Sorry, that was difficult. Yes, I'm just very interesting observations, and the separating OH from H2O is crucial. So when you're talking about water associated with pyroclastics, what's the nature of that water?
Be able to tell the difference between adsorbed and bound, but we believe that the pyroclastic water would be from internal water from the moon when it was like erupted during a volcanic event. So
thanks so much, Casey. I'm going to go ahead and introduce our next speaker, which is David Kring, whose talk is entitled Potential Water and Dry Ice Distribution in the Lunar South Polar Region. Maybe try one more time now that Casey's stopped sharing.
Okay. It's because I have
it is
too many screens. Yeah, give me a second. I just lost my... Okay, do you see the screen now?
We do, but we're in presenter mode if you want to swap displays.
Sorry about that. Okay, so this is a paper with Matt Siegler and David Page, and we've been trying to explore the notion of where volatiles might be deposited and the chemical nature of those volatiles, because that will affect both the locations to meet science objectives and the strategies for ISRU. And so we've done a series of calculations to address that issue. We began, and to be more precise, Matt and David began by using their existing model. The community is familiar with it. It's been outlined for as late as Ziegler et al. In Nature 2016. And this model calculates the thermal stability of different types of ices. Here is a calculated result for the stability of water ice within the upper 1 meter of regolith in the South Polar region. Shackleton crater is in the center. You can see Hawa, Shoemaker, and Faustini nearby, so that should be a familiar terrain. The scale bar ranges from white at the surface to red at a depth of about 1 meter. Where the color is gray, water ice would not be thermally stable in those regions in that 1 meter zone. The same method was done to calculate the thermal stability of dry ice, CO2, in that same region. And this requires colder temperatures, and so the distribution of dry ice is not as extensive as that of water ice. But it does still occur or would be stable within the upper meter in a substantial area or geographic region around the South Pole. This is a side-by-side comparison of those two results. The dry ice is only occurring in the coldest portions of permanently shadowed regions, or PSRs, so its distribution in the right panel is, again, less than that of the water ice as you see in the left panel. I've tried to show that comparison a little bit more explicitly here by doing a transparent overlay of those two maps. And I've labeled some of the geographic points, Shackleton and Cabeus, for orientation. And actually, let me focus your attention on Cabeus because the community is familiar with that. The result suggests that if you were to land in the South Pole region and approach the Cabeus PSR, one is likely to encounter nearly pure water ice in the outer margins, the warmer portions of that PSR, and not actually reach dry ice until one reached the coldest portion of that PSR. Now, for an ISRU purpose, that's a fascinating result because it's actually easier to process pure water ice than more complicated water ices. And so hovering in the warmer outer portions of that PSR will be attractive. On the other hand, if you actually do want to address all of the scientific objectives in, for example, Concept 4 of the NRC 2007 document, you will at some point in time need to penetrate deeply into the PSR to that coldest dry ice portion. Here's two close-ups to give you a better perspective of these results. In the upper two panels is a close-up of Der Garlock and Shackleton region. And in the lower two panels, you see Amundsen. And the two panels side by side, left and right, represent again the distribution of water ice and dry ice. You can see in Shackleton, for example, that water ice may be stable within the upper meter, but dry ice is not anticipated to be stable in the upper 1 meter. Now, I'm a geologist, and so I always like to think in terms of the geologic reality, just not a plan view of what is entailed. And so here's a little notional model of that distribution of water ice in the floor of Shackleton crater. On the right side of the diagram, you see the simple crater form of Shackleton. On the far left is a simple column that cross-cuts through the breccia lens in the center. And one can imagine, per the calculations, that there is water ice in the post-impact regolith that accumulated on the crater floor. It's also, if you step over a couple of columns, it's also possible that that ice diffused downward into the breccia lens, but we're really only interested, at least at this point in time, in what occurs in that uppermost meter of the regolith, because that is the most easily recoverable ISRU target, because you can excavate or recover that water ice without removing significant overburden, which would be an energy-intensive cost. Now, based on that data, I've calculated the resource potential of water ice and other ices throughout the region that you've seen in the previous maps. And I highlight, first of all, this blue zone in this plot of log volume of regolith with ice against log mass of water ice. And that blue zone represents the amount of ice one would anticipate, assuming the Cabeus concentrations of water ice in the coldest portions of Cabeus that was excavated by the L-Cross impactor. Just to put these numbers in different terms, that log mass number of 9 kilograms is 1 million metric tons of water ice. And you can see that there would be less water ice in Shackleton than in Faustini, than in Shoemaker, than in Hallworth, and Cabeus is going to contain the largest mass of water ice in that upper 1 meter of material. This is a similar calculation for dry ice with the green line and other icy constituents that were detected by the L-cross impactor experiment into Cabeus. Again, these constituents are going to be affiliated with regions with dry ice, that is in the coldest portions of the PSRs, and not necessarily in the water-rich regions that you've seen in the previous maps. Okay, I want to step backwards one slide and point out that we don't assume Cabeus abundances of water ice or these ices everywhere. The calculations that we did also consider lower abundances of water ice. Seen here is lines 1 weight percent, half a weight percent, and 0.1 weight percent water. So depending on the assumptions that you feel comfortable with, you can deduce a resource potential for those regions, which should be useful in guiding ISRU prospects. Okay, in conclusion, model calculations suggest 2 times 10 to the 10 to 5 times 10 to the 10 kilograms of water ice could potentially be recovered from the uppermost 1 meter of Cabeus crater regolith. Water ice resource potential values for other sites are, and I won't read all of those numbers, but they're comparable, albeit a little bit less than what you might find in Cabeus. Additional tonnage can be recovered at deeper, that is greater than 1 meter horizons. And depending on the method that you utilize for resource recovery, it may be more efficient to access those deeper horizons at a single location than to collect surface ice at geographically distant sites, but that's a trade that the ISRU community needs to make. Thank you.
Thank you, David. This is a perfect talk after all of the ISRU buzz this week. So we have, again, some interest in the chat. If you have questions, go ahead and raise your hand, but we can start with one of the chat questions, which is, have you looked into the stability of CO ice, although maybe this isn't early, and can you compare it with CO2?
You know, we did these calculations back in December and January, and I can't actually recall if I had CO on that last chart or not. If it's not on that last chart, the answer is no. And I apologize for the fuzzy memory, but all of these calculations and all this data is on an office computer and not at home.
And then another question from the chat is, did you use a single value of CO2 ice density?
Yes, and that answer is yes. And I can't rattle off the number that we use, but yes.
Great. Okay, we have a couple
and
more.
I should add that we don't expect there to be, really expect there to be a different density in the 1 meter depth that we were working at.
Thanks, David. We have a couple more questions in the chat you can look at, but I'll go ahead and introduce the next speaker, which is Paul Lucy, whose talk is entitled Relative Magnitudes of Water Sources to the Lunar Poles.
And how about the sound check, Ariel?
Sound check sounds excellent. And we're seeing your screen. Great, all set.
Okay. Terrific. All right, so we've been hearing a ton about water today, water ice. I'm going to talk about where it comes from and how we might detect it. Got to say, it's a treat to follow Dave because he and his work and their co-workers' work is a big player in what I'm going to talk about today. So there are a zoo of sources into the lunar poles. This particular slide I've been showing so long ago. We showed it in Gilruth Gym at LPSC when we used to use cave paintings to depict our lunar science. But these sources kind of have two types. There are sort of boutique sources here. The solar system goes through giant molecular clouds occasionally. We pick up some volatiles there. we get some volatiles from the Earth, but the big dogs in the sources of volatiles in the poles are impacts of comets, asteroids, and dust, the sun, and then principally through Dave's work, recognizing that the moon itself is a major supplier of volatiles to the poles. So let's talk about solar wind first. A lot of this comes from Dana Hurley's work. Over time, the solar wind is relatively constant. We've got about 30 grams of protons per second into the entire lunar surface. And if you go over a billion years, that's 10 to the 18th grams. If we assume 1 part per thousand is converted to mobile molecular water, and then another tenth of that makes it to the poles, the total mass of water is 10 to the 14 grams, and getting to equivalent ice thicknesses, that's 30 centimeters of ice in a billion years and about a meter since Orientali. This is Dave and Deborah Needham's contribution, recognizing that volcanism is a big contributor to the potential supply to the poles. The volcanic flux strongly peaked in the Imbrium, but there's a non-trivial mass later in the Ratticinian. So the total mass of water since Orientali is 10 to the 16th grams with a polar ice thickness of about 30 meters. So a pretty reasonable supply of ice to the poles. But the 500-pound gorilla among the 3 big dogs is impact. Impact has the biggest potential for contributing volatiles to the poles. We looked at this in a number of ways. It's in the abstract. But in the last billion years, that's about 20 meters of equivalent ice thickness into the polar regions. That's based on both impact fluxes and counting the large Copernican craters. Then if we step back to the Ratticinian, the impact flux was about 5 times higher. The duration is about a factor of 2 longer. And that gives us this really major ice thickness of about 200 meters. We step back to the late Imbrium. I'm only talking about the post-Orientali era. This has 100 times the total flux from the Copernicus, and that corresponds to a potential supply of 2,000 meters of water ice in the permanently shadowed regions. So if we sort of sum up this like a scoreboard, so we have 3 periods and we have three teams, kind of peculiar game here. So in the Imbrian period, the potential supply of impactors is, again, 2,000 meters. It declines exponentially down to 200 in the Ratticinian, 20 in the Copernican. If we just talk about single-digit precision, we have, again, a final abundance of about 2,000 meters. The solar wind is a really pretty minor player in this. There's single-digit contributions of meters to the poles, with a final contribution of on the order of 4 meters. And volcanism is in between, a pretty reasonable contribution in the Imbrian, 3 meters in the Ratticinian, and then they didn't get any runs in the Copernican, but a total ice thickness of about 30 meters. So we should talk about losses. That picture on the right, that was a tough one. There was one more inning to go and it didn't go well. We have more questions than we have answers in terms of losses. We don't really understand very well how well water ice and other volatiles are actually retained promptly after the impact, whether a lot of the volatiles may be lost immediately to space. A lot of questions in terms of losses in transport. We probably have a pretty good feel for exospheric losses, but the surface interactions of actually propagating water molecules from its source point to the poles has a lot of questions. It's possible that a water molecule in its first encounter with the surface may destructively dissociate, and so the polar regions may only be fed by a narrow region at high latitudes. There's a huge question mark about transient atmospheres that have been studied from impact by Dave Stevens, Parvati Prem, others, and also proposed by Dave and Deborah Needham. This is a whole new ball game on transport. Finally, we have very strong losses right at the immediate surface from micrometeorites and sputtering erosions. This basically wipes out solar wind as a contributor. And finally, regolith overturn is often described as a sequestration process, but it's pretty ferocious at the sort of centimeter scale and may actually be a net loss, at least for these superficial sources. So just to talk about current events a little bit. So Ariel Deutsch and the Space Cowboys had a poster earlier this week, and they showed that only pre-Copernican craters exhibit ice detections based on the M-cube results. And this is consistent with loss outstripping supply in the Copernican and may force us to dial down that impact source. But the timing of the ice emplacement isn't really strongly constrained by that. The onset of the permanent shadow could be as late as the late Eratosthenian, and we still get a significant supply. Last year, Lior Rubinenko showed that polar craters on the Moon and Mercury show anomalously shallow depth-diameter ratios, which also correlate with surface ice exposures. These may show that there's a sequestration of ice that's outside the reach of the neutron spectrometers. So here's some terrible tables that address the signatures of volcanism and comet impact. We have some comet analyses by Zhang and Page, the lunar volcanism, volatiles from Needham and Kring, and Tony Colapride's L-Cross results. But if we condense this down to a simple table and we talk about just the elements, the elemental abundances and not the compounds, there's a very significant difference between the volcanic input and the cometary input. So there's thank you. There's almost an inverse signature here where the cometary input has sort of a high carbon, hydrogen, and then kind of dribbles off with intermediate nitrogen and almost negligible sulfur. Whereas we have sort of a Nike swoosh in the volcanic signature, negligible nitrogen, but really high sulfur. So it looks like nitrogen and sulfur could be key discriminators between these two sources. And if we throw in L-Cross here, again, breaking the compounds down into the elemental masses, the L-Cross results kind of have that Nike swoosh-like signature where we have a very high sulfur abundance, but again, a non-negligible nitrogen abundance. So this may show evidence of the presence of both a cometary and a volcanic source. So the takeaways here is that impact is the dominant source. Volcanism is not unimportant, could be looks like 100 times lower if we assume the current retention rates, which might be way off. Looks like solar wind is not a significant long-term source. The micrometeorite and sputtering loss is too high. Sulfur and nitrogen could be key indicators of the presence of volcanism and impact, and L-Cross showed significant quantities of both those elements. The overall water supply appears to be several order of magnitude too high, embarrassment of riches. Is the retention of water and impact overestimated, or are these other losses underestimated? Maybe the cold traps are younger than we think from the polar wander hypothesis of Matt Siegler, or maybe as Lior has pointed out, maybe the ice is just staring us in the face. I think the upcoming missions are going to make huge contributions to this. A lot of sulfur and nitrogen compounds will be detectable by Trailblazer and also by the Viper mission and other upcoming missions. So thank you very much.
Thank you so much, Paul. All right, we have a first question from Bethany Ellman. Curious about what sulfur and nitrogen compounds would we expect in the form of the elements. She's thinking about Lunar Trailblazer, which is from 0.6 to 3.6 microns. What could they detect that might help constrain some of these ideas?
Yeah, thanks. Thanks for the question, Bethany. So the three major compounds are sulfur, elemental sulfur, H2S, and SO2. We probably would expect elemental sulfur and H2S, but there's enough chemistry going on the surface that we can't rule out oxidized sulfur. Their major action for the SO2 and H2S is in the 4 micron region, but there are weak features in the region of Trailblazer that you can latch onto. Sulfur, we're actually doing a search using WAC data right now to see if we can see a sulfur signature in the illuminated portion of the poles. Sulfur has a pretty high volatilization temperature, and so it should be stable on low temperature, but still illuminated lunar surfaces.
And nitrogen ice or ammonia?
Nitrogen, there are some weak features in the 2 micron region that are very distinct. So you've got a shot there for sure.
Thanks, Paul.
Not nitrogen ice, I meant ammonia.
Okay. We have some more questions for you in the chat, or stick around for the break period, but I'm going to go ahead and move along to stay on time. So our next speaker is Jason McLean, who's talking about solar wind proton induced hydroxylation on lunar soil 78421.
Hello, everyone. Hopefully you can hear me.
Sounds good.
I don't have a camera, so we'll just, but I'm here. And yeah, this study really started, we wanted to understand the rate of this process. So, you know, the solar wind, of course, is mainly protons, and it comes and impacts the lunar soil. And that process then creates hydroxyls, and this paper's in revisions, and I really wanted to thank Casey for helping us interpret some of these IR spectra. So I just wanted to jump on in here. So, you know, we had a few null results at first, and this is due to this process of de and rehydroxylation. And Zurlov's model in 2000, which we verified with this study, really made us get a handle on this experiment. And I can just take you through this. I mean, this is fairly simple dehydroxylation model. And so in stage one, when you have like a silica or silicate in vacuum, you just, you know, you remove the multi-layers of water, and that's done at room temperature. And then as you start increasing the temperature, you really start to remove all of those water molecules. And at this point, it's interesting because dissociative absorption is barrierless. So the activation energy is zero. So if a water molecule actually comes back down at this time, it'll dissociate and rehydroxylate the surface. And as you continue up in temperature, things change quite a lot. You start making these bridge bonded oxygens and such. And at about 670 Kelvin, now that same process of rehydroxylation with molecular water becomes an activated process. So it requires energy to split the water on the surface, or actually it's not the water, but it's these bonds here that are really strong. If you take that one step further, then what you'll see here is that now it's the surface becomes hydrophobic. So the process is hardly reversible. It's so strongly activated that I took a sample of this silica, which we heated to this, and boiled it in water, and I could not get any IR signature of OH. So at sort of first glance here, we see that we're never going to see protons hydroxylate unless we remove most of the ones that are there. And another thing that was important here was we were not able to do this all in situ. So we had to remove the samples and put them in the spectrometer. So being able to do that without the contamination of the terrestrial water was really important. So here, this critical heating step, we were able to remove most of the water, and then we had time to move the sample around without worrying about terrestrial water rehydroxylating the sample. We put the samples in a ultra high vacuum chamber, and our first results actually came with this fused silica. That was just by happenstance. I chose that. I figured it would be the easiest to check. We used olivine at first and other analogs before we went on to the lunar sample. And so here you can see the silica being irradiated with 2 keV protons, or I'm sorry, H2 plus. And I wanted to mention just real quick about, so H2 plus, I mean, we know that's not in the solar wind, and but as many of you might know, for an electron impact ion gun or even a plasma source, you can use a VIN filter, a E cross B filter to filter out the H2 plus where you get H plus, and we can do that. But the issue is that the H2 plus flux is just orders of magnitude below. I mean, the H plus flux is orders of magnitude below H2 plus. And so, there's been question of whether or not the H2 plus reacts differently, but there's a body of evidence in the literature, and even we have of evidence of this with neutral atoms that show, especially Weiser in 2002, ion scattering studies where incident H2 plus, it completely dissociates on a surface. And one interesting thing about this is that, the resulting momentum transfer is essentially a beam of 2 solar wind sort of type protons. And mainly the charge fraction is neutral hydrogen, and about 20% is converted to H plus and H minus. Another interesting thing that you'll find is that this process doesn't even really depend on the initial charge fraction of the ion. So you can have H plus or H minus or H neutrals, and you still get this transfer of about 80% neutrals. So we take the sample then and we put it into a drifts setup inside the spectrometer, and we've actually got a way to heat this sample up as well. So I'll present some of that. So the first results show really nicely. We get this really nice check mark feature, really sharp OH feature on the fused silica. You can see here, I measured the back of the sample, so there's no radiation here. The sample's on the order of a couple millimeters thick, and then as we continue, we can see this start to grow in this really nice OH feature. So now we look at the Apollo sample, and we get quite a different result. And so this is very similar to what Ichimura saw. And for a while there, I was skeptical, but you definitely see that there's a large difference between the Apollo sample band at 2.7 and then at here it's broad going all the way to almost 3.8 microns. For those of you that are familiar with these spectra, you know that this is also where the absorbed water band is. So you know, we were kind of struck like, well, what's going on here? And you know, they simply said, well, you know, this is due to this inhomogeneous broadening. And
8-minute mark.
Okay, thank you. And that is very interesting. And so we decided to compare with their results. And then here are our results. There's a follow-up spectra taken of the same sample. And you can see here that the overall feature from 3 different samples, hyaline calcium plagioclase, and then a high iron magnesium pyroxene, and then our sample, are all very similar, which was really really interesting. And maybe we can understand that if you know, with the fact that most of the surface of the minerals on the surface of the moon are silicates, and so you have this silicon tetrahedron backbone where you're forming these, and you're forming them, and they're really being broadened by just being thrown into this very strange mix of defective material. You know, one of the things we were curious is, well, how much water is being absorbed on there during or after the transfer. And we can see here that there's really not much of a 6 micron band to be observed. So we believe that this is all OH, just broadened OH on the real lunar materials. So we did a temperature excursion and found that if you heat it up in the spectrometer and then let it cool back down to 25 Celsius, you do get a decrease in the band area, about a 20% decrease. So we did remove some, however, the band shifted. So we have plans to do this all in vacuum now and really try to understand the equilibrium concentrations. And for the few silica, I have them here in the summary, and for the 7842, which is about every million hydrogens produce an OH. Thank you.
Thank you so much, Jason. I'm going to go ahead and direct you to the chat box and ask that you stay tuned at the end of the section. But we're going to go ahead and move on to the next speaker, which is Yu Huang, who's speaking about molecular dynamics simulations of water and hydrogen formation on the lunar surface.
Thank you. Can you hear me?
Yes, we can hear you.
All right.
And we can see you.
Okay, how about the slide?
Perfect.
Okay, thank you. Okay, good morning. I'm Ziyu Huang. I'm a second-year PhD student at University of Southern California, and I work with Professor Joseph Wang. And this work is also collaborative with Professor Nomura and Professor Natano from USC. And today I'll be talking about molecular dynamic simulations of water and hydrogen formation on lunar surface as induced by deep dielectric charging. Okay, so first I would like to give a brief introduction about water hydroxyl and hydrogen observations. Several observations has been made to map water distribution on polar region, and they have already detected water concentration in craters and craters in polar region and also permanently shadowed regions. And land from ARO also detected rich hydrogen in those areas. But one of the reasons is very obvious, which is temperature. So PSR has temperature lower than 40 Kelvin, which can keep the water in ice or frost. So however, the source of water molecules are still under debate. So here are some theories and experiments to model the formation of water molecules. The mechanism of solar wind interactions is the implanted protons combine with oxygen to produce hydroxyl, and then the diffusion of hydrogen can combine with other hydrogen to form H2 and then being released. And the hydroxide inside the regulus can also trigger recombinative disruption, as the picture shown on the right, which is from John's paper. And however, to get recombinative disruption, it requires enough energy, like a high temperature. And protons implantation alone is not enough to generate water and liberate water. So Drew et al. Did an experiment to model micrometeorite impacts. The heat released by micrometeorite impact would be enough to generate water, but scientists think like how about some other sources which occurs more globally and not limited to just one location. Then I started to think again the contribution of solar wind plasma. And one of the interesting thing I found is when I was reading Jordan's paper about the dielectric breakdown. The figure on the right is the probability of deep dielectric breakdown, and on the left is the estimated electric field induced by deep dielectric charging. The electric field is in the level of 10 to the 6 voltage per meter, which might be able to cause some water formation reactions, just like micrometeorite impact. And also the rate concentrated at permanent shadow regions as a function of time. And by the way, it's reasonable to estimate the electric field to be several times stronger due to the irregular shape of regulus and some more extreme solar energetic particles events. So I decided to use molecular dynamics simulation to test this hypothesis. We tested the silica nanoparticles with hydrogen surrounded. So something about our model, we use RxMD to do the simulation. RxMD is developed and actually still being developed by one of our co-authors, Dr. Namora. The code includes a React FF force field and polarizable charge equilibration model to better solve the effects of electric field and also chemical reactions. We use silica as silica O2 to represent dust particles. Actually, we wanted to use some other lunar simulant like olivine, but it's really hard to find like the force field since iron is so reactive. The electric field is chosen as 5 times 10 to the 6 voltage per meter, which can be found in Jordan's paper. So first we tested 2 cases, both with the same setup, and one of them is completely without electric field, and we call it simulation 1, and the other one is the case with an electric field, which is simulation 2A. And then we plotted the time history of number of water molecules as silica O4 tetrahedral and also hydroxy group. Case 2A had a significant amount of water generated, and the silica was melted down, as we can see from the number of silica. For hydroxy groups, case 1 doesn't change, which means the hydroxy just stay on the surface and no reaction occurs under the temperature. Case 2A, however, has less hydroxyl groups than case 1, so that means hydroxyl are combined to form water molecules. So, and after that, continued from simulation 2A when the fragmentation rate
Did we lose them?
Yeah, it's actually stuck on my screen as well.
Okay. I'll try texting them.
Okay. Oh, maybe his internet went out.
Yeah, he's gone.
It looks like he dropped.
Yeah. Cliffhanger.
Well, we could go on to the next talk and have him finish up at the end, or why don't we wait 30 more seconds, see if he can dial back in.
Sounds good.
Jeff, are you there?
Yeah, I am.
Well,
Is it okay with you, Jeff, if we maybe press on?
Yeah, that's fine.
Okay. Well, excellent. Okay, so our next speaker, I guess, is Jeff Gillis-Davis, who will be speaking about lunar regolith surface features as indicators of volatile release. Hey.
Okay. So can you see that all right, my full screen?
Looks great, thanks.
Okay, great. So yes, today I'd like to present our research on looking at lunar regolith features and seeing some evidence for volatile release in them. So this all stems from evidence that has come out in the last 20 years from radar, albedo, impacts, and neutron spectrometer data that all show that there is water at the poles of the moon, and then with the L-cross impact, that shows us that it's not just simply water ice, but it's actually a very complex mixture and makes it even an interesting story, even more interesting. But the big question, at least in my mind after that, is, well, how did the water get there? And the origin story for water, as Paul Lucy illuminated about 30 minutes ago, is, three of the main reasons are thought to be solar wind protons, volatiles released from volcanic activity, or delivery from comets and hydrous asteroids. And Paul, I think, maybe dismissed solar wind protons as a source, and that's what I want to show today in the rest of my slides, so I'm glad I get to go second. So the premise here is we did some experiments a couple years ago, taking some olivine, irradiating them with deuterium. That helped us make sure that we were making heavy water that came from the experiments and not any kind of contamination. When we did our experiments without heating, we didn't see any evidence for water coming off the samples during the experiment or during the temperature programmed absorption or heating. But we hit the samples with a laser, as you can see on the right, on the top here, after irradiation to 10 to the 18 ions per cubic centimeter. We irradiated it with a CO2 laser when we heated it, and that was to simulate micrometeorite impacts. We were able to release D2O, and when we stopped the signal, at least of the D2 stopped, and also D2 would start to go down. And we're like, well, okay, we're at least now making water, but what does it look like on the samples? So we looked at the samples under SEM. So these two images, A and B, are SEM secondary electron images. And what you can see on image A, about halfway through, there's kind of a shoreline. On the left-hand side of that, there's some radiation expansion that happened. And within that, in the right image, we zoom in, and you can see there are these little vesicles. Some of them even have popped over lids. And it's like, okay, great. This is how the water is escaping. It seems to be happening in kind of little catastrophic events. So those vesicles are only about a half micron or so. But does this actually happen in lunar samples? So we decided to look at some, and on the left we have Neil Armstrong collecting our sample 1084. On the right is what it looks like when we put it on a SEM aluminum stub, and it's about ½ centimeter across. And you can see that we have about 100 grains laid out there. Now, when we looked at these under moderate and high magnification, we could see pits in different grains of sample, and we classified them into 4 types. We have bowl-shaped pits and small irregular pits in that first image, with these guys here being the bowl-shaped pits, and these are the smaller irregular pits, and we'll take a closer look at those. We have larger irregular pits like this guy here in the middle image with the arrow pointing at it. And then these circular, what we call bottomless pits, and these are only found in agglutinates. And they also have these kind of rims that almost look like they could be impact, but it seems to be caused by the process as it degasses. So looking at these a little bit closer, this is an impact melt glass speed, which we know from its composition when compared to Delano 1986. And we're looking straight down at this glass speed. It's actually oriented about 45 degrees. And when we tilt the stage about 90 degrees, you can see here are our bowl-shaped pits, the type 1 pits at both ends. And then you might be able to make out these very fine, small speckled pits, the irregular small pits along the body of it. We're going to zoom into this location next, just to kind of see the two in comparison. So orange arrow here points to our type 1 pits, the bowl-shaped pits, which are about 2 microns across. And then the blue circles in both cases show us the type 2 small irregular pits, which are only about ½ micron. And the next image, we're going to go and look at the grain on the other side. And what you're seeing here is at the top right-hand side is actually a zap pit or a micro pit from a impact crater, a microcrater, and it sheared off this side of the grain. And we find that the pits, the large pits, seem to be mostly antipodal to this impact, and also just adjacent to the impact on the other side. Unfortunately, we've kind of lost this part of the crater. But these pits look a lot like what we see in the experiments that we did. We did some TEM analysis of these pits, and you can just see, the bowl-shaped pit, even at this scale of a couple hundred microns, looks like a bowl. Up top is a bright field image, and then down below is a HADF or dark field image. So carbon and light elements are dark in the HADF image, and you can see a nice profile through the image or through the crater. And then these, again, are bright field and dark field images, top and bottom. The SEM picture at the bottom shows the 1, 2, 3 pits that we intersected, and you can see they kind of looks like a nook and cranny of an English muffin on top there. They're very irregular and a lot smaller. So it suggests it's probably a different formation mechanism. Now looking at some of these type 3 pits, the larger pits, this again is another impact melt grain that we're looking at. We're going to zoom into that box. And here's what the irregular pits look like on top and bottom on the left, and a little zoomed out image on the right. And you can see it's a little bit nicer looking than the irregular pits, but not as bowl-shaped as the bowl-shaped pits. And then moving along to the type 4, we're going to see that a zoom in from this left image, a higher zoom in the middle, and then an even higher zoom on the right. We see these holes that are in the melt glass themselves, which suggests that we're releasing volatiles either from the melt glass itself, or perhaps the blob of melt that landed on this grain actually heated the sample enough to release any volatiles that were contained in the sample. And then this is another image of a type 4. Again, we're zooming in as we go from this time right to left. So on the far right, you see what looks like a nice agglutinate, which is just a melt welded grain that holds together pieces of all types of little rocks, melt grains, and
Keep it, Mark.
thank you. And as we zoom in the middle image, you can see a melt blob that's on the top kind of middle part. It got cross-sectioned, and you can see how vesiculated this melt is, much like agglutinates are known to be. And as we zoom in further and then finally to the bottom, you can see where the melt was sticky enough where when gases came out, you form this kind of lip or rim around the holes, which suggests it's happening over time. Some of these holes have very sharp rims, and then some, after maybe a little bit more cooling, gets these kind of lips or rims to them. But it shows how this pit is probably just an intersection of one of these bigger vesicle voids within the melt. And in this last conclusion, here's another impact melt glass with an impact again in itself. You can see it's got a lot of radiation blistering in some of the small pits, but we don't see any of the larger pits on this. So in conclusion, the type 1 and our type 4, the bowl shape and the bottomless, are evidence of some kind of volatile release. It's either like a 1-2 step process where we have solar wind implantation. It gets stuck in the samples until it gets released by an impact heating event, like our experiments suggested, or some nearby melting, which is kind of like the DeSimone Orlando model. Or the pits might actually be created by volatiles supplied by the impacts, which is kind of interesting if we could get some trapped gases from these. The type 2 small irregular pits might be produced by very low thermal events. These are found ubiquitously over many surfaces, and it could be some evidence, physical evidence of recombinative desorption. And then finally, the type 3, the larger regular pits, they might be bowl-shaped pits degraded by space weathering, or maybe even impressions made while the melt was hot. We see, like in the image on the right, sometimes stuff can actually get stuck in the melt. So that's all I have to present today. TGIF to everyone, and thanks for a great meeting.
Thanks so much, Jeff. We have a question that came up from Tom Orlando asking whether you can confirm that the electron beam in the SEM is not contributing to this. And then he also asks whether you had time-dependent studies to look at if the pits change, mentioning that this could involve a classic radiation damage process.
I think Tom's question is probably mostly focused on the experimental samples, so that's how I'm going to answer it. We didn't see any change with the pit or creation of any pits while we were looking at these samples. With the SEM, we are aware that it is possible to damage and heat these samples up. So we were using low voltage and a wide beam. So we don't think we made it. What was the second? Oh.
Okay. Yeah, you have some more questions coming in the chat you might want to look at.
Okay.
But I think we'll go ahead and start the next talk. So I'll hand it over to Carl.
All right, thanks.
Thanks, Jeff.
All right. The next talk will be by Emily Costello, Impact Gardening of Ancient Ice on the Moon. And before you start, let's remind you that you will be able to finish this talk at the end of the session. So after Rosemary finishes, stay on so we can hear the rest of that talk. Okay, Emily?
Yeah, setting up my share screen now.
We can hear you, but I don't see anything on the screen yet.
Okay.
Here.
How about that? Better?
Yes.
All right, thanks so much. All right, so today I'm going to be sharing some of the results of a recent publication. Got this paper into JGR Planets earlier this year. And it's a pretty big paper. We cover a lot of topics about impact gardening and its effects on ice on both the moon and Mercury. But today I'll just be focusing on the results that we got from impact gardening of ancient ice on the moon. So impact gardening is the process by which small, frequent impacts churn the uppermost surface of the moon. We're looking at an Apollo core here from Apollo 16, where the tick scale is centimeters. And we can see evidence of impact gardening in this core, where on the left, this area was closer to the surface, and on the right, further from the surface. This gradient of darker material to lighter material is the evidence of impact gardening, where space-weathered material has been churned and worked to depth, much greater than it could have been produced at. I have a model that describes the depth of this impact gardening zone as a function of time. The parameters that I put into the model are a cratering rate and some Poisson statistics. The evidence of impact gardening from the Apollo cores is presented in this plot, where we can see these yellow squares and triangles. On the horizontal axis, we're looking at the amount of time that's implied by the mixing. And on the vertical axis, we're looking at the depth of that impact garden zone. The solid line is the results of the impact gardening model using the observed production rate of splotches. These are albedo anomalies that were observed in temporal pairs by the Lunar Reconnaissance Orbiter camera team and published by Spire et al. In 2016. Now, the dotted blue line is a completely theoretical production where I've put in a model of the flux of secondary impacts that includes assumptions about how many secondaries are produced per primary impactor, how many, the velocity of those secondaries, the material properties of the surface regolith, including yield strength, porosity, and density, and also the density of the impactor itself. Now, my completely theoretical model that includes all these assumptions about secondaries and material properties fits the model that used those observational cratering rates and the depth of gardening implied by the Apollo cores. Now, here's another perspective of the impact gardening results in regolith, where I've flipped the vertical axis, where we're still looking at gardening depth, but we have the surface at the very top and we're proceeding to depth, digging deeper as we go down. The horizontal axis is probability. Now, we can think about probability here. If you're familiar with crater statistics, you can think about 100% or approaching 100% probability as crater saturation at these gardening depths. And at lower probabilities, we're at crater sizes and crater depths that are approaching saturation but haven't reached it. And due to the stochastic nature of these impacts, there's some probability the region will see more impacts and deeper gardening than is implied by that 99% saturation gardening, thorough reworking. Now, there's some evidence that there are ancient ice deposits on the moon buried below possibly meters of regolith. Paul talked about this earlier, that Lior Rubinenko in 2019 showed that there are craters at the poles that are shallower in their depth diameter than other craters that are away from the poles. And he proposed that there may be a lens of ancient ice buried below the regolith. Ariel Deutsch also showed that these craters that have ice in them, the permanently shadowed region ice, are ancient, older than Copernican. Well, my impact gardening model shows that over the last billion years, impact gardening at lower probabilities has been upsampling that buried ice. And it's possible that impact gardening upsampling these larger, rare impacts could explain the present day patchy surface ice that we see. This is good news for ISRU. It means that even if the ice is buried 3 meters deep, it's still being upsampled by impact processes over relatively recent timescales, and it may be sampleable and more accessible to us. But I also want to understand how that ice got there initially. There's something that kind of bugs me about this idea of a thick layer of regolith over an ice lens. How did that regolith get there? I always point to the pyroclastic deposits, which are supposedly about the same age, billions of years old, but they're still spectrally distinct at the surface. They haven't been covered by a layer of regolith. So what if instead we had an exposed ice deposit that was exposed to impact gardening over time? What would happen to that deposit? And I can explore using my model how thick that ice deposit must have been initially to have been gardened away to its current state today. So to start, I'm going to model impact gardening in an icy target. Here we're looking at a plot of impact gardening as a function of time again. And the white lines are impact gardening in regolith, and the pink and yellow lines are impact gardening in a hard ice target. I've taken that theoretical model and I've plugged in material properties for an icy target to get these calculations. Now, the flux that I use is only valid over the past billion years, and the ancient flux was much higher. So to anchor our gardening calculations, we anchor on the thickness of the mare regolith. Assuming that 99% probability, 10 reworking events have created a 3-meter thick mare regolith over 3.5 billion years. I can then scale my calculations of impact gardening in an icy target up appropriately. And I find that an ancient deposit must have been about 10 meters thick. If an ancient ice deposit was 10 meters thick, then gardening of that deposit would have pulverized it and mixed it with underlying regolith. This thickness of 10 meters is similar to the thickness or the order of magnitude of the thickness of Mercury's ice deposits. And it's also similar to the thickness that was proposed by Deborah Needham in 2019 from a volcanic source that may have been ancient. Now, in conclusion, I've been able to show that the moon may have once had Mercury-like extensive ice deposits that were about 10 meters thick, that have been pulverized and churned into underlying regolith over the past 3.5 billion years or so by impact gardening. I also showed some hope for ISRU that the remains of any ancient ice that may reside well below the reach of present neutron spectrometer and radar observations are continuously presented to the surface by stochastic impact gardening. If you want to see more about this model or any of our other conclusions about ice on the moon and Mercury, I've included the reference here for your further exploration. Thanks so much.
Hi, Emily. Thank you very much. We have time for some questions. I have one, but I'm waiting for some to show up on chat or a hands be raised. But while waiting for that, can you give some insight onto, in the gardening, how isotropic it would be due to this process, or do we expect things to be uniformly mixed or not?
So I think that we can kind of capture that with the probability. Like I said, the higher probabilities are crater saturation. That is that every point on the surface has been influenced by a cratering event. And I would say that that's pretty well mixed. If we look back at the Apollo cores too, we see a really well mixed zone of space weathering products to about 10 centimeters depth in the right time period. So I would say it's pretty well mixed.
Okay, thank you.
Yeah.
We have another minute till we need to move to the next talk, so stay on schedule. Just wait about 30 seconds or so.
Okay.
I think we have a question on the chat, Emily, which is whether you've considered the moon's obliquity and how that might have changed over the past 3.5 billion years.
Well, that's really interesting. I haven't included that. Does this person asking the question mean that there would be a change in the impact flux implied by the obliquity?
No, just that the moon may have wobbled around, and so if it wasn't placed at the poles 3.5 billion years ago, the pole might not be there anymore.
Right, that's a great point. My model is pretty simplistic. I'm just throwing rocks at the moon basically, and whatever is there, I'm hitting. So if the moon had some wobble, and if these ice deposits were thicker to begin with, and were eroded by obliquity and sublimation processes, then that gives us a bigger budget initially of ice. So if we had more water delivered, we could have more removed, but impact gardening could destroy a 10-meter thick deposit over the past 3.5 billion years.
Okay, thank you, Emily. Very, very nice talk. Let's now move on to our next talk by Norbert Sorkhofer. He will be speaking on what ice on Ceres might tell us about ice on the moon. So, Norbert, are you there?
Yes, can you hear me and see my
Yes.
slides?
We see you, but we don't see your slide yet.
Oh, I haven't turned on screen share, I guess. Um,
And it's trying. It will be there soon. Here we go.
how about now? No?
Yep, looks great. Thank you.
You see the slides?
Yes.
Okay. So, so Ceres is, of course, the largest of the asteroids, and it's also a dwarf planet. And it's still much smaller than the Moon and Mercury, but it has several closely related properties. And one is it has permanently shadowed regions. So its axis tilt is only 4 degrees, and so it provides a great comparison to the permanently shadowed regions of Mercury and Earth's moon. And it's an ice-rich object to begin with, right? So it's sort of always been understood from its low density, and now so Dawn has explored Ceres from 2015 to 2018, so we understand so much more about it now. And so here's a graph of modeled temperatures, and the average temperatures of pole world of about 75 degrees or so. The average temperatures are 110 Kelvin, right? So although these are sunlit regions still, this ice-rich area has a similar temperature than the mean temperature than the lunar cold traps have. So there's some analogies, and we can perhaps learn something from Ceres about the cold traps on the moon, or icing cold traps on the moon. And so one of the there was a surge of ice on the surface of Ceres, and almost none was found. So this famous bright spots in Ceres, which some of them have even been seen from Earth, they turned out to be mostly salt. And so eventually some ice was found, and it's in I don't know if you can see that. Seems to be a delay in the slides. That there's a wide region, which I'm trying to point at here, close to a rim of a crater and so on, where a spectrometer picked up some water ice, and eventually a few spots were found, which are partially water ice, but very small. The largest water ice deposits on the surface of Ceres are actually in the permanently shadowed regions. So it's almost completely near subsurface is with neutron spectroscopy. So the grand instrument measures the neutrons coming back and concentration of hydrogen, and there's a big north-south gradient in the hydrogen concentration. The top meter of Ceres is ice rich, and equator it's probably just a bit lower than that. And in the polar regions, and in contrast between what the surface looks like, almost completely ice-free, while you have an ice-rich, even on a global scale, an ice-rich subsurface. And I think that has some implication just in a subsurface, and the absence of ice on the surface, apparently. So this is sort of a reminder from reality. The absence of ice on the surface does not for Ceres, but the moon. And actually the surface temperature temperatures measured by Divina. So both, which is an instrument around the moon, which measures the temperature. And so a numerical solution to what the subsurface profile temperature profile will look like. And then the bottom panel shows the sublimation loss. And so, you know, within 10 centimeter depth, the loss rate is reduced by 9 orders of magnitude, 9 orders of magnitude. So if a frost patch on the surface lasts for a year, it's going to last 1 billion penetrate to great depth. So, you know, subsurface ice is just much more stable, and sort of a surface is the last place to expect. The moon are the cold traps, right? So here's a nice just 3D image, and the cyan areas here are the cold traps of Ceres, which are the region on the Ceres. I don't know how well that comes through, but this is also actually, there's a bunch of images taken out at least. And that's because the axis tilt is only 4 degrees, at least currently. And then, and this is a model, and these are permanently shadowed regions. Their number sort of, or the fractional area sort of similar to the moon. And then quite quickly, actually, iprite deposits was found in some of them, but only some, and likely ice deposits in them. But the mystery was why only in some of them? And the answer was sort of found in the history of the axis tilt. So the axis tilt of the 20 degrees or 90 degrees, these persistently shadowed regions are smaller, and there are some which are really permanently shadowed for billions of years. So but sort of, you know, to the degree we can determine good evidence that these are indeed, this is a cold trapped ice. In a sense, trapping works on Ceres. It also works on Mercury, we know. And so it may just, how many? Okay, was this 10 minutes? Okay.
Yeah, 4 minutes left.
Okay, so it's been worked out fairly well, corresponds to radar bright features and other evidence. And it seemed the moon underwent about 2 billion years ago. The recent supply of water to the moon may have just been less than on Ceres. Cold trapping works on the moon, you know, there's ice in every cold traps. So conclusions, just because the surface has almost no water ice, doesn't at all exclude, you know, what technique we would choose to map ice on the moon. Then, you know, well, I didn't say that, but of course, Ceres is being bombarded by impact for its entire history, and yet there is still, and impacts have 2 rows, right? They can devolatilise, they can also recharge, and we don't quite understand this yet. But apparently, all this impacting did not get rid of its ice, and that may also be a lesson for the lunar cold traps. And finally, because some water ice in every single cold trap on the moon. Thank you.
Great, thank you. Very nice talk. We have time for some questions. I have one. Interesting, the correlation or the comparing the moon to Ceres. We've talked about that. Could you speak a little bit to that and the possibility of cold trapping other volatiles in these PSRs on a Ceres versus the moon?
Maybe what's the other one? Which whatever is next on a list. So so under current conditions, yeah, it looks like can trap. I mean, it's a simple estimate using a parabolically shaped crater, right? Then you can easily calculate their temperature, 24,000 years. So over that time scale, other volatiles may get erased.
Okay, thank you. And while I was asking the question, 2 more showed up on chat. So if you would, on the exploration resources in the lunar polar regions.
Okay, hopefully this is full screen on for everybody.
Yes, yes it is.
So actually this is a perfect place for this talk against impacts. So of course we know about impacts, you know about meteor showers, and of course the sporadic meteorites here on Earth. Tons of cosmic dust rains down on Earth every day. If you take that to the moon, that's about 5 to 15 tons of material that is hitting the lunar surface. Impact plumes of outgoing small particles, puffs of dust that in response to the incoming high-speed zero particles. There was a mission, the Lunar Atmosphere and Dust Environment Explorer, September 13, April 2014. It made science measurements for. Here I will only talk about the dust instrument itself. So we arrived and we spent about a month or so at between 50 and 100 kilometer height above the surface. And as we flew around the moon, the incoming particles had high enough speed, 1.6, 1.7 kilometer per sec. So the whole instrument has an effective surface area of about 100 square centimeter. They generate, at that speeds, they already generate a puff of plasma in ion detector, and the shape and magnitude of those signals would tell us about the size of the particles. This is all the data that we collected. On the x-axis is time, on the y-axis is the data. Our instrument once per minute. Little bigger particles with radii about 0.7 microns or so, you have to wait every 10 minutes. You have to wait 10 minutes to get an impact. Puffed up and became much denser, like during the Geminids or the Quadrantids or the Northern Tarids. These were the meteorites in December of 2013. We had not seen any effect, but please remember that Chang'e landed way up north, far away from us. And the ballistic trajectories of these parts, that there is a permanently present cloud of dust with a scale height of about 200 kilometers. About some of the black regions are the ones we never visited or we could not make measurements for various reasons, like time sharing with other instruments. Also, best understanding of the cloud that is engulfing the moon at all times, generated by incoming dust particles. The spacecraft is this white dot moving left to right, and then our impact rate is this funny shape because thresholds then are somewhat slower. And in a couple of minutes, of course, then you fly on the other edge of the impact plume. But as a function of height, you can figure out these plumes, and there's a beautiful organization that it takes longer at a higher across a plume. So using these plumes, and actually we don't even need a full plume, just a fraction of the plume, you could figure out where are these particles coming from. What was could make a chemical mapping of a planetary body. There is an instrument being built here. Sasha Kempf is the principal investigator here at University of Colorado. And either the plumes, if they exist, from other reasons, geological activity, or for certainly by generated by incoming particles, there will be dust particles raised from the surface. We have seen and identified surface, and then you could identify the makeup. You could identify regions that have possibly different makeup than the rest of the environment. So that you would have a spacecraft on a polar orbit and fly over permanently shadowed regions. I have to remind, as far as the incoming dust fluxes are concerned, interplanetary dust will come and hit the surface at all places at all times to collect all valuable resources, or even just even kind of the geochemical evolution of the you could make measurements, and not only the size and the speed distribution, but also the makeup instrument that the impact generated plasma is turned into or used as a time of flight mass spectrometer input. This was done on Cassini. Cassini was a linear. You cannot confuse ice with anybody else because it breaks up into clusters of all kinds of interesting things, like identified an interstellar dust particle while orbiting Saturn. And of course, because of the limited spatial instruments, could have a mass resolution that not only you could tell magnesium and silica and sulfur apart, but in some cases you could identify these permanently shadowed regions, identify water, and maybe even identify all the matter that we collected in there throughout history. So I think what I would like you to remember or recall, if you saw out of dust, and those particles, every single one of them is raising a little sample from the surface to the altitude of a spacecraft where you could, of interest, and you could certainly do this in permanently shadowed regions from orbit. Thank you.
Thank you. Excellent talk. We'll wait a couple seconds for that. Look on the chat window. There may be some questions there that may show up over time. Here is one. Yeah, we got time.
Particle detection of about 0.2, 0.25 micron, but we were also sensitive as an integrated signals and whatnot. We should have seen it, we did not. So particles are submicron, and the size distribution seems to be proportional, inversely proportional to the mass of the particles that were a few microns. By 150,000 detections, the bulk of those were submicron, 0.3, 0.5 size.
And
yes, I will.
Thank you again. We have to move on now to the next talk. So that will be Kevin Kennan speaking on a geologic model for lunar. Your slides up. How about a voice check?
Yeah, can you hear me?
Yes.
And this has been fairly well circulated, so I'm not going to spend a lot of time on it. And what I want to do instead is talk about some updates to this work and some new projects that are building on what we developed that looked at the sources of ice over time, the capture and retention at the surface and subsurface, and the evolution of these deposits, and wrapped all of those into update this. And so we've doubled the spatial resolution, and we've also adjusted a few things. And it's important to keep in mind that none of the data sets like the neutron spectroscopy and kind of improve this model over time. And so when we have new data sets coming in from some of these small sats and CubeSats, the hope is that works. And this is not based on any one particular volatile species, but it's based on kind of a complement of carbon-bearing phases. And this might be, now switching gears here a little bit, one of the things that we kind of realized in the early work is that it doesn't really make sense to think about a single episode of that's punctuated by the large craters at the poles that each formed at a distinct point in time. Now, those craters, when they form, materials work to age date craters at the South Pole to estimate ages for the floors of 43 new craters at the North Pole. And then what we've done is created, similar to Paul Lucy, we've also found that it's really the hydrated asteroids that are the dominant source by far. But because of that, you end up with this is using a probabilistic technique. And what we've done is to run a set of Monte Carlo simulations to make 10,000 ensembles of these stratigraphies for all the locations at the North and South Pole. We've also found in a small subset of model runs, we've produced something that looks more like Mercury with a very thick, I hope those will be out in the near future. Now, in the meantime, what I've been working on is to take some of those new lessons from that work and bring them back into this regolith features and processes here. And the ones in blue are new things that I'm working to integrate into this. And I think the most important one is that in the original paper, we just started with a pure layer count, these kind of episodic pulses of new ice deposited at the surface and worked down into the regolith. So that economic geology implications, specifically looking at prospecting. So there's a technique in terrestrial resource estimation called variography. And in most terrestrial hard rock deposits, you end up with something like this, where the ore grades are clumped together. And what you can do is create something telling you is that if you imagine plopping yourself down right here and you measure a high ore grade, you can be quite confident that in the immediate vicinity, now you could also imagine a scenario like here on the right where the ore grades are randomly distributed. This just looks like a noise function. And in this, we take the regolith gardening model and calculate a semi-variogram as a function of time. And so what I'm finding is that very early after a fresh pulse of ice at the sill, but what I'm finding is that quite quickly this evolves to something on the right, where you have this straight something like prospecting. Well, I think it means that you might not necessarily use the same kind of prospecting approach that you would on Earth, where you get things actually easier and less time intensive on the moon. Now, of course, this is a model prediction. And so the question is do we have any kind of ground truth or reason to think that the stratigraphic layers sampled by coring over any distance on the moon, right? And that's because of this regolith gardening. So I think, we need to ask ourselves, does it make sense we're going to go and map out the ice distribution in a given location? And does it make sense to say that, we're going to go search for buried ore deposits of ice under the ground, right? I think we have to be careful about what actually trying these deposits. We need to get access down into these cold trap environments. And I think it's important to distinguish between permanently shadowed regions and cold traps. The PSRs of the PSRs actually have a maximum temperature below 110 degrees Kelvin. So it's really the cold traps that we want to go down and get access to study that's being done out of JPL. And what they had been looking at was some architectures for setting up a mining outpost on the rim of Shackleton Crater. And I think what they realized maybe a bit late is working to look at the accessibility of all the large cold traps at both the North and South Pole. And we're doing this using an automated, and so you can see this here on the right, this algorithm is working to find paths between these well-lit staging areas outside these branches, then converge on what are kind of these super highways that go down into the cold traps at both the North and South Pole. What I'm showing here is kind of a generic measure of the accessibility, where red is bad and blue is good. And for example, there are some attractive options as well at the North Pole. We kind of tend to forget that the moon has 2 poles. So this work is currently under review, but you can grab ArcGIS shapefiles for all of these data that have these accessibility metrics encoded in as paper that we published. And the hope is that eventually we can bring all of these analyses together into a single consolidated units that I'm working to map out over both poles. You can see a sample of that here on the left, and then layer sample illumination based on different tower heights. So with that, I will be happy to take any questions or answer.
Was it, I don't know, can't say the name, just Cheek says, whatever, algorithm that you have used there? Sorry if I missed out.
Yeah, I think it's pronounced Dijkstra's algorithm. Yeah, that's what we use.
We have time now to move on to our next speaker, which is Hardy Prim. Parvati, are you there? The talk is lunar volatile science at the Lander scale, and there we go.
All right, and Carl, you can see the slides okay? Before I get into things, I'm Parvati. I'd like to acknowledge my co-authors on this, Dana Hurley at APL, Mehdi Bena, and that I'll show came from the Texas Advanced Computing Center, to which I had access through a grant from the NSF Exceed program, that even reaches the surface. It's been recognized for several decades that almost any landed lunar mission will be exhaust gases, including a variety of interesting species. And that presents us with both a scientific opportunity to study how those volatiles interact with the surface or exospheric volatiles, or even collecting samples. There's a real need to understand where exhaust gases go and how very likely to have a number of volatile detectors at the lunar surface again. This is something that's been done before. During the Apollo 17 mission, the LACE instrument operated for translating these observations into science. Modeling of some kind is usually a critical part of that process. And so of the gas coming out of that spacecraft nozzle, and we use those conditions to create representative molecules. Today, I'm focusing on the water vapor component of the exhaust, which is about 1/3 of the mass released, though it depends on what kind of fuel you're burning. Of the spacecraft, the gas is sufficiently dense that molecules can exchange energy and momentum through collisions. Further with the surface, we assume that it absorbs for some length of time that depends on the local surface temperature. Molecules can also escape. They can be broken apart by sunlight. We can begin to simulate what happens to those exospheric gases. The 2 snapshots here are taken at 3 hours after during the descent burn have temporarily absorbed. Purple indicates the coverage density. And then these halos that you see around the moon high slice through the plane of spacecraft descent. So this is 3 hours after landing, and you can see at this point a landing at 70 degrees south of a Chang'e 3 class spacecraft. In the vicinity of the landing site, the local exospheric density increases briefly by several orders of magnitude molecules to the surface, are very different. And that indicates that if we measure this during future landings, that what we measure, these densities that you see here, scale with lander mass. This was a fairly small, though impressive lander. If you have something that's heavier, it's going to burn more fuel. These densities will scale. The next few slides just step through. This rather busy figure here shows the fate of exhaust water vapor over the course of 2 lunar days. So if we walk through this, the water vapor that was released is still in the lunar environment. 2 days, 2 lunar days, that is 2 months later. Most of this is absorbed to the or on its way before it's photo destroyed. We begin these simulations at a point, we could begin earlier, but we begin for this particular case at a point in time. You'll also notice that around 13% of the water vapor that's released project those loss rates, those trapping rates rather, forward. We can anticipate that eventually, for this landing scenario, around 20% of the water vapor at higher latitudes. There aren't really many substantial cold traps at 70 degrees south, but at even higher latitudes, you do scale to the lander scale. So this is very much work in progress, but I think we still have some things to talk about. So what I've done here is this is a snapshot of the density of water adsorbed to the surface 10 seconds into the landing burn. So it's absorbed to the cold polar surface. I included this next slide here because I think it illustrates the scale. Thanks, Carl. Figure you saw on the previous page my attempt at an artistic impression of this. But of the surrounding surface is relatively localized. But at the same time, this gives you an idea of the scale. This is 10 seconds into the descent burn. And at this point, but you do get an idea of how this material spreads. In this case, you have a fairly thin layer of water adsorbed to the floor of Shackleton near the poles. I put this table in for reference. I don't expect you to read it, but the main point, burn, you can have a mixture of species. Water actually may be the least volatile of some of these species that are released. Some persist for longer. Others, such as CO2, N2, and NH3, are somewhere in between. They have a range of residence times and a range of photo lifetimes. And so I do want to try, there is still a lot of interesting work to be done from the modeling perspective, and I hope to update you on this as we progress through this, but also measurements of the surface and exosphere during and after future landings are really critical. And I hope that's something that we do going forward. Thank you.
All right, thank you, Parvati. Excellent talk. There are a couple questions online. And first one from Phil Metzger is, what type of model determined the original distribution of volatiles from the descent thrusters?
All right, so for the density, temperature, and velocity of the gas immediately outside the nozzle, we use an analytical expression that was derived by Roberts in 1966. Once these representative molecules are initialized, though, I then use a direct simulation Monte Carlo code to look at how the gas expands. So that's a DSMC code. And we do have a paper that is under review at JGR, which goes into that in much more detail. And, I'm always happy to follow up with excruciating detail by email.
Okay. May have answered his second part of the question. I didn't understand it if you did, though, which is, did it model the shockwave and ground jet features of the plume, or was it a simple conical assumption or something else?
Right, that's a great question, Phil. So because we're modeling, because these simulations start at a fairly high altitude, the spacecraft isn't quite close enough to the surface yet that you have a strong shock forming. And in fact, we cut off our simulations when the spacecraft is around 40 meters from the surface. So this is before the stage at which you have those strong shock features forming and surface alterations happening. So the model could be used to look at those near field effects in more detail, but in this case, we're sort of focusing on what happens earlier on in the descent when the gas has the potential to expand a larger region.
Awesome, thank you very much. And there are several more questions on chat, so if you would jump on there and answer them if you have time. Okay.
All right, thanks, Carl.
Oh, appreciate it very much. We are going to move on to what was going to be our last talk. Rosemary Killen is going to speak on chronographic observations of the lunar sodium exosphere. But don't forget that the talk that was interrupted will finish off after Rosemary finished her talk. So please stick around at the end of Rosemary's talk if you weren't planning to. So, Rosemary, are you here?
Yeah, do you see my screen?
I see your name.
I should
It
have.
does not tell me that you're sharing yet, though.
Oh, should have shared.
Rosemary, there should be a second button click selecting the display you want to share.
Oh, do I click on that?
Give me a second, sometimes it'll lag.
I'm not seeing anything
Still
come
nothing.
through just yet.
Share. Screen share has failed. Try. Well.
There we go.
Oh, okay. So let me go back. Okay, so I'll be talking about coronagraphic observations of the lunar sodium exosphere. I'm going to start with my key points. We found that the lunar sodium exosphere is enhanced during periods of high ion flux to the surface, as measured by Artemis, which is pointing to the importance of ion sputtering in refilling the exosphere. The temporal variations associated with high ion flux are consistent with a short e-folding time. And this is actually consistent with the Killen and Hurley paper in 2012. The scale heights to the extended exosphere increase towards both dawn and dusk limbs, and the column abundances in the extended exosphere are minimum at noon and maximum at both dawn and dusk, and I'll try to explain why that might be true. So our observations are taken with a lunar coronagraph out in Sonoyta, Arizona, and remotely operated from either Goddard or from my house. We reported observations that were taken in the spring of 2017, and we have a paper in review for observations in the 2018-2019 observing season. So for those of you who aren't familiar with coronagraphs, the point of a coronagraph is to occult the bright disk of the primary object, which in this case is the moon, so that the dim exosphere can be observed. And so we have occulting disks that can be moved in and out, and we have sodium filters that can be changed from on band, off band. Now, when you're observing the corona, the local time is a function of the phase angle of the moon as seen from the Earth. And so we can get the exosphere as a function of local time and latitude. So this is an example, but you can see these are actually two observations that are superimposed. We take a 10-minute observation with the occulting disk in place, and that's the black that you see. And then we take a half-second observation of the lunar disk. And we found that it was difficult to get the scale height by rotating around the moon. So we used a polar transform so that we can just scale horizontally and vertically to get our measurements. There's a lot of data reduction that goes into reducing the raw data to get the sodium out, but I won't go into that. I've plotted the waxing and waning phases separately because you're looking at different, the exosphere over a different lunar real estate. for these two phases. So these are waxing, these are from new moon to full moon. And in general, what you find is if you plot the column abundance with latitude, the asterisks there are cosine functions, just to give you a feeling that the corona doesn't follow the cosine. What our observations begin at about 150 kilometers off the surface of the moon. So we are looking at the extended exosphere, not the near exosphere. And you can see from the left-hand side that in local time, in general, from dawn to noon, we decrease, or from noon to dawn, we increase in column abundance. It isn't one-to-one. You have some outliers, notably the blue, which is morning, is not as dense as noon. But in general, there's this sort of trend. And the scale heights are also, they vary a lot, but in general, they average around 1,000 kilometers. And that's consistent with a 4,500 Kelvin temperature. Now, I don't believe that temperature is a good model for an exosphere, but just, because people talk about temperatures, that's about what it would be. And for your waning phases, the scale height is also about 1,000 kilometers. It can be as low as 500 and higher, but in general, it's hot. But and 4,500 is actually hotter than most people think impact vaporization. So there probably is a component of sputtering. There's also this is consistent with what was predicted way back in 1995 by Smith and Marconi. So radiation pressure would tend to increase the scale height towards the dawn and dusk limbs as well. So here you see the opposite trend from noon to afternoon. It increases towards afternoon. And you see, this is a mixture of waxing and waning because we didn't have very many observations in 2019. And again, the variation with local time is a little bit mixed. And for these observations, the scale heights are not quite as consistent, but they're hot. And I'm going to show there's a correlation with Artemis data for some of our dates. On March 3rd in particular, you can see at the bottom where Artemis showed that the ion flux to the surface of the moon, this is in the magnetosheath, and the ion flux abruptly increased. And we measured one of the highest column abundances that we ever saw. So there's some correlation with ion flux, but also February 1st didn't have a particularly high ion flux, but it was near full moon. And as I said, the full moon observations, which we are looking at dawn and dusk terminators, and we have very high column abundances there. So the measured scale heights are on the order of 800 to 1,800 kilometers, but they average at around 1,000. And that's consistent with observations by Cuparacci et al. They used a Fabry-Perot to measure the velocity distribution at the moon. And they also got very high temperatures. The scale heights increase as the moon approaches full phase, but also as it approaches new moon, the scale heights increase. But these are times when you're looking over the dawn and dusk limbs. And I think, like I said, this might be more consistent with radiation pressure than with a different source. And so we do have exceptionally high abundance associated with high ion fluxes and with full moon. And the data are consistent with a minimum near noon, which I believe is also consistent with radiation pressure. So I'd like to acknowledge NASA solar system observations, funding Dream 2 and Leader. And I had students from Howard University, and they were funded by the Minority University Research and Education Project. And a student from Embry-Riddle was also funded by my Solar System Observation. And we thank Artemis for their data. So just to show you where the telescope is, it's in Arizona on the high plains. It's not on a mountain, but it is at a high elevation and very in a very remote area. So there's only one person who lives nearby, and they sort of take care of logistics of internet and so forth. And there we are. So that's what I have, and I'll take questions.
Fantastic. Rosemary, thank you very much for that talk. We do have time for a couple questions before we move on to our newly last talk. Let's see, I'm looking on chat and do not yet see one. Let's wait another 30 seconds or so before we move on to our last talk. Again, Rosemary, thank you very much.
Thank
Nice
you.
talk.
And where, oh, there's Survey.
Oh, you're still sharing your screen, of course.
I'm trying to
Okay.
Or trying to find, oh, there I am.
Okay. Yeah, let's move on to the last talk. If are you there?
Yes, thank you so much for this.
You're a little bit your voice is low.
Okay.
Still low.
Let's see. Can you hear me now?
Yes.
Okay, that's great. Thank you. I'm gonna share the screen. Okay, can you see the slide?
Yes, and your voice is better now too. Thank you.
Thank you so much. I will go over this really quick. So basically, we're trying to use deep dielectric charging events to obtain a really high electric field, and we want to explain some water formation process based on this electric field. So I believe that's where I left. We set up a molecular dynamic simulation like this, and then so this is we tested two cases, both with the same setup. And one of them is completely without electric field, and we call it simulation 1. And another one is with an electric field of 5 × 10⁶ voltage per meter, and that's simulation 2A. And we plotted the time history of the number of water molecules, silica 4 tetrahedra and hydroxide group. And case 2A has a significant amount of water generated, and the silica was melted down, as we can see from the number of tetrahedra. And for hydroxide groups, case 1 doesn't change too much, which means the hydroxide just stay on the surface and no reactions occur under that temperature. And case 2A, however, has less hydroxide groups than case 1. So that means hydroxide are combined to form water molecules. So after that, continue from simulation 2A, when the fragmentation rate of the system reaches the highest value, we shut down the electric field and relax the system to 40 Kelvin as case 1. So that represents the end of a deep dielectric charging event. And the system was cooled down by heat conduction from outer system. So that's actually the video. So the connecting energy of the atoms, of all the atoms, turn into potential energy by forming bonds. And finally, the temperature was relaxed to the original temperature, and the final structure was obtained as figure C. So now let's take a look at the time history of molecular numbers. So simulation 2A, it was actually shown before. So after we shut down the electric field, the silica tetrahedral numbers grows, which means the regular structure was reformed as it used to be, and the water molecule number total was not water molecule number decreases a little bit, basically due to the trapping inside the silica structure. And there are a lot of water molecules attached to the silica surface, and from and there were like hydrogen bonds and other bonds formed. So we also found some ice structure as shown in figure C. So one of the interesting features we got from this simulation is that fully hydroxylated silica surface is believed to be hydrophobic. And our simulation just shows that the reactions turning reduce the number of hydroxy groups and water molecules are attached to the surface. So that potentially means the deep dielectric charging breakdown leads to the change of hydrophobicity of the surface. Well, this could be a key feature for lunar regolith, basically because that would tell us whether the regolith is able to deposit water or lose water. So later we did another simulation to reapply the electric field to the structure we got from simulation 2B. And once we apply the electric field again, we can see some hydrogen and water molecule released. So we started to think that for larger systems, if the volatiles are released from the regolith, then maybe we can see the porous dust particle structure. Another interesting finding from another simulation is that when we shoot hydrogen atoms from the top of the surface, hydronium ions are captured. Hydronium ions are also a carrier of water molecules. So if more in situ measurement data can confirm these ions, then the charging potential of lunar surface might also be a factor for lunar water transportation, like from lower latitude to polar region, and also from day side to night side. So to conclude the work, a new hypothesis is proposed for water formation at the lunar surface, and it was simulated by molecular dynamics. We found the hydrogen from solar wind interact with regolith to form water, and with an estimation of 3,500 years of implantation, more than 15% of the oxygen from the regolith becomes water. And also hydronium ions are also captured, which could potentially become an important factor in lunar water transportation. And also the change of hydrophobicity could be another outcome of space weathering and deep dielectric charging. But anyway, the electric field from space weather may be a key factor in the water formation process. So, and with that, I will take any question you may have. Thank you.
Very interesting talk. Sorry, it got interrupted halfway through. That's unfortunate.
Yeah, apologies for that.
We got you in time anyway. Are there any? I see a hand is up. Micah, you want to go ahead and ask your question?
Easy, you. This is a really interesting talk. I agree with Carl here. One thing that I noticed, and I recognize that these are probably early results for you, but how do you explain the fact that no experimental measurements have ever seen the formation of water molecules, while your simulations do?
So I'm sorry. What was that question? Like, for the measurement.
There's a lot of experiments that have been done on silicate, SiO2, implanting with hydrogen, and pretty conclusively showed that no water was formed. But you appear to be showing that a lot of water is formed. So looks like maybe you froze again. Uh-oh.
Oh, that's too bad. Are you there? Now, his models assumed cold temperature, weren't they? Because he was using dielectric breakdown, which requires for that resistance to be large. Regolith needs to be cold. So I understood his talk. Well, that was actually going to be my question. What temperature does this occur at?
Gotcha.
Yeah.
Sorry, could you hear me now? Use another device. Great. Oh, I'm so sorry for the power outage. And could you, if you can, could you repeat the question again? I didn't catch that.
Oh, my question had to do with the formation of water molecules, and if you can explain why you see them in your model, but they haven't been seen in experiments.
I think there should be some experiment, like I mentioned before. There's, I think there's a group in Hawaii did some micrometeorite impact to produce some to produce some energy for the fully hydroxy lunar simulant, and then water formation was detected by this kind of mechanism. But I don't think anyone have this have done this kind of dielectric breakdown experiment. So that's kind of something we are interested in the future. Maybe we will test this in our lab, or maybe looking for some in situ measurement data when the space weather is really extreme condition in the polar region. So maybe that could be a verification for a model in the future.
Well, I got you. I understand now. This isn't due to hydrogen implantation or irradiation. This is dielectric breakdown of saturated soil.
Yeah, that's right. Sorry, I didn't show that in before.
No, I got you. Thank you. That's very interesting.
Thank you so much.
And let's see. Pam Clark mentioned everybody that there's a group. Okay, she confirmed what you were just saying.
Yes, I noted that experiment with great interest. It came out, results started to come out about a year ago or so, perhaps. And they were the first group, I believe, that added in the thermal bit from simulating micrometeorite impact. There's still a lot of work to be done, but it was a very interesting result.
Yeah, that's the paper I was talking about. Is the use of like micrometer impact lab to simulate the micrometer impact. That was really good.
One last point by Jeff Gillis Davis is that you're basically, the difference is you're doing this through dielectric breakdown instead of irradiation with the laser. Different process. Yeah. What temperature does the soil need to be at for a dielectric breakdown to occur or be effective for causing this? Is that part of your model?
So basically, I think from a model, from our molecular dynamic model, I see the temperature can go up to like over 1,000 Kelvin, and then but immediately, like in femtosecond, they were relaxed into like 40 Kelvin, which is the environment temperature on lunar polar region.
Okay.
So the reaction actually happens in a really fast period, and then it will relax to the iridium temperature.
I see your point. Okay, thank you. So this concludes the session, but I think we're supposed to stay on, or can stay on, for additional chats. Is that the way it works? You'll see that this whole session.
Hi, Carl. It's Christina. Yes, you can. I just quickly want to announce that we're going to stay on time today. Great job with the session and timing. Thank you. So we'll start the Student Poster Award announcements at 1:30 Pacific time, but please continue to your discussion until you feel that you have exhausted everything you want to. Did you all hear me?
Yes, I heard you.
Okay.
It's not exhausted already. At least
it's exhausted already. Okay. I was finishing up my own task here, so I missed that. So if it's exhausted, everybody can take a break for 20 minutes and we'll see you back then.
All right.
Thank you very much, everybody.
Thanks you.
Thanks to all the speakers.
Ricky, are you on?
Yes, I am.
Okay, this is Deborah Domingue. I'm one of the co-chairs for the next session.
And your audio is nice and clear.
Okay, so we're, instead of, basically saying, hey, you've got, 8-minute warning, I would like to try a bell.
Sure.
So I just want to see if the one that I've chosen works.
Okay, so I'll just sort of keep making noise and as if I was presenting, and you can ring the bell at any time to see if it rings.
Do you hear it?
It's very faint.
Okay, so I don't know how to make that louder because it's pretty loud. I hear it in my headsets really loud.
Deborah, this is Jim. I'm your first speaker. It wasn't very clear to me at all. So
it wasn't, yeah, no, it's got to be clear. Let's see let me try something else.
Feel free to use your voice. It's okay with me.
Holding up the, whatever's making the noise next to your microphone.
Well, it's my computer's making the noise. So hang on, I'm going to try my phone just a second because earlier it was not very loud either.
Yeah, if you use your phone, it'll probably be better. Oh, that's much better noise.
Was that heard?
Yeah, that was a better.
Jim, did you hear the doorbell?
Yeah, I did, but is that going to be 8 minutes or 10 minutes?
That's good. So we'll give the, Ben and I will give the instructions at the beginning, but that's going to be 8 minutes.
Mm-hmm. And then another one at 10.
I'll give another one at 10.
Okay.
And then at 12, I will interrupt you.
Okay, that sounds great.
Hi, Deborah. It's Christina Gibbs. How are you?
Hi, Christina.
Just really quickly, the poll.
Yes.
I just threw up our standard slides that everybody's probably pretty sick of or memorized by now. But what time, Ricky, do you want to do the poll? And will it just be on top of this?
The poll will initially open up right on the center of the screen.
Yeah, so it'll just be in front of this and that's okay, or just stop this and it can be in front of the image you've been posting?
So when I spoke with Ben, the idea was that at the beginning, we'd each introduce ourselves. He would give the rules of the road. We'd put up the poll and people would have till the end of the session and we give the results of the poll at the end of the session.
Okay, one of the features, good or bad, about the poll is that it's a pop-up window and it'll be on people. Well, once they answer, I guess, does it go away, Ricky?
No, but they could close that window.
They can, so they can answer it and then close it?
Yes.
Okay, all right then. I just didn't want it to be annoying to people for an hour or plus.
Yeah, no, I don't want to annoy anybody. The goal isn't to annoy people, but it's just a fun thing. It's just to get people the spirits. Okay, what do I like about the moon?
Okay, no, I think that's great. I love it.
Is that going to pop up in the middle of the talk, or where is it, in a chat box, or where does that go?
So what it'll do is it'll pop up before your talk. So during the introductions that Ben and I do.
Mm-hmm.
So
and you could answer it and then close that window.
Yeah. So and we'll tell everyone that okay, there's going to pop-up window, answer it, close it, it goes away, and we'll give the results of the poll at the end of the session. And Ben and I decided to do things a little differently. He's going to do all the introductions, and I'm going to do the timing and the questions and make sure that I'm going to handle that part of it, and we're not going to switch mid-session.
And when you want the poll to be revealed again?
At the end of the session.
Yeah,
okay.
Just let me
I'll
know,
ping
then
you.
I'll bring it, I'll publish it.
Okay. Yeah. So Ben is going to do, basically he handles all the intros and I handle all the end product, towards the end, the questions. I'll do the results. He'll introduce the poll and I'll do the results at the end. So I think that's the way we had kind of worked it out.
So Ricky, this is not going to pop up in the middle of the talk anywhere, is it?
No, it will not.
Okay, thanks. Just feel more comfortable about that.
Yeah. So like I said, we'll put up the poll before you start talking. And if you answer and close the window, you're good to go.
Just inform people to answer and close the window as well. I think it will help for people who aren't completely sure how to make it go away. Say you can answer it, your answer will be logged, and then go ahead and close the window, and we'll share the results at the end.
Is this all going to go on during the beginning of my talk? Is that the idea that people are going to be answering this on their own?
No, they're introductions to themselves.
Okay. So and it's not going to pop up on my window, is it?
It will pop up on your window. You answer the poll or not as you see fit, and close the window.
Okay, sounds
and
great.
It should pop up while Ben and I are introducing ourselves, introducing the session, giving the rules of the road for the session.
Okay, great.
Okay, so that's when it should pop up.
And I don't know that I'll take the full 15 minutes for the student poster awards. We're only announcing 3 students. But I have a few thank yous to make, and we'll announce them, and then we'll hand it over to you guys and be out of your hair.
Hey, Christina, I can always use the extra few minutes.
Well, with that in mind, actually, so I would say I will go as quickly as I can without going too fast. But by all means, start your introductions and don't feel like you have to wait, Deborah. As soon as I'm done, just go ahead and start doing that, because you do have a little something extra special so that Jim can get his full 12 minutes.
So the goal here is to make sure everybody gets 12 minutes.
Yeah.
But everybody gets just 12 minutes.
Well, I was going to divide it up among the speakers equally, of course.
You always have wonderful things to say, Jim. But yeah, I think we are all looking forward to the session and looking forward to a great conclusion as well. All right. So after you're done with Dr. Metzger, we probably need to see if Greg is on, but it may be that he's intending to introduce Carly. I need to confirm that.
I can certainly do that. Yeah, I'm here.
Okay, great.
Okay, so you want to do the intro. We'll just need to, when Ben logs in, he was grabbing lunch real quick. So when he joins us, just let him know that you want to do the intro for Carly, because he's doing all the intros.
Okay, sure. That sounds great.
Yeah.
Maybe I'll send a private message in chat too.
Okay, let's see if you can see me.
Yeah.
Okay, I can't.
I can.
All right. Okay, great. You know what? Let me put on a background, because I think. Let's see. What I'm going to do. I'm going to do this. There we go. Happy place. Okay. Ben, are you on?
Yep, I just got here.
Okay, cool.
Yep.
Cool.
And I am, go ahead.
So I was talking with Ricky and Christina and Greg. So we'll introduce the poll as part of our introductions and rules of the road stuff. And part of it is to tell people that answer the poll and then go ahead and close the window. And that will give the results at the end of the session. They don't want the window sitting in the middle of their screen the whole time.
Okay. That sounds good. I'm just looking at the program, making sure that I have everybody's names. I'm not seeing all of their organizations though.
That's okay. I think you just introduce their name and their title. By the way, Greg wants to do Carly Peters at the end. He wants to introduce Carly. So that's the only.
Greg wants to introduce Carly?
Carly, yeah. Hers is basically an invited presentation. So he would like to introduce her, but we introduce everybody else. So basically our session ends with Phil Metzger.
Okay.
And then Greg will introduce Carly and he will provide the closing remarks. So so I think maybe what we can do is we can provide the poll results after Metzger's talk.
Okay. That sounds good. And then I'm trying to find everybody's titles too, as far as like doctor, professor, so on.
Just assume everybody's a doctor.
Okay.
Good advice. Hey Ben, this is Jim Head. I'm the first one up, so I'm ready to go. So not to worry. And I also have my affiliations. I think most people will on their screens. Okay.
Oh, we have the student poster awards first.
Yes, we'll do the student posters.
Yes, and that's starting right about now.
Yeah.
Okay.
Okay, I'm gonna go ahead and mute.
Yep, me too, and I'll just go after you.
Okay.
All right, well, that was a great lead in. It is time. Ah, dang it. Nah, go backwards. I am having so much trouble with that. Well, some of you just got a heads up, but I'm so frustrated with my advancing slides on this setup. But I will hit reset and we will start our award sessions right now. I would like to thank all the students who have submitted their request to be evaluated. We had 13 students compete in the poster competition this year, and that was fabulous. I would also very much like to thank our judges. We had 13 fabulous judges, and they all completed all their evaluations on time, and was really great to be able to see the students get a really nice representative evaluation. So thank you for that. This year, the students will get a $1,000 stipend for their awards, and that goes to all the students in third, second, and first place. For those of you that we do award the stipends, we will have you jump to a breakout session, and by doing that, it really means that Ricky will invite us to a breakout session as soon as the awards are done so that we can take a picture, but that will allow the plenary session to continue without having to wait. And after I make the announcement, go ahead and turn on your camera and your microphone if you like, so that everyone can congratulate you. There's a few ways to do that if you haven't figured it out already. I do believe in participants. There is a way to clap. Where's the clap, Ricky? It's not in participants.
It's under the reactions.
Under the reactions.
If you do it in the reactions, it's in the on the screen, on the video. If you do it in the chat, it shows up in the, or it's actually under the participant list, under the more section.
Okay.
That'll show up in the participant list.
Okay. Well, I didn't even touch my computer and it advanced the slide. This is how touchy the system is. So without further ado, I am going to congratulate Kristen Lechsinger for her poster titled Pushing the Boundaries of Lunar Ice. I'm gonna reduce this. Vertical volatile transport in seasonal shadowed regions. So Kristen, congratulations on receiving 3rd place. Are you here with us today?
Yes, I am. Thank you very much.
Oh, wonderful. It's great to see you. Thank you for all your effort and all the extra that we asked you to do for our poster sessions.
Thank you. The poster sessions went really, really well. So thank you to everyone who organized that. That was fantastic.
That's wonderful to hear. Thank you. We put a lot of effort into that and we're glad to hear it paid off. Thank you. Okay, now I'm going to attempt to move on to the next. Okay, in 2nd place is Marina Gemma for her poster titled Multiple Dimension Characterization of Mineral Abundance in Ordinary Chondrite Meteorites. So Marina, are you still here?
I am. Thank you so much, Christina. It's really an honor.
Wonderful. Wonderful to have you, and thank you again for your help in being a session chair as well as contributing. Okay, and so I don't think I've accidentally shared this one. So the 1st place goes to Ryota Nakano. Ryota, are you with us today? And her title was Mass Shedding Activities of Asteroid 3200 Phaethon Enhanced by Its Rotation.
Hi, can you hear me?
Yes. Hi.
So much. I was not expecting that.
Well, you did very well and it was rated very high. So congratulations. And thank you for being a part of it. We're very excited about the next generation. We put a lot of effort into supporting it and hopefully you all have a very, very bright future. So with that, I promise
Congratulations
to hand over,
to all of our poster award winners.
Thank you, you guys, and thank you, Greg. I promised to hand over a few minutes to the session following us, but Ricky, if you can throw the 6 of us into the breakout room, the other group can get started. Thank you, everybody, and well done.
Thank you.
Well, I want to also voice my congratulations to the poster winners. Job well done, and thank you for your participation. It's our final plenary session. My name is Deborah Domingue. I'm with the Planetary Science Institute, and I will be chairing this session with my co-chair, Ben Farr. Ben, you want to say hi?
Yeah, hi. I'm Ben Farr. I just graduated. I am a research assistant with the Impact Dust Lab at LASP at CU Boulder. And so to start the session off, we wanted to do a little poll just to kind of make it, a little bit fun. So the poll is going to be, which is your favorite swirl region? And then you've got 4 options. So everybody who wants to vote, please vote. And then once you do, go ahead and just exit out of that window. And then we will reveal the results at the end of the session. And also, while everybody's doing your polling, I just want to kind of lay out the rules of the session, just so that everybody knows exactly what's going to happen. So everybody gets 10 minutes for their discussion and then 2 minutes for questions. And then to kind of keep track of time and just make sure everything is going according to schedule, we will give you a warning at 8 minutes in the form of a little bell. We didn't want to interrupt anybody, so there's just going to be a bell at 8 minutes. And then there's going to be a bell at 10 minutes, and that means that it's time for your questions. And then once you hit 12 minutes, we will cut off your time.
Just so you know what the bell sounds like, here we go. So that's your bell.
Yes. And then at the end of your time, we will unfortunately have to move on to the next, just to make sure that everybody gets their time. So with that being said, we're going to go ahead and move on to the first presentation, which is going to be by Dr. James Head. And the title of the presentation is Rethinking Lunar Mare Basalt Regolith Formation, New Concepts of Lava Flow, Protolith, and Evolution of Regolith Thickness and Internal Structure. James, go ahead and take it away.
You got that?
Yep, we can see it. We can hear you.
Okay, great. Thanks. Okay, so I really want to talk today about essentially Mare basalt regolith formation and rethinking this from the context of not just our terrestrial experience, but also what happens on the moon. And a really critical part of this is that when we look at the characteristic lava flows on the moon, such as these Eratosthenian flows in Mare Imbrium, you know, we think, oh, they look a lot like the Earth. Okay, there's a high aspect ratio of length versus width. And also we see a lot of evidence, for example, of the characteristics of these in terms of regoliths superposed on top. Stand by 1 second. Okay, so these superposed impact craters then, of course, build up the regolith as a function of time. And we see in this really nice diagram, conceptual diagram by Wilcox et al. In 2005, that the characteristics of the basic lava flow that comes out here is the protolith. This is the basic rock from which the regolith is derived. And it's generally thought to be a solid lava flow. And then, of course, the superposed impacts build up the regolith as a function of time. We can start to map out the thickness of the regolith using the Quaid and Overbeck classic method of looking at larger craters, ever larger craters, until they penetrate to the substrate. And then we can derive from the depth diameter relationships a key estimate of the thickness of the debris. And sometimes it ranges from a couple of meters from the youngest flows up to 10 to 15 meters for the oldest flows. We've also walked around on the surface with the Apollo missions, and we put cores into the surface down to about a meter or so. So we have a lot of information about the regolith, but what I want to talk about today is really the characteristics of the regolith from the point of view of regolith protolith. What is the primary rock? We are really prejudiced by, I think, our terrestrial view of having a solid lava flow come out on the surface. And so the first thing to remember is that the moon is not the Earth, and there's fundamental differences here. So we need to think about these when we think about the production of regolith on the surface of the moon. So on the Earth, we have a very large planet, okay? We have, in fact, very high overburden pressure because of that, high gravity, and indeed, we also have, this inhibits the exsolution of volatiles because of the high overburden pressure, and when the magma gets to the surface, it encounters an atmosphere, 1 bar atmosphere, and for both Plinian and Hawaiian types of eruptions, that collimates the plume significantly, okay? So that's what we see on the Earth, but the moon is not like the Earth because in fact, it's 1/6 gravity, it's a very small body, 1/4 the diameter of the Earth, and this has an effect on the depth and amount of volatiles that get exsolved and produced, so more and deeper. And then when it gets to the surface, there's no atmosphere, it's a vacuum. Instead of a collimated plume, it expands significantly into, in fact, an umbrella-shaped plume, exactly like what we see on Io, okay? So we really need to keep these things in mind. It produces an optically dense cloud here, which is very different than the kinds of things we see here. So let's press on and think a little bit about how we can solve that problem. What we tried to do was to forward model the formation of these lava flows, and we needed to do 2 things in order to make that happen. The first one was, in fact, to figure out the volatile generation and magma fragmentation as a function of depth. So in this paper in American Mineralogist, we put together kind of like the sequence of gas exsolution and formation as a function of depth as the magma is rising to the surface. And then we combine this together in a model for the lunar basaltic volcanic eruption structure and morphology, and to look at gas release patterns and sequential eruption phases. So in this particular situation, that's going to be nice. Okay, and in this particular situation, what we found out was that, in fact, we can divide these up into 4 phases. We have an eruption phase, 4 of them. Dike penetrates to the surface, phase 2, phase 3, and phase 4, and I'll go over those in a little bit of detail. We can look at the dike configuration, the surface eruption style, and also a whole host of features here, the magma rise speed, the phase duration, magma volume flux, and so on. So in the first phase, in fact, the dike is propagating to the surface from great depth. It penetrates to the surface, And the gas at the top of the dike and the foam at the top of the dike explosively decompresses. And this is kind of like an ultraplinian eruption. You get pyroclast, but not very much. Okay, the volume is small, and they go very widely distributed, tens of kilometers. And the transparent gas expands out into the onto the lunar surface as well. So that's over in like 3 minutes. It's not something you want to be standing next to when that eruption occurred. So the second phase, the dike is still rising, and this is actually 70% of the volume, but it doesn't last very long because the flux is really high. And what happens during this phase? This is the Hawaiian eruptive phase, and when we look at this, we find in fact that this is a period in which there's extremely efficient magma degassing in this particular phase. So this is a cross-section of the eruption. In this area here, as the magma comes to the surface, it explosively decompresses and expands, but it's coming out at such high rate that in fact, this is a very optically dense part of the cloud. And so the pyroclasts fall right back down onto the surface, and they're still liquidus temperatures. And so they actually thermally erode a crater here, a pit crater, and then the lava fills that and flows out. This is where we get essentially degassed lava coming out because it's losing most of its volatiles here, and it forms turbulent flows because of a very high flux that transition to laminar flows and then stop due to rheological or cooling limitations. Okay, so that's really interesting because it's a major phase, and when we now go to the fourth phase, this is also really interesting, the transition between the third and the fourth phase. This is the Strombolian phase. So the flux is decreasing as a function of time, 20 to 10, now 5 to 1, less than 1 meter per second. And so when we take a look at a cross section of that activity, in fact, this is when it changes to, okay, let me try that again.
This is one of the things you just I should.
Welcome to modern technology.
Yeah, what the hell? That, I believe the whole thing has quit. Okay, desktop 1. Okay, close the PowerPoint. Okay, so I got to go find that. Okay. Don't pay any attention to me here.
Ignore the man behind the curtain.
Yeah.
Your timer for 8 is about to go off, just so you're aware.
That's okay. We'll just do this.
Now we all see the secrets of Jim Head's hard drive.
Yeah, boy, it's a map of my mind. It's not a pretty sight. Okay, so we'll fast forward here a little bit. So basically, we're going on to this phase here. That's good. We'll go to full screen. Give me a video check. Okay?
Yep, we're good.
Okay. So the bottom line here is that basically the bubble rise rate exceeds the magma rise rate. So you go into Strombolian activity here. And then when we go to the next phase, which is the final phase here, basically, this is really interesting. And there are 4 parts of this. What's going on here is that the dike is decreasing in width because the elastic forces that propped it open are now closing. And so this produces, in fact, a situation in which magma is exsolving a hell of a lot of volatiles. And we can go through 4 phases here. That would be, so this one here where we extrude very vesicular magma, this can actually produce an autoregolith because the magma is so volatile rich that it explodes and produces maybe a 1 to 3 meter layer of regolith. So the bottom line is that the second one, you can actually get dike inflation, dike flow inflation from the dike, okay, and that, if you say, look here, in the same situation, that very vesicular magma can intrude into the dike, inflate the flow, and produce things like we see at the Apollo 15 site. A third one is summit pit craters, for example. If we go to summit pit crater, this volatile enhancement can actually produce a significant volatile-rich deposit, which can extrude out onto the surface, and we think this may be where these mounds come from and the Ina crater. And then finally, we have this fissure eruptions in which you can get the complete vertical sequence. So let me just say a couple of things. One of them is that the traditional view of basalt regolith is only one of a wide variety of regolith-protolith outcomes. We've mapped out 8 candidate regolith protoliths. So we have to think about these, and we need to think about them in the context of a variety of things: basal regolith substrate interfaces, We get a lot of different opportunities to have different substrates. Energy partitioning is going to be different from superposed craters. We're going to see a whole host of things here in terms of regolith growth rates, autoregolith formation. Regolith may start with 3 meters of regolith. Also, regolith thickness with age may vary because of these factors. And come in. And regolith components and maturation rates are critical as well. Those morphology of superposed craters, and finally, a couple of extra things here. The degradation of superposed craters, impact crater size frequency distribution may also be affected. And finally, despite all this diversity and complexity, the eruption phase parameter space really offers promise to unravel the eruption history of individual cross-section exposures and lava flows like we see here. This is why Laura Kerber's Moondiver mission was so critical, because we could have gone over to the side and measured all these things. So there's lots of promise to sort this out. And finally, we have tremendous amounts of opportunity with the data sets we have in hand to look at this, including remote sensing measurements that have already been made, assumptions about regolith thickness, and analyzing things like the Apollo, Luna, and Chang'e data on the lunar regolith. So I hope this is an introduction to sadly more complex, but potentially more interesting and documented. And this is going to tell us a lot about how regolith forms, but also we can use this to invert into an understanding of the basaltic lava flow and placement of processes on the moon too. So I hope this helps. Thanks.
Thank you, Jim, very much. We have time for maybe one question. Hannah really liked this was a great summary. I have a quick question I'm going to ask. How likely is it for the volatile components to have been trapped somewhere? Do we have a sample of these extrusion volatiles somewhere? Or is there a possibility that we could have that?
Absolutely. I think that the key point here is that, say, things like the Apollo 15 seep belt basalt are a good example of that. If you looked at, you saw that little inset of that sample, it's extremely vesicular in nature, and that is not the only Apollo 15 sample that looks that way. So one of the key points here is we've only been to a small number of sites. Apollo was great, but as everyone knows, it didn't go everywhere. And so one of the things we can do is use these predictions to find places which are close to the vent that have these different characteristics like INA, and go test these ideas and refine our views about these things. So our prediction would be that INA would be even more vesicular if we were able to sample it underneath the current regolith. So yeah, so that I think there's a lot of hope there, and we do see evidence for this type of activity in the existing samples.
Okay, we do need to move on. Thank you, Jim. Ben?
Awesome, yeah. So moving forward, we have Dr. Nandita Kumari, who is giving a presentation titled Different Trends of Variation in Christensen Feature on the Lunar Surface, Effects of Iron Content and Particle Size. You can feel free to take it away whenever you're ready.
Jim, you'll have to stop sharing your screen. So
yeah, I'm trying to find it. I'm trying to find a control for that.
I think it's, there you go.
There we go. Okay, what do I do here? Sorry, stop, just get rid of this. Yeah.
Just mute yourself and we can move forward.
Let me, I'm just trying to I don't know, share my screen right now.
Yeah, sure, okay.
Okay, give me a second. I don't know, it's just asking me to leave the meeting. I'm sorry about that. Okay, Deborah, I have kind of sent you an email because I was kind of, prepared for this, that if anything goes wrong. So you'll have my slides if you do not mind. Would you mind sharing them, I guess?
No, I don't. Let me go to my email and find them. They are not in my email.
Oh,
they're there. Okay. Okay, so give me a second and I'll put your slides up for you. Share screen. I'm just going to share your talk. Oh, now you're going to have me multitasking. We'll see how well I can do that. Can you? All right. Can everybody see her slides?
Yes, we can. This is great. Okay. Cool. I think I'll just start. So hi, I'm a grad student at Stony Brook University, so not a doctor yet, but yeah. Well, so I'm going to talk about variation in Christensen feature with respect to albedo on the moon next. So this is kind of the overview of the talk. I'm going to talk about a bit about CF, the factors that we know that affect CF, why am I doing this project, a bit about space weathering, variations in it, and then like, what have I done next, more or less. Next slide. So thermal infrared emission spectroscopy is like a very broadly used tool to identify silicates on airless bodies. So CF is the emissivity maxima in this regime. And it's an indicator of like silicate degree polymerization in a mineral. And so like it's a very useful tool for determining the bulk composition. These three lines that you see are the three brands of diviner instrument that I'm using for like doing my study. Around like band 3, 4, and 5, around 7.9, 8.2, and 8.5. Next. So we know that there are some factors that affect CF. And so prior to analyzing diviner data, we thought that CF, since it's at a longer wavelength, it will not be affected by any other factors, as the particularly the effects that we see in VNIR. But after analyzing diviner data, we came to know that space weathering, regolith compaction, and particle size, all of these affect CF. And just to like be more specific, an increase in compaction and space weathering leads to a redshift in CF, and like a decrease in particle size also leads to a redshift in CF. Next slide. I'm doing this project particularly because silicate minerals, they're like very abundant across the solar system, particularly on, across the solar system. And we use thermal infrared a lot for studying silicate minerals, particularly the bulk composition. It is very important to quantify the factors that influence CF for an accurate interpretation of the remote sensing data sets. It will not only have like use for our current data sets that we have, but also like a lot of upcoming data sets and ongoing missions, such as OSIRIS-REx, Baby Colombo, and Lunar Trailblazer. In data sets, I've used diviner CF data, band 3, 4, and 5, and like Kagua multiband imager. I'll be like going through the methods a bit in detail in a few like minutes. Next slide. So talking a bit about space weathering. So space weathering is a term that basically gives it's the cumulative effects of processes that is active on the materials in space environment. It leads to formation of agglutinates, glasses, and then like also leads to formation of nanophase metallic ions as a coating on the mineral surfaces. It also leads to like reddening of continuum in near IR region, and also like in decreasing of depth in visible region of the minerals, ion absorption depths. Next slide, please. So one thing to start with is like, is the space weathering same for all the minerals? They are not. So it is not. Why? Because so there's this study by Allen 1993, which states that he or she did the study on different minerals and found out that the amount of nanophase metallic ion particles that form are relatively different for different minerals. For instance, in synthetic glass, around 80% of original iron in the mineral structure got reduced to nanophase ion particles. It was 40% in case of olivine, and it was even less in case of enstatite, and like further reducing into like a lot less in augite. So these are like the red globules that you see on the surface are those nanophase metallic ion particles, and you can see them decreasing with the decrease in ion content of the mineral. Next slide, please. So space weathering leads to darkening of the surface. So this is a young crater, I think it's Dionysius, on the lunar surface. So you can see like it has a bright ray pattern around it, but like with time, it darkens. As you see, like the surface around it is relatively dark. It also leads to like a lot of pulverization and like breaking of rocks into fine regolith. So now we also know that space weathering affects CF, but like we are kind of going into look into detail, how does it, and like what all things do we need to look into to make sure that we are getting the bulk silicate composition correctly. Next slide, please. So to do this study, the ideal sites would be Copernican craters because they have a bright ray pattern around them, and also like they overlay on a relatively older surface. So they have like essentially the same silicate composition, but different albedos. Same is the case with soils. So soils have these bright patterns, and the most, I would say, like there are multiple hypotheses floating around in the community, but the one that is more prominent is that it's due to the magnetic shield soil regions. So yeah, you see these bright patches as you can see on the right. So I've taken these two sites like across the different locations, and these are the locations. These are the locations that I took across the lunar surface: the Highland craters, Highland soils, Mare craters, and Mare soils. Slide. Okay. So now Highlands. This is a Highland crater, Giordano Bruno, and here you can see like I've taken two locations with wavelengths, or like it leads to a redshift in CF, not reddening, but rather a redshift in CF. Next slide, please. With the decrease in albedo, not increase, with the decrease in albedo, as is like evident from the scatter plot and the histogram. Can we go to the next slide, please? The CF shifts to like longer wavelengths, essentially having the same bulk silicate composition, but still it shifts to longer wavelengths. Here I did it for like the dark lanes as well as the dark lanes, the bright spots, and the region nearby with relatively lower albedo. And you can see soil is like significantly shifted. So like basically this soil is a good example of showing that this shift is not like, you know, so let's look at the particle size effects. So here you can see craters in blue and the soils. So this is all the 23 locations, and you can see like essentially for the same albedo change, there has been like significantly different changes in CF. Craters have undergone more changes in CF compared to like soils, and this is because crater ejectas are essentially blockier, as in like they're larger in size, so it also like leads to breaking down. So there is a change in particle size that happens along with a change in the nanophase formation of along with the formation of nanophase metallic ion particles. So in craters, you are like the particle size variation is more prominent. So that is like kind of visible here, that, you know, essentially for having the same albedo change, craters have like more significant CF change compared to soils. Can we go to the next slide, please? So here it's like, since I selected the locations both on Mare and Highland, we see a different trend of CF variation in Highland and Mare. Now Mare are like more, like they basically consist of more mafic-rich minerals compared to Highlands, which are like more felsic. So here we see that, you know, essentially for like same CF variations, like comparable CF variations, the albedo changes in Highlands are a lot more compared to albedo changes in CF. So even for like, even if the, what I essentially want to say is like for the same amount of space weathering in Mare, the CF change will be significantly, like literally higher than that in Highlands. So yeah, next slide, please. Combining both of them, looking at the Highland craters, Mare craters, Highland soils, and Mare soils, we see that for like the craters again, in both Highland and Mare, we see that, as I said, like for the amount of same CF change, you see like a different amount of albedo change. And when you look at like the soil and crater comparison, the crater like for the same amount of albedo change, you see like CF of crater is like has changed more than the CF of soil. Conclusion and going forward. So first thing is like most of the corrections that have come for CF do not take into account the initial composition, the primary composition of iron in the mineral. So we need to take that into account to quantify these changes and also to explain these changes. So as I said, the increased variation is due to like presence of different minerals with different iron composition in these two locations. And going forward, it is like, so when we talk about the steady state, reaching steady state due to space weathering in VNIR, like the thing is there a definite amount of CF that needs to change after which it just stops changing, that we reach the steady state and it will not affect the CF changes anymore? So we have to like kind of look into that. Is there a definite amount, or like, you know, it varies with minerals? Also like quantify variation in CF due to like thermal gradient on the top few microns that builds up. And also understanding that the different factors that affect CF change, are they like additional, like for instance, does the CF change only due to space weathering add on to the CF change due to particle size and thermal gradient, or like how are they related to each other? Like yeah, so that is my talk. Thank you.
Thank you so much. Do we have questions? So I was not able to monitor the chat while doing that. But do we have any questions for Nadita? And forgive me if I mispronounced the name. So I have just a basic question. How are you proposing to take a look at these changes in CF and albedo to separate out, say, space weathering and particle size? Do you have a test in mind to separate the effects of those?
Yes. So me and Tim, my advisor, are kind of planning to do this laboratory work where like we are going to take the same sample of like different particle sizes and like kind of reduce them and then like see how much CF changes for the same particle size and also for the different particle size. Then like we can kind of do a comparison that was if it is same, then it is possibly like the same, essentially the same phenomena. But if it is different, it means that they might be adding up, like, you know, the particle size is also increasing it along with the space weathering. So it's like taking the same sample in different particle size and in the same particle size, reducing them and then like comparing the changes in CF. But that's essentially a lab that like we are planning to do sometime.
Oh, I can't wait for your results. Ben, we need to move on. Take it away.
Awesome. Yeah. So our next presenter is Dr. David Blewett, and he is presenting a talk on lunar swirls in the Mariah and Highlands near ultraviolet and near infrared space weathering trends. So David, feel free to take over whenever you're ready.
Okay, how's my audio?
I hear you.
Okay, and you can all see the screen?
Mm-hmm.
All right, well, that was a great lead in from Nandita. I'm going to continue to talk about space weathering, except here in the near UV and the near IR, again, talking about swirls. So space weathering. Well, as we know, rocks on the surface of airless bodies undergo a variety of changes as they're converted to soil. The optical changes are particularly profound. If you can see my cursor there, is illustrated here on the plot on the right, which shows lab reflectance spectra for a freshly crushed Apollo 15 Mare basalt and a mature soil of the same composition. And these optical changes are caused by accumulation of nanometer-sized metallic iron in the form of blebs and coatings on and within the soil particles. And this nano-sized iron is thought to be created during solar wind exposure and micrometeoroid bombardment, although the relative importance of these two agents is debated, and the relative fluxes of these change from place to place in the solar system, as well as place to place on the moon. So it's important to have a good handle on their effects. Now, magnetic anomalies. There are these magnetic regions of the lunar crust, and they provide really unique environments for investigation of a wide variety of questions in lunar and planetary science. The presence of a magnetic field attenuates the flux of solar wind ions that can get down to the ground to some degree, but the micrometeoroids are unaffected. So what you have at a magnetic anomaly is a natural space weathering experiment with a control on one of the variables. And as it happens, and as we heard in the previous talk, many magnetic anomalies correspond to these peculiar albedo markings called lunar swirls. Probably the most famous of which is Reiner Gamma, and maybe you all voted for that in Deborah's poll at the beginning of the session. So the goal of my work is to help gain an improved understanding of this optical space weathering on the moon and its causes, through a combined analysis of swirls in these two wavelength regimes. But before we go to the moon and look at the remote data, it's helpful to have a framework for interpreting what we'll see, and that can come from laboratory spectra for Apollo rocks and soils. So I'll be talking about two spectral parameters, the near-infrared reflectance ratio at wavelengths of about 1550 and 750 nanometers. This is a measure of the near IR continuum slope, as you can see here in the middle plot, where the continuum slope increases for more mature materials. And then this near UV ratio of 321 over 415 shown here. That is a steeper slope in fresher materials, and this is related to the strength of an oxygen metal charge transfer absorption that extends into the ultraviolet. So we can plot up these parameters, these ratios, and look at how they vary with reflectance for the different lunar samples and with the I sub s over FEO maturity parameter, which is the ferromagnetic resonance parameter index that is related to the abundance of single domain iron. And I've divided up the lunar samples into these four categories: low and high titanium Mari samples, and then two in the highlands, depending on the iron abundance. Now, another really valuable resource for helping to understand space weathering are these silica gels that were created by Sarah Noble and her collaborators. What these are transparent media that which are impregnated with nano-sized iron particles of different sizes and different abundances. So this lets us look at the spectral effects of those two factors. And so what I've done here, the two plots on the right, are I took the data that was this reflectance spectra for all these samples that were published by Sarah Noble, and converted them into these ratio reflectance plots for in the near UV part of the spectrum and the near IR parameter that I'm looking at. And this allows us to see the differences for the different size and the different abundances of these particles. All right, now onto the spacecraft data. Somewhat similar to what you saw in the previous talk, we have image data for a number of lunar swirls for the near UV. We have the LROC WAC data, and I'm using the Kaguya multiband imager for the near IR. And so at each location, we define regions of interest, different parts of the swirl, the dark lane, background material. And this has been done for 3 swirls in the Maria and 3 in the highlands. So by extracting those pixel values from the images, we can create ratio reflectance scatter plots for the two different parameters. And what these allow us to see are just how are these materials, different surfaces, related to each other in these spectral spaces, from the bright swirl, edges of the swirl, dark lanes, background, and can do things like doing fits within each point cloud for a particular surface type. This lets us understand what's kind of going on within each type of material. I'm not going to talk more about that today, but that's something that's of interest. And in the interest of time, I'm just going to skip to some of the observations. One is that we don't see evidence for over-maturation in the dark lanes at the swirl, at least for the swirls we've examined. The idea here is that in the process of shielding the surface from the solar wind, the magnetic field may actually be channeling or focusing the solar wind into higher concentrated or higher fluxes in certain areas, perhaps those dark lanes that that wind through the sinuous parts of so many swirls. If that were the case, you might expect that material will becoming kind of super mature, even darker and redder than the normal background, in which case you might think it would plot up here at a very low reflectance and a high reddish ratio. But we don't see that. The dark lanes generally seem to be transitional between less mature materials and the background. Of course, overmaturation could be taking place on local scales, depending on what we expect to be the very complicated and the very complicated nature of the magnetic field actually down on the surface. All right, so looking again at the comparisons with the Apollo samples, it appears that the swirl materials contain abundances of nanosized iron that correspond to what the sample workers call immature or submature soils. So it's clear that the bright swirls are different from normal fresh material. And we see that here in this plot, which is this UV ratio and the reflectance, where each Apollo sample has been labeled with its I/S/FeO value. And then we see two of our other popularity swirl contestants, the Highland swirl at Gerasimovich and its nearby background. And then here's the Maury swirl at Ingenii and its Maury background. And just from looking at the relative locations of these things with respect to the freshest samples and to each other, it's clear that the bright swirl material doesn't represent, pristine, fully immature material. Now, noticing that the smaller size range of nanophase iron has the strongest effects in the near UV, as you can see from the red and blue plots here. We infer that it's a deficit in the smallest size range that's primarily responsible for the character of the swirls. And this fits with a conclusion from David Trang and Paul Lucy, who made maps of nanophase iron abundance based on their radiative transfer modeling work. And they saw that the bright portions of swirls have lower abundances of nanophase iron. So if that's the case, then because magnetic anomalies reduce the flux of solar wind ions that reaches the surface, it would follow then that solar wind exposure is chiefly responsible for this production of the smaller size particles in normal space weathering. And then kind of as the corollary to that, micrometeoroid melting and vaporization, which takes place unimpeded in swirls as well as going on in normal non-magnetic areas, that must be the chief producer of the larger iron particles. And I think that is my last slide. I'm just going to stop there and just leave you with a gallery of Maury and Highland swirls. I didn't know Deborah was going to be taking that poll, but there's some of the contestants. So thanks.
Sorry about that, I was muted. Thank you, Dave. That was actually really interesting. We have time for one question. Tim Glotch did make a comment that I would like to echo. It's that your lack of evidence for near IR dark lane overmaturation was consistent with what Nandita just presented. And I agree with him. It's nice when you approach things from different angles and you get similar results, things that are consistent. We are about out of time. Ben, you want to take it away?
Yeah, that sounds good. So our next presenter is actually going to be Deborah Domingue, doing her talk on regolith structural characterization of lunar swirls within Mare Inge. And I do apologize, but I don't have the same bell sound as you, so your timer is going to be a little bit different sounding.
That's okay. I will try to respect the time. So I'm assuming people could see my slides, yes?
Yes.
Okay, so let's see. So this is a project I've done with several of my colleagues at PSI, and we're taking a look at the structural characteristics of on versus off swirl. The goal is, can we see evidence for structural differences? Are they more consistent with the space weathering hypothesis that Dave described? There's another idea for their formation that involves dust levitation. Is it more consistent with that, or is it a bit of both? The methods we applied, we did topography using stereophotoclinometry. And this is a method that's used for spacecraft navigation to identify landmarks. It has the ability to get very high topographic and therefore incident emission phase angle information on a pixel by pixel level for the images we used. We applied a photometric model. I'm one of Bruce Hapke's students, so guess which model I applied. So we looked to basically see, do we get the same values on swirl as off swirl? And can we correlate the modeling results with structural characteristics? So here's my story. Why is it important? You know, we really do want to have an understanding of how these features form. Dust is everywhere. One of the things for going back to the moon is, how do we deal with that? And what kind of mobility does it have? Because we're going to have to design our habitats, our equipment, our protective gear for our people with that in mind. It is one of those environmental issues that we're going to need to deal with. And what can the structure of the regolith tell us about these features that the spectroscopy hasn't already told us? So what are the relative roles of these two processes? So I already mentioned this. We use stereophotoclinometry to co-register images and to provide a high fidelity and a high spatial resolution for our topography, which in turn means we can derive the photometric angles, the changes in incident emission due to topography. And that is very time inclusive and time intensive. So instead of doing the whole mare, we took a look at this little swirl here, this little tail within Mare Engine. And one of the things when you do a photometric study is you look at the quality of the data. And what I mean in terms of quality of the data is, does it cover enough of the incident emission and phase angle space to be able to constrain the parameters? Is this going to be able to give you viable solutions? And this is a data quality map of our region. Green is great, blue is good, red is eh. That's what you need to take away from this slide. And basically what it does, how we determined that is we looked at how many bins of angle range. So for every degree of incident emission, did I have data in that bin? And out of all the bins that I could have, how many bins did I cover? So it's a simplistic way of looking at the coverage. Oh, great. My slide now doesn't want to work. Okay. So we used Hapke's model, and for anybody who lives, eats, and breathes photometry, there are pros and cons to Bruce's model. There are others out there that can be used to characterize the surface. But what this one does is it allows us to compare one region to another, and it allows us to correlate parameters with surface properties. This particular model is based on radiative transfer. The different components of the model are correlated to or derived from physical mechanisms, physical processes, scattering processes. So there is minimum a theoretical correlation between the parameters and different physical properties. In the lab, we've shown that the parameters aren't uniquely just this property and this property alone. So when we interpret their values, we keep in mind what the laboratory tests have shown us, that different physical structures can impact the parameter values. So you need to keep those in the back of your mind. We just did a simplest approach, least squares grid search. We varied all the parameters simultaneously. And these are our results. Yay! What am I looking at? All right. So going from left to right, what we have is a map of the single scattering albedo, a map of the phase function, the scattering function, and then a map of the surface roughness. Right. So I'm going to go through each of these in order. So in the lower right-hand corner, you see an albedo map of the swirl region. And if you can see my cursor, here's the nice little curly Q tail that we were looking at. This is on swirl. Oops, nope. And this is off swirl. And you can see, despite all the different data quality regions, and they do map, you can see the swirl in the single scattering albedo map. Once again, if you look at the scattering function, however, you see it in the albedo, this is where it is. We do not see the swirl being brought out in the value of the scattering function parameter. So this tells us no correlation. The particle scattering function is correlated to particle structures and interparticle relationships. And we're not seeing variations between on swirl and off swirl here. Surface roughness, once again, we should see our little curly Q here, and we don't. So there's no variations in what I call granular topography. Surface roughness as defined within this model correlates to the optically active portion of the regolith. So we're talking about a few microns deep here. So we're talking about on the order of millimeters at most. So we're looking at how the topography on the grain level. So once again, no correlation. So I'm going to summarize here real quick what we think in terms of expectations for space weathering versus expectations from dust levitation. And to me, this would make a good discussion. We see variations in the single scattering albedo, and we would expect that whether it's from space weathering or from dust levitation. The dust levitation model, since that has not been discussed too much, supposes that we have a fine-grained feldspatic portion that is preferentially placed in the bright swirl region. So feldspar is brighter than is the brightest portion of the regolith. So that's why we would see the correlation with single scattering albedo. The scattering function variations, we would expect to see differences in grain structure from space weathering. We expect to pick up radiation damage in the grain structure, but we don't see it correlated here. So that's why we have the red X under for space weathering. We don't expect too much difference in grain structures between on swirl and off swirl with the dust levitation model. And as far as surface roughness, we don't expect the space weathering to change the surface roughness, but we would expect it to see it in dust levitation because you would have a finer grain component being overlain on the topography of the coarser grains. So we have some pros for both and some cons for both hypotheses. But once again, we only took a look at a little area. So our next step here is to go and take a look at a larger area, one that shows more dynamic variations in albedo. And stay tuned. We've just finished building the topography for this region, and now I just need to run it through the photometric model. And hopefully within a month or so, we will be able to compare and contrast those two regions and see if they tell us the same story.
Oh, right. You are just about out of time, but we do have time. We have time for a couple questions. We have a couple minutes left.
All right.
So does anybody have any questions?
Okay, so I can't see the chat box with my when I share slides, so I'm going to stop sharing.
I can read you the questions as well.
Okay. Okay.
Paul Sanchez asks, "What do you mean by granular topography?"
Okay, so most people, when they think of topography, they think of, okay, I'm going up on this ridge and I'm down and I'm flat here, and oh, here's the topography of a crater. That's large scale. When I talk about granular topography, think about I have this rock here and I have this rock here. Now all of a sudden I have this kind of topography. So it's small scale topography. Does that make sense? So that when I say granular topography, that's the kind of thing I'm talking about. I'm talking the roughness that the particles themselves create on the surface. So when let's say this is my rock A, rock B, or grain A and grain B. If I've got a fine grain, so I have this kind of roughness. If I have a piece of fine grain dust come in and sit in over here, it's going to even out this topography. So that's why I had expected, if dust levitation was playing this big role, I would have seen a change in roughness.
Okay, so Paul said yes, but that requires a very high resolution. And do you have that kind of data?
Okay, so if you
we'll
look,
have about 1 minute left.
Okay, all right, so I'll try to answer this real quick. So when you look at the derivation of the roughness parameter in the model, the roughness parameter is basically an average from the footprint size of your detector down to the particle scale. And Paul Helfenstein took a look at some of the Apollo images to try to say, okay, at what scale are we really talking about when we look at this Hapke roughness parameter? And he determined it was probably the centimeter scale centimeter to millimeter scale was dominating the roughness that this parameter referred to. Does that answer your question? So we're thinking we're being dominated by millimeters to centimeter scales here with our data set.
Okay, Paul says yes, that does answer the question. And there are quite a few other questions, but we are out of time. So if anyone has extra questions, I believe you could email if that's all right with you.
That's great if you could, because I won't have time to answer them in the chat, because I do want to pay attention to the talks in this session as one of the co-chairs. So, but I want to say thank you for the interest.
All right, then we are going to move on to Dr. Andrew Jordan, who is doing a talk on observational evidence for dielectric breakdown weathering on the moon. Dr. Jordan, feel free to take over whenever you're ready.
All right, can you hear me?
Yes, I can hear you.
And can you see my slide?
Mm-hmm.
Okay, great, thanks. So this is work that's been supported by LRO Crater and Survey's LEADER team. And that's an old picture of me, but I chose it because it's from a Lunar Science Forum many years ago. And I really liked the lanyard back then. We've had some great talks on space weathering, and the current view is that mainly micrometeoroids and the solar wind dominate space weathering, and it's a bit of a discussion as to which one's more important. For the past few years, I've been arguing that another space weathering process is going on the moon called dielectric breakdown. And what happens is during large solar storms like coronal mass ejections or solar flares, these magnetic events accelerate particles to high energies. These are called solar energetic particles, or SEPs. And these SEPs can cause deep dielectric charging in cold soil on the moon. So by cold, I mean less than about 100 or so Kelvin. and that's in permanently shadowed regions on the night side of the moon. And SEPs don't follow lines of sight from the sun like the solar wind does, or like an electromagnetic radiation. Some of them have really large gyro radii, so they can hit the night side of the moon. They scatter off the magnetic irregularities in the magnetic field, in the heliospheric magnetic field. So observations from Crater, from Lunar Prospector have shown that SEPs can hit the night side of the moon. And during really large events, they can charge the soil to the point where the electric field in the top millimeter or so causes dielectric breakdown, or you can think of it as sparking or lunar lightning, I guess, but just really small. And you get rapid melting, vaporization. And in our 2019 paper, we predicted that dielectric breakdown weathering should be comparable to micrometeoroid weathering. And in that paper, we predicted a latitude profile for the energy flux of breakdown weathering into the lunar soil in terms of joules per meter squared per year. You can see it varies, it increases by about 20% from the equator to the pole. And in that paper, we used the Grunedal 1985 mass flux and Santala's velocity to calculate an energy flux for the micrometeoroids. And since then, I've combined that with a latitudinal distribution that Gallant et al. Found. So that's a cosine of latitude function that decreases by 10% from the equator to the pole. And so you can see the micrometeoroids seem to be contributing more weathering, more melting and vaporizing than does breakdown on a global scale. But because both of these processes are melting and vaporizing, it seems reasonable to add the two together to get a net profile for this. And what you see is here in the bottom plot, the weathering profile is roughly constant from the equator up to about 40 or so degrees. And then it starts rolling over and becomes more and more like the cosine of latitude at higher latitudes. And I'm not showing the solar wind on this because its energy flux is a few orders of magnitude higher than this. So you wouldn't see any of those variations. So now I'm going to compare this to the reflectance profile of the Maria. And I'm focusing on the Maria because the latitudinal trends are clear there. They've been studied in more detail. Hemingway et al. In 2015 did one of the studies, and I'm showing data from that paper. On the left is the Maria reflectance at 750 nanometers, and on the right is the reflectance at 1064 nanometers. I'm showing the 1 sigma there. And if you just take that weathering profile from the previous page, the bottom plot there, and just fit it to the data, I just fit it at, or set it equal to the data at the equator and at 60 degrees latitude using the equation on the upper left-hand corner. I just take breakdown plus micrometeoroid energy flux, multiply it by a negative constant, and that just flips the sign, and then add another constant. And then you get the fits that you see here. And the reflectance data show a similar trend as the modeled reflectance, where both of them are flat out to about 40, latitude 40 degrees, and then it starts increasing rapidly at higher latitudes. Now, if the solar wind were dominating weathering, you'd expect the reflectance data to follow a cosine of latitude trend. And that's what this dotted line is here. And the cosine of latitude trend does not seem to fit the data. And so it seems like the Maria reflectance can be best explained by this combination of dielectric breakdown and micrometeoroid weathering. And we've been talking quite a bit about swirls, and I really enjoyed the previous two talks. It's given me a bit to think about. Here I'm just going to talk a little bit about Reiner Gamma, which I did vote for. It has a magnetic field strength of about 20 nanotesla at an altitude of 30 kilometers. Now this is fairly weak if you're an SEP particle, so most SEPs can penetrate right to the surface. So all SEP protons and the energetic electrons have energies, gyro radii, that are large enough to make it to the surface. I'm just using a simple gyro radius argument. Lower energy SCP electrons, so on the order of 10 keV and lower, they can be reflected or shielded out by the magnetic field. So we'd expect breakdown weathering to be reduced in a swirl. And just for some context, the solar wind is reduced by about 80% at the surface by this magnetic field. So we'd expect breakdown weathering to be reduced by quite a bit less than that because we're talking about more energetic particles. So let's go back to the data. So there again, you see the reflectance of the Maria with latitude, and then that star shows where Reiner gamma is at a reflectance of about 0.15. And then there's the fit of the model to the reflectance. And then if I decrease breakdown weathering by just 3%, that's more than enough to explain the brightness of Reiner gamma. And 3% is, as it should be, a whole lot less than 80% shielding that you get of solar wind. So just reducing breakdown weathering by a little bit, which is what you'd expect, given how energetic these particles are, seems like you can explain the brightness of Reiner gamma. Now, some of you are probably thinking, well, how can you argue that the solar wind doesn't cause any weathering? There's been about 60 years worth of experiments saying that it does. And I can't go into detail about this. This is a paper that's in preparation, but I wanted to make one point about that. In order to keep laboratory timescales reasonable, these studies have to use really high fluences of particles. So the ones that I've reviewed are all 10 to the 14 to 10 to the 20. I think I've even seen one up to 10 to the 21 charged particles per centimeter squared. But dielectric breakdown in most solid dielectrics, which includes things like lunar soil and simulant, only needs 10 to the 10 charged particles per centimeter squared. So these experiments are exceeding the threshold needed for dielectric breakdown by 4 to 10 orders of magnitude. And the solar wind can't cause this kind of charging because it's hitting the day side of the moon, where the soil is a lot warmer, so the electrical conductivity is a lot higher, and it can dissipate that charging. So it seems like these experiments might actually be not so much a simulation of solar wind weathering, but they might actually be a better proxy for breakdown weathering. But stay tuned, hopefully I'll be able to talk more about that at a later date. So to summarize, the Maria reflectance shows a fairly level trend from about 0 from the equator to about 40 degrees, and then it increases rapidly. And it doesn't seem to follow a cosine of latitude trend. So it doesn't seem that the solar wind dominates. Whereas the breakdown plus micrometeoroid trend, based on the work that we did in 2019, does have that region of level weathering or constant weathering from the equator to about 40 degrees. And then it increases rapidly after this. So I'm proposing that maybe it's micrometeoroids and dielectric breakdown that are dominating weathering in the Maria, and the solar wind might play a minor role. So thank you, and I'll take any questions. You can also email me questions if you want.
Okay, that is fascinating. I'm going to take a host prerogative, and I'm going to ask you a question. So I see that nice plot of yours, and is this lunar specific, or can you apply it to Mercury?
Oh,
you've got another
man,
2 minutes.
Yeah. Mercury does have a magnetic field. So this might play a role near the poles, near the cusp regions, where these SCP particles can get in. I don't know about lower latitudes.
So if someone were to send you, for example, flux to the surface as a function of time for Mercury, could you say where this dielectric breakdown would be probable or a process to consider, and where it would not be effective?
Yeah, definitely.
Okay, so I'll be in touch then.
Sounds good.
Okay, so we do have another question. let's see, what kind of subsurface geologic feature would it take to explain the magnetic field lines? And how deep would they have to be buried?
Oh, that's above my pay grade. I'm a particle guy. I'm not a geophysics guy.
Okay. Fair enough. Okay, so with that, I think we'll move on. Ben, you've got it.
All right, yeah. So our next presenter is going to be Licia Yeo, doing a talk on triboelectric charging of lunar dust by rover wheels. So Licia, go ahead and take over whenever you're ready.
Yeah. Is my screen visible?
Yep, I can see it, and we can hear you.
Great. Okay, so my name is Licia, and I work at the University of Colorado with Mihai and Shu. And this work that I'm about to present was done in collaboration with Edita from UCF and George Grost and Joseph Minafra from the Ames Research Center. So as everyone by now in the session should know, the surface of the moon is covered with a layer of fine dust called the regolith. And this dust, as Deborah mentioned, I think 2 talks ago, it's a key challenge for landed missions and long-term human habitats. It's a human health hazard, especially when it is inhaled, and it can clog mechanical joints, obscure sensors, solar panels. It can cling to equipment, and if it does so, it poses the risk of electrostatic discharge. So I've included here a picture of the Apollo 17 astronaut, Harrison Schmitt, and you can see his spacesuit is almost entirely coated in lunar dust during his field investigations. I also want to give a bit of quick context about the lunar plasma environment before I delve into the specifics of dust charging. I think yesterday Bill Farrell gave quite a good talk related to this topic, so I'll be brief. We know that UV radiation and solar wind help make up the lunar plasma environment, which then go on to charge the dust grains on the lunar surface. And on the day side, for instance, photoelectrons dominate any dust charging processes that take place, but on the night side, the surface potential can be up to tens or even hundreds of volts because the solar wind electrons fill in the wake ahead of the solar wind ions. And then on top of that, we have local topographies like craters that alter the solar wind flow. So all these natural processes go on to affect the charging of the dust on the moon. But what I would like to focus on is triboelectric charging. And this occurs when 2 materials rub against each other. And what happens is they're going to transfer charge between them. So if you've ever removed a sweater and you felt that static electricity build up, or you rub your hair against a balloon, you've had firsthand experience with triboelectricity. So the amount of charge that's transferred depends on the type of materials being rubbed together, how vigorous or long that rubbing is, as well as the specific surface properties of the materials in question. And previous work by Gross, Sharma, Sikafou, Stanovsky, they focused on triboelectric charging of dust with various materials as they interacted with plates and beads and so on. But this work in particular focuses on the interaction between rover wheels and dust. So I've included here a couple of screen grabs of the Apollo 16 mission, and we can see that dust is kicked up in copious amounts by the rover, which then begs the question, well, how much charge is being exchanged between the dust and the rover? And as we return to the moon, knowing the answer to how the dust and wheels interact with each other electrically is going to become more and more important. So in 2005, Jackson et al., they modeled the charge on wheels as they interacted with dust. But in the next couple of slides, I'm going to present some experimental work on the triboelectric charging of the dust itself. Okay, here is our experimental setup. It's simple and direct, and it was designed in collaboration with the NASA Ames Research Center. And it just measures the amount of dust charge on wheels. The amount of charge on dust that has been kicked up by a rover wheel. And it's the first of its kind, and it's very straightforward. We have a rover wheel, it's spinning on a bit of dust, and it's kicking up this dust that is then collected into a charge detector. It's also known as a Faraday cup. And here's a picture of our little rover that we used at the dust bit. So after this initial proof of concept work was done at the Ames dust bit facility, I went back to Colorado and I constructed a similar setup, this time with just a single wheel that spins on an axis. And it allows me to change the wheel speeds as well as the material on the wheel and the type of dust being investigated. So these three variables are going to be explored in the slides to come. So before we go into that, let's see if this works. Just our rover wheel in action, kicking up dust into our detector. And the graphs on the right represent the charge signal events. So the initial rising peak, let's see, well, it's fairly obvious. The initial rising peak is proportional to the amount of charge that's on the dust. And then this can easily be calibrated by inputting known charges into our Faraday cup, which we did. And the rest of the curve, as it falls and rises again, is characteristics of the internal circuitry of our system. There we go. So without further ado, here are some results. The graph on the right shows the charge distributions that were measured out of different dust simulants as they interacted with a rubber wheel. So on the x-axis, it's the dust charge in picocoulombs, and the y shows the relative frequency with which we measure these charges. So we can see right off the bat that the dust charge that we measured is overwhelmingly positive, which is good news in a way because it shows that what we are measuring is interaction between a rubber wheel and the dust. So if what we were going to see is dust-dust interactions, then I think I would expect an equal distribution of positive and negative charges. But because rubber is extremely electronegative, it loves to collect electrons. And this leaves the dust particles that it interacts with positively charged. And that's exactly what we're seeing. Another obvious difference that we are noticing here is that when we use different dust simulants, the charge distributions are pretty different. So in the first row, GSE-1A, that's a commonly known LUNAR simulant, then it's a Martian dust simulant, and the final row is the asteroid simulant. Yeah. And finally, I also want to point out that in some cases, the maximum charges that we are measuring on these dust grains can be up to, hundreds of volts. So another variable that I found that changes the dust distribution, charge distribution, is the wheel speed. So here is some data that shows two different dust simulants, each interacting with the same rubber wheel, but at different speeds. So each of these graphs represents somewhere between 2 and 400 data points. And intuitively, you might expect that a higher wheel speed would lead to a more positive charge distribution. But at least in this case, for this set of rubber wheels, we instead measure a slight negative shift in charges at higher wheel speeds. And the reason why this might be, I suspect, is that as I was taking this data, I noticed that there was an increased amount of dust sticking to the wheels at higher wheel speeds, which leads me to suspect that more dust-dust interaction is taking place. If you recall, I think in the previous slide, I mentioned that if the triboelectric charging interaction was purely between dust and dust, then I would get an even distribution around zero charge. So this amount of dust that's being stuck to the wheel is something that can be quantified, and it's on the top of my list of tasks once I manage to get back into the lab and actually get more data. And a final observation that I like to share with you is the difference in charging when the wheel material is varied. So here we compare rubber and PVC wheels with the same dust simulant, and notice how for the rubber wheels there's a much larger variation in charge. Larger variation in charge that we're measuring. So how can we use this knowledge to plan future rover-based missions? we know now that the charging effect is significant and that it depends on the type of dust that the rover is traveling on, but also what wheels it has and how fast it's going. On top of that, there are a few other factors that we should be careful about. For instance, in the absence of sunlight, we expect the dust to stay charged longer because there's no plasma to help dissipate the charge. But well, and so this means that if we were to set up a lunar base in a permanently shadowed region, then this effect is something we're going to have to be extra cautious about. And this bit of research also lets us start to maybe think about recommending a range of safe speeds for rovers, depending on where they are and what the tolerance of the equipment around it is. And also note that as the wheels are charging dust, the wheels themselves are also simultaneously being charged back in the opposite polarity by the dust. So this effect can be used to measure the triboelectric charging of the dust in situ by including electrometers, for instance, attached to the wheels. And finally, I'd like to just share once more some of the next steps I'm excited to take, measuring dust adhesion versus the wheel speed. And something that I also want to look into is whether dust is clumping as it enters the dust detector. There are a couple of papers out there that predict that this will happen for certain kinds of dust, so I'd like to look into that. And maybe one day we can start to build a repository of information depending on dust type and wheel materials so that we can be better prepared for any sort of mission planning. And that is it for me. Thank you.
I want to thank you so much. That is very, we have a time for a few minutes, for questions for a few minutes. We have one submitted by Alex Hobbs. He said, you said that max charges on dust grains are equivalent to hundreds of volts. How are you defining a grain with respect to size mass?
That was done as an estimate. So we have a distribution of dust sizes and we know the density of that. So yeah, so we know the dust size, and therefore as an estimate, we just took the voltage, we assume it was a sphere and calculated. Yeah.
Okay. So Micah, I'm not going to even try the last name because I don't want to mispronounce it. He asks, is there any time dependence of the dust charge signal, or is every touch of the wheel statistically similar?
That is a great question, and something we are also hoping to look into. So these experiments were done at atmospheric pressure, but we know that there is moisture in the air, for instance. So the charges are going to change over time. And something we're hoping to be able to do is repeat this in a vacuum chamber so that we are more sure of the charges on the dust. So yes, that's a really great point.
Okay, you have check the chat. You have one or two more questions, but we do have to move on. So Ben, take it away.
Yeah, sounds good. So moving forward, Dr. Philip Metzger is going to give a presentation on quantifying engine exhaust ejecta from landing large spacecraft on the moon. So Philip, feel free to take over the screen whenever you are ready.
Okay, let's see if this works. Do you see my charts?
Yep, I can see your screen and we hear you just fine.
Awesome. Okay, I'm going to be talking about quantifying engine exhaust when a large lander lands on the moon. This is based on about 20 years of research. It's going to be an extremely top level overview. So the phenomena when you look at a landing like an Apollo lunar module, these are images looking out the window from one of the lunar module landings. The primary phenomenon is that the rocket exhaust is scouring the surface and blowing ejecta particles away as a dispersed flow. However, at the very end of the landing, we did see bursts of dense clods of material, large clumps of material blowing out en masse. So we know that scouring the surface is not the only phenomenon that occurred, even with a lander about 8 tons like the lunar module. So when you go to larger landers, like a 40-ton human landing system, there may be deeper cratering phenomena. But because we have to peel this onion away one layer at a time, this talk is going to focus just on the scouring phenomena and try to quantify that. We do also see rocks blowing during the lunar landings. In Apollo, there's a rock that's the size of your fist going 60 miles per hour. We have evidence about the damage that this can cause from Apollo 12. The lunar module landed 160 meters away from the old Surveyor 3 spacecraft. The astronauts cut pieces off like that camera you see in the middle, and then the right-hand picture is the bottom section of the camera. Coupons were cut out. I had several of those coupons in my lab for several years. We had a team of people analyzing them. For example, the left is the paint as it was protected underneath a washer, and the right shows the paint after it was sandblasted by the Apollo lunar module. And there's lunar soil mixed all in the paint. There's a crack you can see running through the paint. Those cracks look like a dried mud cracking pattern. A lot of the junctures where the cracks meet, there are cylinders where a lunar sand-sized particle was embedded into the paint. This is a laser scan on the right. It's inside out, but it shows one of the pits where a sand particle penetrated into the paint, and these ridges running away from it are the cracks that radiated away from the pitting. Now, the damage was pretty extensive, but it would have been 1,000 times worse if the Surveyor had been 1 meter higher. It was down in a crater, and most of the ejecta went right over it. So only about 1 part out of 1,000 that was scattering out of the sheet actually hit the Surveyor. Nevertheless, it was complete coverage. This is a shadow that was etched into the Surveyor by the sandblasting. It's the shadow of a bolt that was here that has been removed. And you can see by the completeness of the shadow that it was a complete scouring of the entire spacecraft. And also there's no penumbra. That gives us information about the particle scattering. Okay, so now this is more recent work. This is a video that I just completed with Jim Mantovani at the Kennedy Space Center. This is the result of a 40-ton lander landing on the moon. This light circle is the moon. You're going to see the ejecta blowing out. This is faster than real. It takes, in real life, it takes about an hour for the ejecta to go all the way around the moon. But you can see the ejecta does blow globally on the moon. It deposits all over the entire globe, and it continues to rain in for weeks after a 40-ton lander lands on the moon. This is zoomed out, the same simulation. There's the moon. This dotted ellipse is the orbit of the proposed lunar orbital gateway. And so you can see the ejector from a 40-ton lander will blow completely off the moon. It wraps around the moon. This is a cross section. If you want to see the 3-dimensional figure, you would rotate it around the center axis, and that would be the shape of the ejecta cone. But this, I'm going to stop it right here. This is several hours later, and the lunar orbital gateway, if it passes through this point, we were estimating it would sustain about 10,000 impacts per square meter at hypervelocity. These are particles 10 microns and smaller that reach to that altitude. Now, when we try to calculate how much erosion would actually occur, we spent a lot of time analyzing the imagery under the lander. You can see evidence of the erosion, like this is a headed erosional remnant. The erosion is actually more about a meter away from the nozzle because the shear stress is higher there. You can see these strata in the lunar soil where there was a mechanical discontinuity between the layers, and it was eroding, and it stair-stepped down, moving away from the nozzle. And so when you factor all of these features and add it up, it looks like about 1 ton or 2 of regolith was blown away. We did a lot of experimental work trying to quantify the erosion rate, including about 450 parabolas in lunar gravity in a reduced gravity aircraft. We did vacuum chamber testing out at NASA Ames. We did testing on volcanoes in the natural tephra. And the end result of all the experimental work is this equation. This says that the erosion rate in kilograms per square meter per second is proportional to the shear stress that the gas puts on the soil divided by a bunch of soil parameters, the density, the gravity, the cohesion. And if you lump all the soil and environmental parameters together, it turns out it's equal to an environmental factor times the shear stress. So if you do these simulations of the landing, you should be able to integrate over the shear stress everywhere and calculate the total erosion. When we do that, it comes out with an answer that's 10 times too high. So something was wrong. We went back and we did more analysis on the landing videos. We invented a method of looking at synthetically adding dust or subtracting dust from the images to create the haziness that we can match from frame to frame. And when we used this method, we came up with a different answer. It told us that the shear stress to the 2.5 power is the erosion rate. So how do we reconcile these? By the way, when we did this method, it predicted 2.6 tons of soil were blown, and that is about right. So I believe this method that was based on the empirical data. Something's wrong with the terrestrial experiments. Well, here's a clue. When we did these experiments out at NASA Ames, if we kept the shear stress constant, but we made the gas increasingly rarefied, as it gets more rarefied, the erosion rate increases. And this is an effect that only shows up when the gas is very, very rarefied. So the erosion rate starts increasing as it gets more rarefied, approaching lunar vacuum. I'll explain this curve in a moment. Now, this is important because a 5-ton lander or an 8-ton lander like the lunar module is in free molecular and transitional flow all the way down, whereas the gas under a 40-ton lander will transition into continuum flow regime. So if there's a transition in the physics, it will make a difference with these larger landers. Now, this is the simplest possible model. When we put all the empirical data together, you end up with a surface that looks like this. The x-axis is the rarefaction, the Knudsen number. The axis back into the page is the shear stress locally on the soil, and the vertical axis is the resulting erosion rate. The left side is continuum flow, matches our experiments. The right side is vacuum conditions. These darker lines are where we took data. You can see there are big areas where we don't have any empirical data. And so this simplest model may not be telling the whole story, but this is what we have so far. If you look at a 40-ton lander, it laps over into these regions that we've never measured before. And when you look at a small CLIPS lander, a very small lander, it's down in the same region that the lunar module was operating. So when we integrate this equation over the landing trajectories of different size landers, the empirical result is that erosion scales as the mass of the lander to the 1.77 power. It's not as bad as we previously thought, but it is still faster than linear. And so here's the answer. If you have a 40-ton lander landing on the moon, it looks like, to the best of our knowledge today, it's going to blow about 98 tons of soil, which is enough soil hard packed to fill an entire kitchen. And so that would cause, we think, about 2,000 hypervelocity impacts every time the lunar orbiter gateway flies through the ejecta sheet, which is twice per orbit on a week-long orbit. We don't know how long until the solar wind and the gravity of the sun and the earth perturb it enough to disperse it. But until it's dispersed, it's going to be getting on the order of 2,000 impacts twice per orbit. A 200-ton lander, which might be, for example, a 100-ton lander with 100 tons of ascent propellant, that would blow about 1,570 tons of ejecta, according to the best theory we have today. So that's enough ejecta to fill a 2-story suburban home hard packed. And so therefore it would be quite a crater. And that would cause about 32,000 impacts per square meter, twice per orbit of the lunar gateway. So the result is the damage caused by large landers may be severe. This is preliminary work. More work is needed for confidence, obviously. This did not, as I said at the beginning, did not assess the bulk cratering phenomena. Those would likely aggravate the problem. So we do need instruments to measure these effects. We can't do the right experiments here on the Earth. And the final conclusion is we definitely need to develop mitigation methods like building landing pads on the moon. This is a consequence of it being an airless body. Okay, so that's it. Thank you for your attention.
Phil, thank you very much. You do have some questions in the chat room. So I think you almost answered the one from Rodrigo Romo. He said, it seems logical that a landing pad would significantly reduce the ejecta from a lander. Have you calculated or modeled how big does the landing pad have to be to safely eliminate risk to adjacent infrastructure?
Well, that's a work in progress, but I can tell you for a 40-ton lander, we did this, Paul Vansusante and I did some calculations, and we were estimating about a 20-meter diameter, maybe 23 meter, depends on the spacing of your engines. That would be sufficient to avoid all erosion. Obviously, the larger the lander, the larger the pad that you need.
Okay. Ijwal Rout asks, he says, a great talk. What's the lifetime on the impact rate in orbit?
Yeah, we don't know that. Josh Colwell at UCF has a student currently working on that. And so she's doing simulations of the three body problem, I guess, Earth and moon gravity with the dust. And then we have a postdoc who's going to put in the solar wind effects, but we won't have answers on that for a few more months at least.
Okay, I think we have time for just one more. Laurent Sibyl writes, do the predicted ejecta masses assume that the large landers use main engines for landings to within a few meters of the surface? What about ejected during launch from the surface?
Great questions, both. So I assumed the trajectory was the same as the lunar module, and I assumed engine cutoff. I think I assumed 1.5 meters above the surface, free falling the last little bit. So if you have the engines mounted higher, it will have a fantastically good effect in reducing the ejecta. That hasn't been quantified yet, but I have done enough work to know that it will be a dramatic reduction. Launching effects, you end up with a shock effect from engine ignition, and that shock effect is dramatically worse than the steady state flow effects, maybe almost an order of magnitude worse for a brief blast. So lighting an engine on the moon for a large lander with the engines mounted low is going to produce a very big blast of ejecta. There will also be acoustic issues. We usually don't think about acoustics on the moon because it's a vacuum. But when you've got that much gas around your lander, especially if you have a multi-engine lander with upward convection between the engines, that will couple acoustics back to the vehicle. So we do need to look at that as well.
Okay, I want to thank all our, thank you, Phil. I want to thank you, all our speakers. I think this has been a really dynamic discussion, a lot of really great presentations. I would like to, Ben and I would like to end the session and hand it over to Greg with sharing the results from our poll. So I'm assuming I hit share and that everyone can see that by 60%, Reiner Gamma is our favorite swirl region. Mare Engini follows with 20% of the remainder of the vote. So I hope you found that fun. I hope it got you in the spirit of our discussion, our dialogue. I would once again like to thank our speakers and our presenters. Ben, do you have anything you want to add? Anything you want to say?
Not particularly. Just want to say that, yeah, all the talks were really, really fantastic. I enjoyed hearing all of your presentations, and I think everything went pretty smoothly. Thank you for putting up with a little bit of disorganization from us. And yeah, I hope all y'all's research goes really, really well into the future. And yeah, that's about all I've got.
Okay, so with that, I want to pass things off to Greg. We have a great speaker coming up to wrap up this forum, and I'm looking forward to hearing what she has to say. Greg, take it away.
Excellent, excellent. Thank you so much. Thanks for an excellent last full session, and thanks to both of you for the great job chairing it. And Reiner Gamma, by the way, was my favorite as well. So I would like to introduce someone who in this community really doesn't need an introduction. Professor Carly Peters has been a faculty member at Brown since 1980, after having worked several years at JSC in Houston. And this is something I didn't know until recently as a Peace Corps volunteer. Her general research efforts include planetary exploration and evolution of planetary surfaces, with an emphasis on remote compositional analyses. She was the founder and initial science manager of the NASA Reflectance Experiment Laboratory, otherwise known as RELAB, a NASA-supported multi-user spectroscopy facility at Brown that operates from 0.3 to 25 microns. She's been principal investigator for NASA's Moon Mineralogy Mapper experiment, launched to the moon in 2008 aboard Chandrayaan-1, and is currently currently is not quite right, was co-investigator on Dawn, a mission to explore the large asteroids Vesta and Ceres. And she was amongst the first PIs at NLSI and was selected in the first round of PIs at Survey. So I'm delighted to share as well that we're in the process of bringing Dr. Peters on as Survey Distinguished Scientist. So I invited her to give us a talk on the importance of our moon. And so Carly, please go ahead. Thank you.
Unmute and share my screen. I think I've got it. Can you hear me?
Background.
Can you hear me?
Yes.
Okay. Well, first of all, it's been a fantastic couple of days. I've thoroughly enjoyed it. I'm sure we're all hyped up with a lot of exciting science. Some of it scary, like I think Phil really put terror in my heart. But okay, now we're going to go back to our current environment. And I want to just sort of step back and have a moment to think about some things that I think many of the things that I'm going to show you today are familiar to you. I hope some of them are new, but hopefully it will put things in perspective. Okay, so what is our current environment? Well, we all know it's this guy, which we don't really like, but our life has been pretty much altered as we're dealing with the coronavirus. Some of the outcomes are interesting, some of them are fun, like the kinds of meetings we've just had, and we're learning new ways of interacting. But I'd like to step out of that environment and now really just focus on our Earth-Moon environment, which is a broader perspective and is going to outlast our current environment. So with that sort of introduction of where I'm heading, there's a couple of things that you might want to note if they're not locked into your brain is what some of the distances are, namely the distance from the Earth to the Moon is about 0.4 million kilometers and the Earth's sun is about 150, because most of the images I'm going to be showing you, I'm going to be giving you scale, and it would be good to know the scale to translate into that. So 0.4 is Earth to the Moon, and Earth Moon to the sun is 150. Okay, well, the first Earthrise went back several decades ago with Lunar Orbiter 1 as it came around the moon and took this very famous shot from the moon looking at the Earth. And for those of you who followed what technology was available at that time, all these little stripes were because they were thin pieces of film that were developed on board, then scanned, then sent back to Earth. It was a marvelous achievement, but it did have the limitations of the technology at the time. Of course, since then, with all our capabilities in the present era, we've been able to restore some of the details with the kinds of computers that we now have. But nevertheless, this was the original character of that first image, looking from the moon towards the Earth. Well, a few years later, of course, Christmas Eve, Apollo 8 went around the moon, and this was the first time humans orbited the moon. And from the moon could look at planet Earth in its blue marble form, and brought the film back with the kind of resolution that film can achieve at that time. And this was an awesome image that we all felt inspired by. And of course, you all know how some of this story played out. Not long after that, humans landed on the moon. This picture I hadn't seen before, but in looking for images to show you today, this is when the first astronauts from the surface returned to orbit and reunited with Collins in orbit. I like to think that orange thing over on the side is Collins's thumb. I don't really know what it is, but this is the first humans returning from the moon and then returning back to our home planet Earth. Okay, and it's in that context that started the exploration of our Earth-Moon environment. Okay, here's again the numbers. Okay, now, a few years later, Mariner 10 set out to head to its rendezvous several times with Mercury and had a camera on board and looked back at the Earth and the Moon from 2.6 million kilometers. Didn't take these two in the same shot. They took the Earth and the Moon and processed them and made a composite together. But nevertheless, it was a really nice whole body image of our planet Earth and our moon. In the same geometry, you know, we know where the sun is and et cetera, et cetera. So this was really a nice understanding of our place in the solar system and how we appear in the space environment. This was the first picture taken by Voyager, of course, which is now exiting our solar system. And it's the first picture where the Earth and the Moon were as a whole planetary body taken together. I find this a remarkable image. 1977, pretty far away from the Earth, 11 plus a million kilometers. But nevertheless, it really, again, gives us the sense of how our Earth-Moon system is tied together in the solar system. This image was taken by the Galileo spacecraft on its way to Jupiter, of course. It's one of my favorites. It was one of the first images of the Earth-Moon taken with CCD technology. I have this hanging in my office, and when people come in to visit me, I'll ask them if they can look at this image and tell me whether the moon is on the far side of the Earth or on the near side of the Earth. Which side is the moon actually on? Clearly, the perspective has them together. And it takes a while. And I think the first person that got it really quick was a young teenager. And he said, oh, well, that's the far side of the moon. So the moon must be on this side of the Earth. And I said, wonderful, you've got it. You understand how everything is put together. It was a delight to hear someone recognize that right away. Well, okay, moving on. That was 1992. And here is this wonderful image created by the Kage spacecraft a decade or two later, that again is a real time sequence of the Earthrise. It's one of the most dramatic images, I think, that brings the concept of our relationships between the Earth and the Moon together. Really a delightful sequence. Here's another one, not long after that, taken by Messenger on its way to Mercury, pretty far away. Notice it's 183 million kilometers. And of course, if you can't see it, that's the Earth and the Moon right there. So it's pretty far away. It's probably overexposed because you see these two little dots. But you see there are two dots and they're close together, and it is the Earth-Moon system. from very far away. Okay, here's one that I hadn't seen before. It's, excuse me, more recent, taken by the Chang'e 5 test vehicle. And you can tell it's on the far side of the moon. You know it has this large extended orbit. You can probably recognize the parts of the moon. You can see Giordano Bruno, you can see Moscoviense, and of course the Earth in the distance. So it's the kind of perspective that we haven't seen very frequently yet. Here's one of my new favorites that was a surprise when I was looking at this, and you have to think about this carefully. This is taken by the Solar Dynamics Observatory, which is in an inclined geosynchronous orbit. And I call it a family portrait because it has this particular orbit for this satellite, which is to study the sun, was selected so that it could stare at the sun pretty continuously. But about twice a year, it would go into an eclipse with the Earth. And when it does that, of course, the Earth has an atmosphere and it's not a sharp edge. But another about 3 times a year, given the geometry of this satellite, the moon will cross the path. Well, in this particular time, in September of 2015, it have both the Earth and the sun and the moon all together. And the difference and the distinction of each of the 3, I love. This is one of my favorites now. Here's a picture that I think everyone recognizes, and I notice many of you have used it as a backdrop. It is a beautiful image that LRO has produced, which is on many people's backdrop for a good reason. I don't need to tell you much more about this. It is, again, a favorite, clearly, for many of us in this chat room. Here's another one that maybe you've seen, maybe you haven't. It's the Deep Space Climate Observatory, which is it's a satellite placed at the L1 position. So it's between the Earth and the sun at 1.5 million kilometers. And in that position, because it's in the L1, it essentially gets a full illumination of the Earth. And that's one of its principal objectives, is to understand the whole deep space climate environment. But of course, from time to time, the moon crosses its path. And of course, it's a bit further away. And it again has full illumination on the moon. And you can recognize that this is the far side of the moon that we're looking at. You can see South Pole Aiken and Moscoviense up there, but it's a wonderful view that we don't see all that often. Here's one I had not seen before. This is our Earth-Moon system from Mars. It's using the HiRISE camera, which, as you know, looks at Mars with very high resolution, but it has sufficient resolution to get, again, a Earth-Moon portrait from 205 million kilometers away. You can see in the Earth part, there's Antarctica and Australia and Asia in the upper right. And if you do the same sort of thing that I queried about with the Galileo image, okay, we have the moon, here's the Earth. Is the moon on this side of the Earth or is it on the other side of the Earth? And I hope every one of you can immediately say which side it's on. I'll put that in the quiz, and anybody who fails the quiz gets a negative point. Okay, here's my next to the last slide because it's back to present. And it was a photograph taken by a 747 airline pilot, commercial pilot at 40,000 feet. And I'd like to read the comments that he made associated with this lovely picture that he took. And it brings us back, in fact, to the present. Global society came to a total standstill after the uncontrolled outbreak of this strange new virus. Deserted streets, empty airspaces, entire populations locked in their homes, and a gigantic economic crash that leaves us with more questions than answers. Flying as a long-range cargo pilot, I appreciate my flights even more than before, as passenger flights have been grounded overnight, entire fleets parked indefinitely, tens of thousands of airline employees discharged or furloughed. And yet, here I am, skimming through the stratosphere, one of the very few unfortunate ones to keep on flying. Armed with masks, gloves, disinfectant gels, we continue to provide medical supplies, food, toilet paper, and other essential goods by air bridge across oceans and continents. The clouds, the calming blue ocean, the glow of Earth's atmosphere slowly blending into the infinite void of space. Well, technically, space is not looking entirely empty at this time. The moon rises on schedule, as she did undisturbed for billions of years and will continue to do so for many more. In a way, it's reassuring to see that the universe really keeps on going, with or without lockdown and virus. Clouds form, grow, and dissipate. Meteors trail across the stars, and auroras dance vividly in the midnight sky. No matter how bleak or depressing life may seem to many of us right now, try to keep in mind that we will get through all this eventually. Just like the moon evolves through her phases and hides again in shadows, only to start her silent show of light and darkness all over again. Okay, going on to my last slide, just a reminder of where we're going. This goes back a few years, of course, to Apollo 17's. And this is when all three astronauts were in the module and were heading for home. I like this image very much. Largely when I see the moon in the evening, especially the new moon, it always seems to be smiling, you know, sort of a Cheshire cat smiling, saying, yeah, we're all here. And now it's sort of in a reverse mode where the astronauts are at the moon and they're looking at the Earth, they're smiling and heading to home. And that's what's going to be continued. Good luck to everyone. Have a wonderful time. Bye-bye.
Thank you, Carly. Wow. Wow. That was rather powerful, I'd say. I didn't know exactly what to expect, but I knew it was going to be amazing, and it sure has been. So I want to put this up on our website. So thank you so much for giving us a little bit of perspective at the end. And so I now want to say a few closing remarks. I'm going to start with some thank yous. I want to thank all of our presenters, of course, for the fabulous presentations that we've heard the last 3 days. I want to thank our session chairs, with a particular thanks to our next gen session chairs. Quite honestly, that worked out so well that that's a permanent feature of the forum from now on. I want to thank the poster presenters for willing to engage with us in an experiment. By the discussions that I've heard, I think it was a success, but we want your opinions on that. I want to thank the SOC for its invaluable help in creating such a great program. And in particular, thank the chairs, Rachel, Tobin, and David, for all their hard work over a period of months. Not knowing what kind of an event this was going to be, not knowing how many people were going to come. I want to thank our student poster judges. Christina's already sent a note to them, but just add my thanks to that. And then let me share my screen here. Let's see, hang on, give me just a second. Here we go. And I want to share a little picture of our team right here. And so we, Christina and I asked the team to take pictures of themselves at their various home stations. Me at the upper left, there's Christina just to my right, Ricky Gibbs, there is Maria and Milo, and gosh, fortunately my screen is blocking things, so I hope I can see the small version of this. Yvonne Ibera, our fearless administrative assistant, Brian Day, Ashkan Najad, and unfortunately it's being blocked. Christina, can you read the rest for me, please? I can see Teague. Anyway.
Yeah, Teague. We've got Yvonne, Jen, Joe, and Ashkan on the bottom, and Brian on the right.
Great.
We got everybody.
Great. Thank you. Thank you. So anyway, this. Obviously, this conference wouldn't have happened without them, and I want to give a particular thanks to Christina for her expert leadership of this event. You know, it was just fabulous, and I really feel very lucky to have Christina as my deputy for Survey. I will also want to congratulate the award winners. And then I want to say that that the survey is up on the forum webpage, and the day 2 recordings are already up, and the day 3 recordings today will be up fairly soon. And so this meeting's been about sharing great science and exploration, of course, and I hope that we've done that well. But it's also been about bringing people together. I knew this was going to happen, and probably those of you who know me well knew that too. But this was a theme that was echoed in a lot of ways by our award winners yesterday. So I hope you leave with a feeling that as much as technology will allow, pardon me, you've gotten at least a few steps closer to all the people in the community we value so much. Thank you. Thanks so much. Bye-bye.
Thank you, Greg.
Thanks, Greg. Jim Head, thanks so much. You know, and also special thanks to Ricky Guest. I can't imagine that this would have gone so well without his real incredible capabilities, and it went seamlessly.
Thanks, Jim. Thanks. I appreciate that. And that's absolutely true.
It is absolutely true. I also want to say Ashkan and Maria, they pulled off some amazing feats with the poster sessions. And so Ricky and Ashkan and Maria have worked so amazingly in concert, and I just want to thank them all.
Greg and Christina, you and your team put together a fabulous forum. You have been keeping us all connected and staying excited about going to the moon. So congratulations on a job well done. Thank you very much.
Thank you. It's quite a privilege.
Mm-hmm.
So we'll look forward to seeing all you guys next year, and I sure hope it's in person.
Yeah, I sure do too.
I think they deserve a big round of applause.
Yay!
Thanks, Amy. All right. Take care,
All
everyone.
right.
Be well, everyone.
Take care.
Bye-bye.
Stay safe.
Bye.